Section 0 Introduction of Creative Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adam Marsatich, Alexandria, Virginia, 2010. Creative Chemistry by Edwin E. Slosson. Introduction by Julius Stieglitz, formerly president of the American Chemical Society, professor of chemistry in the University of Chicago. The recent war, as never before in the history of the world, brought to the nations of the earth a realization of the vital place which the science of chemistry holds in the development of the resources of a nation. Some of the most picturesque features of this awakening reached the great public through the press. Thus, the adventurous trips of the Deutschland, with its cargoes of concentrated aniline dyes, valued at millions of dollars, emphasized as no other incident our former dependence upon Germany for these products of her chemical industries. The public read, too, that her chemists saved Germany from an early disastrous defeat, both in the field of military operations and in the matter of economic supplies. Unquestionably, without the tremendous expansion of her plants for the production of nitrates and ammonia from the air by the process of Haber, Ostwald, and others of her great chemists, the war would have ended in 1915 or early in 1916 from exhaustion of Germany's supplies of nitrate explosives, if not indeed from exhaustion of her food supplies as a consequence of the lack of nitrate and ammonia fertilizer for her fields. Inventions of substitutes for cotton, copper, rubber, wool, and many other basic needs have been reported. These feats of chemistry, performed under the stress of dire necessity, have, no doubt, excited the wonder and interest of our public. It is far more important at this time, however, when both for war and for peace needs the resources of our country are strained to the utmost, that the public should awaken to a clear realization of what this science of chemistry really means for mankind, to the realization that its wizardry permeates the whole life of the nation as a vitalizing, protective, and constructive agent very much in the same way as our blood, coursing through our veins and arteries, carries the constructive, defensive, and life-bringing materials to every organ in the body. If the layman will but understand that chemistry is the fundamental science of the transformation of matter, he will readily accept the validity of this sweeping assertion. He will realize, for instance, why exactly the same fundamental laws of the science apply to, and make possible scientific control of, such widely divergent national industries as agriculture and steel manufacturing. It governs the transformation of the salts, minerals, and humus of our fields and the components of the air into corn, wheat, cotton, and the innumerable other products of the soil. It governs no less the transformation of crude ores into steel and alloys, which, with the cunning born of chemical knowledge, may be given practically any conceivable quality of hardness, elasticity, toughness, or strength. And exactly the same thing may be said of the hundreds of national activities that lie between the two extremes of agriculture and steel manufacture. Moreover, the domain of the science of the transformation of matter includes even life itself as its loftiest place. From our birth to our return to dust, the laws of chemistry are the controlling laws of life, health, disease, and death and the ever clearer recognition of this relation is the strongest force that is raising medicine from the uncertain realm of an art to the safer sphere of an exact science. To many scientific minds it has even become evident that those most wonderful facts of life, heredity and character, must find their final explanation in the chemical composition of the components of life-producing, germinal protoplasm. Mere form and shape are no longer supreme, but are relegated to their proper place as the housing only of the living matter which functions chemically. It must be quite obvious now why thoughtful men are insisting that the public should be awakened to a broad realization of the significance of the science of chemistry for its national life. It is a difficult science in its details because it has found that it can best interpret the visible phenomena of the material world on the basis of the conception of invisible minute material atoms and molecules, each a world in itself, whose properties may be nevertheless accurately deduced by a rigorous logic controlling the highest type of scientific imagination. But a layman is interested in the wonders of great bridges and of monumental buildings, without feeling the need of inquiring into the painfully minute and extended calculations of the engineer and architect, of the strains and stresses to which every pin and every bar of the great bridge, and every bit of stone, every foot of arch in a monumental edifice, will be exposed. So the public may understand and appreciate with the keenest interest the results of chemical effort without the need of instruction in the intricacies of our logic, of our dealings with our minute, invisible particles. The whole nation's welfare demands, indeed, that our public be enlightened in the matter of the relation of chemistry to our national life. Thus, if our commerce and our industries are to survive the terrific competition that must follow the reestablishment of peace, our public must insist that its representatives in Congress preserve that independence in chemical manufacturing which the war has forced upon us in the matter of dyes, of numberless invaluable remedies to cure and relieve suffering, in the matter, too, of hundreds of chemicals which our industries need for their successful existence. Unless we are independent in these fields, how easily might an unscrupulous competing nation do us untold harm by the mere device, for instance, of delaying supplies, or by sending inferior materials to this country, or by underselling our chemical manufacturers, and, after the destruction of our chemical independence, handicapping our industries as they were in the first year or two of the Great War. This is not a mere possibility created by the imagination, for our economic history contains instance after instance of the purposeful undermining and destruction of our industries in finer chemicals, dyes and drugs by foreign interests bent on preserving their monopoly. If one recalls that through control, for instance, of dyes by a competing nation, control is in fact also established over products, valued in the hundreds of millions of dollars, in which dyes enter as an essential factor, one may realize indeed the tremendous industrial and commercial power which is controlled by the single lever, chemical dyes. Of even more vital moment is chemistry in the domain of health. The pitiful calls of our hospitals for local anesthetics to alleviate suffering on the operating table, the frantic appeals for the hypnotic that soothes the epileptic and staves off his seizure, the almost furious demands for remedy after remedy that came in the early years of the war, are still ringing in the hearts of many of us. No wonder that our small army of chemists is grimly determined not to give up the independence in chemistry which war has achieved for us. Only a widely enlightened public, however, can ensure the permanence of what far-seeing men have started to accomplish in developing the power of chemistry through research in every domain which chemistry touches. The general public should realize that in the support of great chemical research, laboratories of universities and technical schools, it will be sustaining important centers from which the science which improves products, abolishes waste, establishes new industries and preserves life, may reach out helpfully into all the activities of our great nation that are dependent on the transformation of matter. The public is to be congratulated upon the fact that the writer of the present volume is better qualified than any other man in the country to bring home to his readers some of the great results of modern chemical activity as well as some of the big problems which must continue to engage the attention of our chemists. Dr. Slosson has indeed the unique quality of combining an exact and intimate knowledge of chemistry with the exquisite clarity and pointedness of expression of a born writer. We have here an exposition by a master mind, an exposition shorn of the terrifying and obscuring technicalities of the lecture room, that will be as absorbing reading as any thrilling romance, for the story of scientific achievement is the greatest epic the world has ever known, and like the great national epics of bygone ages, should quicken the life of the nation by a realization of its powers and a picture of its possibilities.
Creative Chemistry. La chimie possède cette faculté créatrice à un degré plus éminent que les autres sciences parce qu'elle pénètre plus profondément et atteint jusqu'aux éléments naturels des êtres. Berthelot. Cet enregistrement fait partie du domaine public.
End of section 0. End of introduction. Section 1, Chapter 1 of Creative Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adam Marsatich, Alexandria, Virginia, 2010. Creative Chemistry by Edwin E. Slosson. Chapter 1. 3 Periods of Progress. The story of Robinson Crusoe is an allegory of human history. Man is a castaway upon a desert planet, isolated from other inhabited worlds, if there be any such, by millions of miles of untraversable space. He is absolutely dependent upon his own exertions, for this world of his, as Wells says, has no imports except meteorites and no exports of any kind. Man has no wrecked ship from a former civilization to draw upon for tools and weapons, but must utilize as best he may such raw materials as he can find. In this conquest of nature by man there are 3 stages distinguishable. 1. The approbative period. 2. The adaptive period. 3. The creative period. These areas overlap, and the human race, or rather its vanguard, civilized man, may be passing into the 3rd stage in one field of human endeavor while still lingering in the 2nd or 1st in some other respect. But in any particular line, this sequence is followed. The primitive man picks up whatever he can find available for his use. His successor in the next stage of culture shapes and develops this crude instrument until it becomes more suitable for his purpose. But in the course of time, man often finds that he can make something new which is better than anything in nature or naturally produced. The savage discovers, the barbarian improves, the civilized man invents, the first finds, the second fashions, the third fabricates. The primitive man was a troglodyte. He sought shelter in any cave or crevice that he could find. Later he dug it out to make it more roomy and piled up stones at the entrance to keep out the wild beasts. This artificial barricade, this false facade, was gradually extended and solidified until finally man could build a cave for himself anywhere in the open field from stones he quarried out of the hill. But man was not content with such materials and now puts up a building which may be composed of steel, brick, terracotta, glass, concrete, and plaster, none of which materials are to be found in nature. The untutored savage might cross a stream astride a floating tree trunk. By and by it occurred to him to sit inside the log instead of on it, so he hollowed it out with fire or flint. Later, much later, he constructed an ocean liner. Cain, or whoever it was first slew his brother man, made use of a stone or stick. Afterward, it was found a better weapon could be made by tying the stone to the end of the stick, and as murder developed into a fine art the stick was converted into the bow, and this into the catapult, and finally into the cannon, while the stone was developed into the high explosive projectile. The first music to soothe the savage breast was the soughing of the wind through the trees. Then strings were stretched across a crevice for the wind to play upon, and there was the Aeolian harp. The second stage was entered when Hermes strung the tortoise shell and plucked it with his fingers, and when Athena, raising the wind from her own lungs, forced it through a hollow reed. From these beginnings we have the organ and the orchestra, producing such sounds as nothing in nature can equal. The first idol was doubtless a meteorite fallen from heaven, or a fulgurite or concretion picked up from the sand, bearing some slight resemblance to a human being. Later man made gods in his own image, and so sculpture and painting grew until now the creations of futuristic art could be worshipped, if one wanted to, without violation of the second commandment, for they are not the likeness of anything that is in heaven above, or that is in the earth beneath, or that is in the water under the earth. In the textile industry the same development is observable. The primitive man used the skins of animals he had slain to protect his own skin. In the course of time he, or more probably his wife, for it is to the women rather than to the men that we owe the early steps in the arts and sciences, fastened leaves together or pounded bark to make garments. Later fibers were plucked from the sheepskin, the cocoon, and the cotton ball, twisted together and woven into cloth. Nowadays it is possible to make a complete suit of clothes, from hat to shoes, of any desirable texture, form, and color, and not include any substance to be found in nature. The first metals available were those found free in nature, such as gold and copper. In a later age it was found possible to extract iron from ores, and today we have artificial alloys made of multifarious combinations of rare metals. The medicine man dosed his patients with decoctions of such roots and herbs as had a bad taste or queer look. The pharmacist discovered how to extract from these their medicinal principle, such as morphine, quinine, and cocaine, and the creative chemist has discovered how to make innumerable drugs adapted to specific diseases and individual idiosyncrasies. In the later or creative stages we enter the domain of chemistry, for it is the chemist alone who possesses the power of reducing a substance to its constituent atoms and from them producing substances entirely new. But the chemist has been slow to realize his unique power, and the world has been still slower to utilize his invaluable services. Until recently, indeed, the leaders of chemical science expressly disclaimed what should have been their proudest boast. The French chemist Lavoisier in 1793 defined chemistry as the science of analysis. The German chemist Gerhardt in 1844 said, "I have demonstrated that the chemist works in opposition to living nature, that he burns, destroys, analyzes, that the vital force alone operates by synthesis, that it reconstructs the edifice torn down by the chemical forces." It is quite true that chemists up to the middle of the last century were so absorbed in the destructive side of their science that they were blind to the constructive side of it. In this respect, they were less prescient than their contemned predecessors, the alchemists, who, foolish and pretentious as they were, aspired at least to the formation of something new. It was, I think, the French chemist Berthelot who first clearly perceived the double aspect of chemistry, for he defined it as the science of analysis and synthesis, of taking apart and of putting together. The motto of chemistry, as of all the empirical sciences, is savoir c'est pouvoir, to know in order to do. This is the pragmatic test of all useful knowledge. Berthelot goes on to say, "Chemistry creates its object. This creative faculty, comparable to that of art itself, distinguishes it essentially from the natural and historical sciences. These sciences do not control their object. Thus they are too often condemned to an eternal impotence in the search for truth of which they must content themselves with possessing some few and often uncertain fragments. On the contrary, the experimental sciences have the power to realize their conjectures, what they dream of that they can manifest in actuality. Chemistry possesses this creative faculty to a more eminent degree than the other sciences because it penetrates more profoundly and attains even to the natural elements of existences. Since Berthelot's time, that is, within the last 50 years, chemistry has won its chief triumphs in the field of synthesis. Organic chemistry, that is, the chemistry of the carbon compounds, so called because it was formerly assumed, as Gerhardt says, that they could only be formed by vital force of organized plants and animals, has taken a development far overshadowing inorganic chemistry or the chemistry of mineral substances. Chemists have prepared or know how to prepare hundreds of thousands of such organic compounds, few of which occur in the natural world. But this conception of chemistry is yet far from having been accepted by the world at large. This was brought forcibly to my attention during the publication of these chapters in The Independent by various letters, raising such objections as the following. When you say in your article on What Comes from Coal Tar that art can go ahead of nature in the dye-stuff business, you have doubtless for the moment allowed your enthusiasm to sweep you away from the moorings of reason. Shakespeare, anticipating you and your creative chemistry, has shown the utter untenableness of your position. Nature is made better by no mean, but nature makes that mean, so or that art, which, you say, adds to nature is an art that nature makes. How can you say that art surpasses nature when you know very well that nothing man is able to make can in any way equal the perfection of all nature's products? It is blasphemous of you to claim that man can improve the works of God as they appear in nature. Only the Creator can create. Man only imitates, destroys, or defiles God's handiwork. No, it was not in momentary absence of mind that I claimed that man could improve upon nature in the making of dyes. I not only said it, but I proved it. I not only proved it, but I can back it up. I will give $1,000,000 to anybody finding in nature dyestuffs as numerous, varied, brilliant, pure and cheap as those that are manufactured in the laboratory. I haven't that amount of money with me at the moment, but the dyers would be glad to put it up for the discovery of a satisfactory natural source for their tinctorial materials. This is not an opinion of mine, but a matter of fact, not to be decided by Shakespeare, who is not acquainted with the aniline products. Shakespeare in the passage quoted is indulging in his favorite amusement of a play upon words. There is a possible and a proper sense of the word nature that makes it include everything except the supernatural. Therefore, man and all his works belong to the realm of nature. A tenement house in this sense is as natural as a bird's nest, a pea pod, or a crystal. But such a wide extension of the term destroys its distinctive value. It is more convenient and quite as correct to use nature as I have used it, in contradistinction to art, meaning by the former the products of the mineral, vegetable, and animal kingdoms, excluding the designs, inventions, and constructions of man which we call art. We cannot, in a general and abstract fashion, say which is superior, art or nature, because it all depends on the point of view. The worm loves a rotten log into which he can bore. Man prefers a steel cabinet into which the worm cannot bore. If man cannot improve upon nature, he has no motive for making anything. Artificial products are therefore superior to natural products as measured by man's convenience, otherwise they would have no reason for existence. Science and Christianity are at one in abhorring the natural man and calling upon the civilized man to fight and subdue him. The conquest of nature, not the imitation of nature, is the whole duty of man. Metchnikoff and St. Paul unite in criticizing the body we were born with. St. Augustine and Huxley are in agreement as to the eternal conflict between man and nature. In his Romanes lecture on Evolution and Ethics, Huxley said, "The ethical progress of society depends, not on imitating the cosmic process, still less on running away from it, but on combating it." And again, "The history of civilization details the steps by which man has succeeded in building up an artificial world within the cosmos." There speaks the true evolutionist, whose one desire is to get away from nature as fast and far as possible. Imitate nature? Yes, when we cannot improve upon her. Admire nature? Possibly, but not be blinded to her defects. Learn from nature? We should sit humbly at her feet until we can stand erect and go our own way. Love nature? Never! She is our treacherous and unsleeping foe, ever to be feared and watched and circumvented, for at any moment, and in spite of all our vigilance, she may wipe out the human race by famine, pestilence, or earthquake, and within a few centuries obliterate every trace of its achievement. The wild beasts that man has kept at bay for a few centuries will in the end invade his palaces. The moss will envelop his walls and the lichen disrupt them. The clam may survive man by as many millennia as it preceded him. In the ultimate devolution of the world animal life will disappear before vegetable, the higher plants will be killed off before the lower, and finally the three kingdoms of nature will be reduced to one, the mineral. Civilized man, enthroned in his citadel and defended by all the forces of nature that he has brought under his control, is, after all, in the same situation as a savage, shivering in the darkness beside his fire, listening to the pad of predatory feet, the rustle of serpents, and the cry of birds of prey, knowing that only the fire keeps his enemies off, but knowing too that every stick he lays on the fire lessens his fuel supply and hastens the inevitable time when the beasts of the jungle will make their fatal rush. Chaos is the natural state of the universe. Cosmos is the rare and temporary exception. Of all the million spheres, this is apparently the only one habitable, and of this only a small part, the reader may draw the boundaries to suit himself, can be called civilized. Anarchy is the natural state of the human race. It prevailed exclusively all over the world up to some 5,000 years ago, since which a few peoples have for a time succeeded in establishing a certain degree of peace and order. This, however, can be maintained only by strenuous and persistent efforts, for society tends naturally to sink into the chaos out of which it has arisen. It is only by overcoming nature that man can rise. The sole salvation for the human race lies in the removal of the primal curse, the sentence of hard labor for life that was imposed on man as he left paradise. Some folks are trying to elevate the laboring classes. Some are trying to keep them down. The scientist has a more radical remedy. He wants to annihilate the laboring classes by abolishing labor. There is no longer any need for human labor in the sense of personal toil, for the physical energy necessary to accomplish all kinds of work may be obtained from external sources, and it can be directed and controlled without extreme exertion. Man's first effort in this direction was to throw part of his burden upon the horse and ox or upon other men. But within the last century it has been discovered that neither human nor animal servitude is necessary to give man leisure for the higher life, for by means of the machine he can do the work of giants without exhaustion. But the introduction of machines, like every other step of human progress, met with the most violent opposition from those it was to benefit. "Smash 'em!" cried the working man. "Smash 'em!" cried the poet. "Smash 'em!" cried the artist. "Smash 'em!" cried the theologian. "Smash 'em!" cried the magistrate. This opposition yet lingers, and every new invention, especially in chemistry, is greeted with general distrust and often with legislative prohibition. Man is the tool-using animal, and the machine, that is, the power-driven tool, is his peculiar achievement. It is purely a creation of the human mind. The wheel, its essential feature, does not exist in nature. The lever, with its to and fro motion, we find in the limbs of all animals, but the continuous revolving lever, the wheel, cannot be formed of bone and flesh. Man as a motive power is a poor thing. He can only convert 3,000 or 4,000 calories of energy a day, and he does that very inefficiently. But he can make an engine that will handle 100,000 times that, twice as efficiently and 3 times as long. In this way only can he get rid of pain and toil and gain the wealth he wants. Gradually, then, he will substitute for the natural world an artificial world, molded nearer to his heart's desire. Man the artifex will ultimately master nature and reign supreme over his own creation until chaos shall come again. In the ancient drama it was Deus ex machina that came in at the end to solve the problems of the play. It is to the same supernatural agency, the divinity in machinery, that we must look for the salvation of society. It is by means of applied science that the earth can be made habitable and a decent human life made possible. Creative evolution is at last becoming conscious. End of chapter 1. Section 2, Chapter 2 of Creative Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adam Marsatich, Alexandria, Virginia, 2010. Creative Chemistry by Edwin E. Slosson. Chapter 2. Nitrogen, Preserver and Destroyer of Life. In the eyes of the chemist, the Great War was essentially a series of explosive reactions resulting in the liberation of nitrogen. Nothing like it has been seen in any previous wars. The first battles were fought with cellulose, mostly in the form of clubs. The next were fought with silica, mostly in the form of flint arrowheads and spear points. Then came the metals, bronze to begin with and later iron. The nitrogenous era in warfare began when Friar Roger Bacon or Friar Schwartz, whichever it was, ground together in his mortar saltpeter, charcoal, and sulfur. The Chinese, to be sure, had invented gunpowder long before, but they, poor innocents, did not know of anything worse to do with it than to make it into firecrackers. With the introduction of villainous saltpeter, war ceased to be the vocation of the nobleman, and since the nobleman had no other vocation, he began to become extinct. A bullet fired from a mile away is no respecter of persons. It is just as likely to kill a knight as a peasant, and a brave man as a coward. You cannot fence with a cannon ball, nor overawe it with a plumed hat. The only thing you can do is to hide and shoot back. Now you cannot hide if you send up a column of smoke by day and a pillar of fire by night, the most conspicuous of signals, every time you shoot. So the next step was the invention of a smokeless powder. In this, the oxygen necessary for the combustion is already in such close combination with its fuel, the carbon and hydrogen, that no black particles of carbon can get away unburnt. In the old-fashioned gunpowder, the oxygen necessary for the combustion of the carbon and sulfur was in a separate package, in the molecule of potassium nitrate, and however finely the mixture was ground, some of the atoms, in the excitement of the explosion, failed to find their proper partners at the moment of dispersal. The new gunpowder, besides being smokeless, is ashless. There is no black sticky mass of potassium salts left to foul the gun barrel. The gunpowder period of warfare was actively initiated at the Battle of Crécy, in which, as a contemporary historian says, the English guns made noise like thunder and caused much loss in men and horses. Smokeless powder, as invented by Paul Viel, was adopted by the French government in 1887. This, then, might be called the beginning of the guncotton or nitrocellulose period, or, perhaps in deference to the caveman's club, the second cellulose period of human warfare. Better, doubtless, to call it the high explosive period, for various other nitro compounds besides guncotton are being used. The important thing to note is that all the explosives from gunpowder down contain nitrogen as the essential element. It is customary to call nitrogen an inert element because it was hard to get it into combination with other elements. It might, on the other hand, be looked upon as an active element, because it acts so energetically in getting out of its compounds. We can dodge the question by saying that nitrogen is a most unreliable and unsociable element. Like Kipling's cat, it walks by its wild lone. It is not so bad as argon the lazy and the other celibate gases of that family, where each individual atom goes off by itself and absolutely refuses to unite even temporarily with any other atom. The nitrogen atoms will pair off with each other and stick together, but they are reluctant to associate with other elements, and when they do, the combination is likely to break up any moment. You all know people like that, good enough when by themselves, but sure to break up any club, church, or society they get into. Now, the value of nitrogen in warfare is due to the fact that all the atoms desert in a body on the field of battle. Millions of them may be lying packed in a gun cartridge, as quiet as you please, but let a little disturbance start in the neighborhood, say a grain of mercury fulminate flares up, and all the nitrogen atoms get to trembling so violently that they cannot be restrained. The shock spreads rapidly through the whole mass. The hydrogen and carbon atoms catch up the oxygen, and in an instant they are off on a stampede, crowding in every direction to find an exit, and getting more heated up all the time. The only movable side is the cannonball in front, so they all pound against that and give it such a shove that it goes 10 miles before it stops. The external bombardment by the cannonball is, therefore, preceded by an internal bombardment on the cannonball by the molecules of the hot gases, whose speed is about as great as the speed of the projectile that they propel. The active agent in all these explosives is the nitrogen atom in combination with two oxygen atoms, which the chemist calls the nitro group and which he represents by NO2. This group was, as I have said, originally used in the form of saltpeter or potassium nitrate, but since the chemist did not want the potassium part of it, for it fouled his guns, he took the nitro group out of the nitrate by means of sulfuric acid, and by the same means hooked it on to some compound of carbon and hydrogen that would burn without leaving any residue, and give nothing but gases. One of the simplest of these hydrocarbon derivatives is glycerin, the same as you use for sunburn. This mixed with nitric and sulfuric acids gives nitroglycerin, an easy thing to make, though I should not advise anybody to try making it unless he has his life insured. But nitroglycerin is uncertain stuff to keep and, being a liquid, is awkward to handle. So it was mixed with sawdust or porous earth or something else that would soak it up. This molded into sticks is our ordinary dynamite. Instead of glycerin, we take cellulose in the form of wood pulp or cotton and treat this with nitric acid. In the presence of sulfuric, we get nitrocellulose or gun cotton, which is the chief ingredient of smokeless powder. Now, gun cotton looks like common cotton. It is too light and loose to pack well into a gun. So it is dissolved with ether and alcohol or acetone to make a plastic mass that can be molded into rods and cut into grains of suitable shape and size to burn at the proper speed. Here, then, we have a liquid explosive, nitroglycerin, that has to be soaked up in some porous solid, and a porous solid, gun cotton, that has to soak up some liquid. Why not solve both difficulties together by dissolving the gun cotton in the nitroglycerin and so get a double explosive? This is a simple idea. Any of us can see the sense of it, once it is suggested to us. But Alfred Nobel, the Swedish chemist, who thought it out first in 1878, made millions out of it. Then, apparently alarmed at the possible consequences of his invention, he bequeathed the fortune he had made by it to found international prizes for medical, chemical, and physical discoveries, idealistic literature, and the promotion of peace. But his posthumous efforts for the advancement of civilization and the abolition of war did not amount to much, and his high explosives were later employed to blow into pieces the doctors, chemists, authors, and pacifists he wished to reward. Nobel's invention, cordite, is composed of nitroglycerin and nitrocellulose with a little mineral jelly or vaseline. Besides cordite and similar mixtures of nitroglycerin and nitrocellulose, there are two other classes of high explosives in common use. One is made from carbolic acid, which is familiar to us all by its use as a disinfectant. If this is treated with nitric and sulfuric acids, we get from it picric acid, a yellow crystalline solid. Every government has its own secret formula for this type of explosive. The British call theirs lyddite, the French melinite, and the Japanese shimose. The third kind of high explosives uses as its base toluol. This is not so familiar to us as glycerin, cotton, or carbolic acid. It is one of the coal tar products, an inflammable liquid resembling benzene. When treated with nitric acid in the usual way, it takes up like the others 3 nitro groups and so becomes trinitrotoluol. Realizing that people could not be expected to use such a mouthful of a word, the chemists have suggested various pretty nicknames: trotyl, tritol, trinol, tolite, and trilit, but the public, with the wistfulness it always shows in the matter of names, persists in calling it TNT, as though it were an author like GBS or GKC or FPA. TNT is the latest of these high explosives and in some ways the best of them. Picric acid has the bad habit of attacking the metals with which it rests in contact, forming sensitive picrates that are easily set off. But TNT is inert towards metals and keeps well. TNT melts far below the boiling point of water, so can be readily liquefied and poured into shells. It is insensitive to ordinary shocks. A rifle bullet can be fired through a case of it without setting it off, and if lighted with a match it burns quietly. The amazing thing about these modern explosives, the organic nitrates, is the way they will stand banging about and burning. Yet the terrific violence with which they blow up when shaken by an explosive wave of a particular velocity, like that of a fulminating cap. Like picric acid, TNT stains the skin yellow and causes soreness and sometimes serious cases of poisoning among the employees, mostly girls, in the munition factories. On the other hand, the girls working with cordite get to using it as a chewing gum, a harmful habit, not because of any danger of being blown up by it, but because nitroglycerin is a heart stimulant and they do not need that. TNT is by no means smokeless. The German shells that exploded with a cloud of black smoke and which British soldiers called Black Marias, coal boxes, or Jack Johnsons, were loaded with it. But it is an advantage to have a shell show where it strikes, although a disadvantage to have it show where it starts. It is these high explosives that have revolutionized warfare. As soon as the first German shell packed with these new nitrates burst inside the Gruson cupola at Liège and tore out its steel and concrete by the roots, the world knew that the day of the fixed fortress was gone. The armies deserted their expensively prepared fortifications and took to the trenches. The British troops in France found their weapons futile and sent across the Channel the cry of "Send us high explosives or we perish." The home government was slow to heed the appeal, but no progress was made against the Germans until the Allies had the means to blast them out of their entrenchments by shells loaded with 500 pounds of TNT. All these explosives are made from nitric acid, and this used to be made from nitrates such as potassium nitrate or saltpeter, but nitrates are rarely found in large quantities. Napoleon and Lee had a hard time to scrape up enough saltpeter from the compost heaps, cellars, and caves for their gunpowder, and they did not use as much nitrogen in a whole campaign as was freed in a few days' cannonading on the Somme. Now there is one place in the world, and so far as we know one only, where nitrates are to be found abundantly. This is in a desert on the western slope of the Andes, where ancient guano deposits have decomposed and there was not enough rain to wash away their salts. Here is a bed 2 miles wide, 200 miles long, and 5 feet deep, yielding some 20 to 50% of sodium nitrate. The deposit originally belonged to Peru, but Chile fought her for it and got it in 1881. Here all countries came to get their nitrates for agriculture and powder making. Germany was the largest customer and imported 750,000 tons of Chilean nitrate in 1913, besides using 100,000 tons of other nitrogen salts. By this means, her old, worn-out fields were made to yield greater harvests than our fresh land. Germany and England were like two duelists buying powder at the same shop. The Chilean government, pocketing an export duty that aggregated $500 million, permitted the saltpeter to be shoveled impartially into British and German ships, and so two nitrogen atoms, torn from their Pacific home and parted, like Evangeline and Gabriel, by transportation over sea, may have found themselves flung into each other's arms from the mouths of opposing howitzers in the air of Flanders. Goethe could write a romance on such a theme. Now the moment war broke out, this source of supply was shut off to both parties, for they blockaded each other. The British fleet closed up the German ports, while the German cruisers in the Pacific took up a position off the coast of Chile in order to intercept the ships carrying nitrates to England and France. The Panama Canal, designed to afford relief in such an emergency, caved in most inopportunely. The British sent a fleet to the Pacific to clear the nitrate route, but it was outranged and defeated on November 1st, 1914. Then a stronger British fleet was sent out and smashed the Germans off the Falkland Islands on December 8. But for 7 weeks the nitrate route had been closed, while the chemical reactions on the Marne and Yser were decomposing nitrogen compounds at an unheard of rate. England was now free to get nitrates for her munition factories, but Germany was still bottled up. She had stored up Chilean nitrates in anticipation of the war, and as soon as it was seen to be coming, she bought all she could get in Europe. But this supply was altogether inadequate, and the war would have come to an end in the first winter if German chemists had not provided for such a contingency in advance by working out methods of getting nitrogen from the air. Long ago it was said that the British ruled the sea and the French the land, so that left nothing to the German but the air. The Germans seem to have taken this jibe seriously and to have set themselves to make the most of the aerial realm in order to challenge the British and French in the fields they had appropriated. They had succeeded so far that the Kaiser when he declared war might well have considered himself the prince of the power of the air. He had a fleet of Zeppelins and he had means for the fixation of nitrogen such as no other nation possessed. The Zeppelins burst like windbags, but the nitrogen plants worked and made Germany independent of Chile not only during the war but in the time of peace. Germany during the war used 200,000 tons of nitric acid a year in explosives, yet her supply of nitrogen is exhaustless. Nitrogen is free as air. That is the trouble. It is too free. It is fixed nitrogen that we want and that we are willing to pay for. Nitrogen in combination with some other elements in the form of food or fertilizer so we can make use of it as we set it free. Fixed nitrogen in its cheapest form, Chile saltpeter, rose to $250 during the war. Free nitrogen costs nothing and is good for nothing. If a landowner has a right to an expanding pyramid of air above him to the limits of the atmosphere, as I believe the courts have decided in the eavesdropping cases, then for every square foot of his ground he owns as much nitrogen as he could buy for $2,500. The air is 4/5 free nitrogen, and if we could absorb it in our own lungs as we do the oxygen of the other fifth, a few minutes breathing would give us a full meal. But we let this free nitrogen all out again through our noses, and then go and pay 35 cents a pound for steak or 60 cents a dozen for eggs in order to get enough combined nitrogen to live on. Though man is immersed in an ocean of nitrogen, yet he cannot make use of it. He is like Coleridge's Ancient Mariner, with water, water everywhere, but not any drop to drink. Nitrogen is, as Hood said not so truly about gold, hard to get and hard to hold. The bacteria that form the nodules on the roots of peas and beans have the power that man has not of utilizing free nitrogen. Instead of this quiet, inconspicuous process, man has to call upon the lightning when he wants to fix nitrogen. The air contains the oxygen and nitrogen which it is desired to combine to form nitrates, but the atoms are paired, like to like. Passing an electric spark through the air breaks up some of these pairs, and in the confusion of the shock the lonely atoms seize on their nearest neighbor and so may get partners of the other sort. I have seen this same thing happen in a square dance where somebody made a blunder. It is easy to understand the reaction if we represent the atoms of oxygen and nitrogen by the initials of their names in this fashion. NN, nitrogen, plus OO, oxygen, goes to NO plus NO, nitric oxide. The arrow represents Jove's thunderbolt, a stroke of artificial lightning. We see on the left the molecules of oxygen and nitrogen before taking the electric treatment as separate elemental pairs, and then to the right of the arrow we find them as compound molecules of nitric oxide. This takes up another atom of oxygen from the air and becomes NOO, or using a subscript figure to indicate the number of atoms and so avoid repeating the letter, NO2, which is the familiar nitro group of nitric acid, HO, NO2, and of its salts, the nitrates, and of its organic compounds, the high explosives. The NO2 is a brown and evil-smelling gas which when dissolved in water (HOH) and further oxidized is completely converted into nitric acid. The apparatus which effects this transformation is essentially a gigantic arc light in a chimney through which a current of hot air is blown. The more thoroughly the air comes under the action of the electric arc, the more molecules of nitrogen and oxygen will be broken up and rearranged, but on the other hand, if the mixture of gases remains in the path of the discharge, the NO molecules are also broken up and go back into their original form of NN and OO. So the object is to spread out the electric arc as widely as possible and then run the air through it rapidly. In the Schönherr process, the electric arc is a spiral flame 23 feet long through which the air streams with a vortex motion. In the WWII furnace there is a series of semicircular arcs spread out by the repellent force of a powerful electric magnet in a flaming disc 7 feet in diameter with a temperature of 6300 degrees Fahrenheit. In the Pauling furnace the electrodes between which the current strikes are two cast iron tubes curving upward and outward like the horns of a Texas steer and cooled by streams of water passing through them. These electric furnaces produce 2 or 3 ounces of nitric acid for each kilowatt hour of current consumed. Whether they can compete with the natural nitrates and the products of other processes depends upon how cheaply they can get their electricity. Before the war, there were several large installations in Norway and elsewhere where abundant water power was available, and now the Norwegians are using 500,000 horsepower continuously in the fixation of nitrogen, and the rest of the world as much again. The Germans had invested largely in these foreign oxidation plants, but shortly before the war they had sold out and turned their attention to other processes not requiring so much electrical energy, for their country is poorly provided with water power. The Haber process that they made most of is based upon as simple a reaction as that we have been considering, for it consists in uniting two elemental gases to make a compound, but the elements in this case are not nitrogen and oxygen, but nitrogen and hydrogen. This gives ammonia instead of nitric acid, but ammonia is useful for its own purposes, and it can be converted into nitric acid if this is desired. The reaction is NN nitrogen plus 3HH hydrogen goes to 2 of NHHH. The animals go in 2 by 2, but they come out 4 by 4. 4 molecules of the mixed elements are turned into 2 molecules, and so the gas shrinks to half its volume. At the same time it acquires an odor, familiar to us when we are curing a cold, that neither of the original gases had. The agent that effects the transformation in this case is not the electric spark, for this would tend to work the reaction backwards, but uranium, a rare metal, which has the peculiar property of helping along a reaction while seeming to take no part in it. Such a substance is called a catalyst. The action of a catalyst is rather mysterious, and whenever we have a mystery we need an analogy. We may, then, compare the catalyst to what is known as a good mixer in society. You know the sort of man I mean. He may not be brilliant or especially talkative, but somehow there is always something doing at a picnic or house party when he is along. The tactful hostess, the salon leader, is a social catalyst. The trouble with catalysts, either human or metallic, is that they are rare and that sometimes they get sulky and won't work if the ingredients they are supposed to mix are unsuitable. But the uranium, osmium, platinum, or whatever metal is used as a catalyzing agent is expensive, and although it is not used up, it is easily poisoned, as the chemists say, by impurities in the gases. The nitrogen and the hydrogen for the Haber process must then be prepared and purified before trying to combine them into ammonia. The nitrogen is obtained by liquefying air by cold and pressure and then boiling off the nitrogen at 194 degrees centigrade. The oxygen left is useful for other purposes. The hydrogen needed is extracted by a similar process of fractional distillation from water gas, the blue flame burning gas used for heating. Then the nitrogen and hydrogen, mixed in the proportion of 1 to 3, as shown in the reaction given above, are compressed to 200 atmospheres, heated to 1300 degrees Fahrenheit, and passed over the finely divided uranium. The stream of gas that comes out contains about 4% of ammonia, which is condensed to a liquid by cooling, and the uncombined hydrogen and nitrogen passed again through the apparatus. The ammonia can be employed in refrigeration and other ways, but if it is desired to get the nitrogen into the form of nitric acid, it has to be oxidized by the so-called Ostwald process. This is the reaction NH3 ammonia plus 4O oxygen goes to HNO3 nitric acid plus H2O water. The catalyst used to effect this combination is the metal platinum in the form of fine wire gauze, since the action takes place only on the surface. The ammonia gas is mixed with air which supplies the oxygen, and the heated mixture runs through the platinum gauze at the rate of several yards a second. Although the gases come in contact with the platinum only a 500th part of a second, yet 85% is converted into nitric acid. The Haber process for the making of ammonia by direct synthesis from its constituent elements and the supplemental Ostwald process for the conversion of the ammonia into nitric acid were the salvation of Germany. As soon as the Germans saw that their dash toward Paris had been stopped at the Marne, they knew that they were in for a long war, and at once made plans for a supply of fixed nitrogen. The chief German dye factories, the Badische Anilin and Soda Fabrik, promptly put $100 million into enlarging its plant and raised its production of ammonium sulfate from 30,000 to 300,000 tons. One German electrical firm with aid from the city of Berlin contracted to provide 66 million pounds of fixed nitrogen a year at a cost of 3 cents a pound for the next 25 years. The 750,000 tons of Chilean nitrate imported annually by Germany contained about 116,000 tons of the essential element in nitrogen. The 14 large plants erected during the war can fix in the form of nitrates 500,000 tons of nitrogen a year, which is more than twice the amount needed for internal consumption. So Germany is now not only independent of the outside world, but will have a surplus of nitrogen products which could be sold even in America at about half of what the farmer has been paying for South American saltpeter. Besides the Haber or direct process, there are other methods of making ammonia which are, at least outside of Germany, of more importance. Most prominent of these is the cyanamide process. This requires electrical power since it starts with a product of the electrical furnace, calcium carbide, familiar to us all as a source of acetylene gas. If a stream of nitrogen is passed over hot calcium carbide, it is taken up by the carbide according to the following equation: CaC2 calcium carbide plus N2 nitrogen goes to CaCN2 calcium cyanamide plus C carbon. Calcium cyanamide was discovered in 1895 by Caro and Frank when they were trying to work out a new process for making cyanide to use in extracting gold. It looks like stone and, under the name of lime nitrogen or Kalkstickstoff or nitrolim, is sold as a fertilizer. If it is desired to get ammonia, it is treated with superheated steam. The reaction produces heat and pressure, so it is necessary to carry it on in stout autoclaves or enclosed kettles. The cyanamide is completely and quickly converted into pure ammonia and calcium carbonate, which is the same as the limestone from which carbide was made. The reaction is CaCN2 calcium cyanamide plus 3H2O water goes to CaCO3 calcium carbonate plus 2NH3 ammonia. Another electrical furnace method, the Serpek process, uses aluminum instead of calcium for the fixation of nitrogen. Bauxite or impure aluminum oxide, the ordinary mineral used in the manufacture of metallic aluminum, is mixed with coal and heated in a revolving electrical furnace through which nitrogen is passing. The equation is Al2O3 aluminum oxide plus 3C carbon plus 2N2 nitrogen goes to 2AlN aluminum nitride plus 3CO carbon monoxide. Then the aluminum nitride is treated with steam under pressure, which produces ammonia and gives back the original aluminum oxide, but in a purer form than the mineral from which was made. 2AlN aluminum nitride plus 3H2O water goes to 2NH3 ammonia plus 2Al2O3 aluminum oxide. The Serpek process is employed to some extent in France in connection with the aluminum industry. These are the principal processes for the fixation of nitrogen now in use, but they by no means exhaust the possibilities. For instance, Professor John C. Bucher of Brown University created a sensation in 1917 by announcing a new process which he had worked out with admirable completeness and which has some very attractive features. It needs no electric power or high pressure retorts or liquid air apparatus. He simply fills a 20-foot tube with briquettes made out of soda ash, iron, and coke and passes a producer gas through the heated tube. Producer gas contains nitrogen since it is made by passing air over hot coal. The reaction is 2Na2CO3 sodium carbonate plus 4C carbon plus N2 nitrogen goes to 2NaCN sodium cyanide plus 3CO carbon monoxide. The iron here acts as the catalyst and converts two harmless substances, sodium carbonate, which is common washing soda, and carbon, into two of the most deadly compounds known to man, cyanide and carbon monoxide, which is what kills you when you blow out the gas. Sodium cyanide is a salt of hydrocyanic acid, which for some curious reason is called prussic acid. It is so violent a poison that, as the freshman said in a chemistry recitation, a single drop of it placed on the tongue of a dog will kill a man. But sodium cyanide is not only useful in itself for the extraction of gold and cleaning of silver, but can be converted into ammonia and a variety of other compounds such as urea and oxamide, which are good fertilizers, sodium ferrocyanide that makes Prussian blue, and oxalic acid used in dyeing. Professor Bucher claimed that his furnace could be set up in a day at a cost of less than $100 and could turn out 150 pounds of sodium cyanide in 24 hours. This process was placed freely at the disposal of the United States government for the war, and a 10-ton plant was built at Saltville, Virginia, by the Ordnance Department. But the armistice put a stop to its operations and left the future of the process undetermined. We might have expected that the fixation of nitrogen by passing an electrical spark through hot air would have been an American invention, since it was Franklin who snatched the lightning from the heavens as well as the scepter from the tyrant, and since our output of hot air is unequaled by any other nation. But little attention was paid to the nitrogen problem until 1916, when it became evident that we should soon be drawn into a war with a first-class power. On June 3, 1916, Congress placed $20 million at the disposal of the President for investigation of the best, cheapest, and most available means for the production of nitrate and other products for munitions of war and useful in the manufacture of fertilizers and other useful products by water power or any other power. But by the time war was declared on April 6, 1917, no definite program had been approved, and by the time the armistice was signed on November 11, 1918, no plants were in active operation. But 5 plants had been started and 2 of them were nearly ready to begin work when they were closed by the ending of the war. United States Nitrate Plant No. 1 was located at Sheffield, Alabama, and was designated for the production of ammonia by direct action from nitrogen and hydrogen according to the plans of the American Chemical Company. Its capacity was calculated at 60,000 pounds of anhydrous ammonia a day, half of which was to be oxidized to nitric acid. Plant No. 2 was erected at Muscle Shoals, Alabama, to use the process of American Cyanamid Company. This was contracted to produce 110 tons of ammonium nitrate a year, and later 2 other cyanamid plants of half that capacity were started at Toledo and Anchor, Ohio. At Muscle Shoals, a mushroom city of 20,000 sprung up on an Alabama cotton field in 6 months. The raw material, air, was as abundant there as anywhere, and the power, water, could be obtained from the government hydroelectric plant on the Tennessee River, but this was not available during the war, so steam was employed instead. The heat of the coal was used to cool the air down to the liquefying point. The principle of this process is simple. Everybody knows that heat expands and cold contracts, but not everybody has realized the converse of this rule, that expansion cools and compression heats. If air is forced into smaller space, as in a tire pump, it heats up, and if allowed to expand to ordinary pressure, it cools off again. But if the air, while compressed, is cooled and then allowed to expand, it must get still colder, and the process can go on till it becomes cold enough to congeal. That is, by expanding a great deal of air, a little of it can be reduced to the liquefying point. At Muscle Shoals, the plant for liquefying air, in order to get the nitrogen out of it, consisted of 24 towers, each capable of producing 1,765 cubic feet of pure nitrogen per hour. The air was drawn in through two pipes a yard across and passed through scrubbing towers to remove impurities. The air was then compressed to 600 pounds per square inch. 9/10 of the air was permitted to expand to 50 pounds and this expansion cooled down the other tenth, still under high pressure, to the liquefying point. Rectifying towers 24 feet high were stacked with trays of liquid air from which the nitrogen was continually bubbling off since its boiling point is 12 degrees centigrade lower than that of oxygen. Pure nitrogen gas collected at the top of the tower and the residual liquid air, now about half oxygen, was allowed to escape at the bottom. The nitrogen was then run through pipes into the lime nitrogen ovens. There were 1,536 of these, about 4 feet square, and each holding 1,600 pounds of pulverized calcium carbide. This is at first heated by an electrical current to start the reaction, which afterwards produces enough heat to keep it going. As the stream of nitrogen gas passes over the finely divided carbide, it is absorbed to form calcium cyanamide as described on a previous page. This product is cooled, powdered, and wet to destroy any quicklime or carbide left unchanged. Then it is charged into autoclaves and steam at high pressure, and pressure is admitted. The steam acting on the cyanamide sets free ammonia gas, which is carried to towers down which cold water is sprayed, giving the ammonia water, familiar to the kitchen and the bathroom. But since nitric acid rather than ammonia was needed for munitions, the oxygen of the air had to be called into play. This process, as already explained, is carried on by aid of a catalyzer, in this case platinum wire. At Muscle Shoals there were 696 of these catalyzer boxes. The ammonia gas, mixed with air to provide the necessary oxygen, was admitted at the top and passed down through a sheet of platinum gauze of 80 mesh to the inch, heated to incandescence by electricity. In contact with this, the ammonia is converted into gaseous oxides of nitrogen, the familiar red fumes of the laboratory, which, carried off in pipes, cooled and dissolved in water, form nitric acid. But since none of the national plants could be got into action during the war, the United States was compelled to draw upon South America for its supply. The imports of Chilean saltpeter rose from 500,000 tons in 1914 to 1.5 million in 1917. After peace was made, the Department of War turned over to the Department of Agriculture its surplus of saltpeter, 150,000 tons, and it was sold to American farmers at cost, $81 a ton. For nitrogen plays a double role in human economy. It appears like Brahma in two aspects, Vishnu the preserver and Shiva the destroyer. Here I have been considering nitrogen in its maleficent aspect, its use in war. We now turn to its beneficent aspect, its use in peace. End of chapter 2. End of section 2. Section 3. Chapter 3. Of Creative Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Adam Marsatich, Alexandria, Virginia, 2010. Creative Chemistry by Edwin E. Slosson. Chapter 3. Feeding the Soil. The Great War not only starved people, it starved the land. Enough nitrogen was thrown away in some indecisive battle on the Aisne to save India from a famine. The population of Europe as a whole has not been lessened by the war, but the soil has been robbed of its power to support the population. A plant requires certain chemical elements for its growth, and all of these must be within the reach of its rootlets, for it will accept no substitutes. A wheat stalk in France, before the war, had placed at its feet nitrates from Chile, phosphates from Florida, and potash from Germany. All these were shut off by the firing line and the shortage of shipping. Out of the 80 elements only 13 are necessary for crops. 4 of these are gases: hydrogen, oxygen, nitrogen, and chlorine. 5 are metals: potassium, magnesium, calcium, iron, and sodium. 4 are nonmetallic solids: carbon, sulfur, phosphorus, and silicon. 3 of these, hydrogen, oxygen, and carbon, making up the bulk of the plant, are obtainable ad libitum from the air and water. The other 10 in the form of salts are dissolved in the water that is sucked up from the soil. The quantity needed by the plant is so small and the quantity contained in the soil is so great that ordinarily we need not bother about the supply except in case of 3 of them. They are nitrogen, potassium, and phosphorus. These would be useless or fatal to plant life in the elemental form, but fixed in neutral salt they are essential plant foods. A ton of wheat takes away from the soil about 47 pounds of nitrogen, 18 pounds of phosphoric acid, and 12 pounds of potash. If, then, the farmer does not restore this much to his field every year, he is drawing upon his capital, and this must lead to bankruptcy in the long run. So much is easy to see, but actually the question is extremely complicated. When the German chemist, Justus von Liebig, pointed out in 1840 the possibility of maintaining soil fertility by the application of chemicals, it seemed at first as though the question were practically solved. Chemists assumed that all they had to do was to analyze the soil and analyze the crop, and from this figure out, as easily as balancing a bank book, just how much of each ingredient would have to be restored to the soil every year. But somehow it did not work out that way, and the practical agriculturist, finding that the formulas did not fit his farm, sneered at the professors, and whenever they cited Liebig to him, he irreverently transposed the syllables of the name. The chemist, when he went deeper into the subject, saw that he had to deal with the colloids, damp, unpleasant, gummy bodies that he had hitherto fought shy of because they would not crystallize or filter. So the chemist called to his aid the physicist on the one hand and the biologist on the other, and then they both had their hands full. The physicist found that he had to deal with a polyvariant system of solids, liquids, and gases, mutually miscible in phases too numerous to be handled by Gibbs' rule. the biologist found that he had to deal with the invisible flora and fauna of a new world. Plants obey the injunction of Tennyson, and rise on the stepping stones of their dead selves to higher things. Each successive generation lives on what is left of the last in the soil plus what it adds from the air and sunshine. As soon as a leaf or tree trunk falls to the ground, it is taken in charge by a wrecking crew composed of a myriad of microscopic organisms who proceed to break it up into its component parts so these can be used for building a new edifice. The process is called rotting, and the product, the black, gummy stuff of a fertile soil, is called humus. The plants, that is, the higher plants, are not able to live on their own proteids as the animals are. But there are lower plants, certain kinds of bacteria, that can break up the big complicated proteid molecules into their component parts and reduce the nitrogen in them to ammonia or ammonia-like compounds. Having done this, they stop and turn over the job to another set of bacteria to be carried through the next step. For you must know that soil society is as complex and specialized as that above ground, and the tiniest bacterium would die rather than violate the union rules. The second set of bacteria change the ammonia over to nitrates, and then a third set, the amalgamated union of nitrate workers, steps in and completes the process of oxidation with an efficiency that Ostwald must envy, for 96% of the ammonia of the soil is converted into nitrates. But if the conditions are not just right, if the food is insufficient or unwholesome, or if the air that circulates through the soil is contaminated with poison gases, the bacteria go on a strike. The farmer, not seeing the thing from the standpoint of the bacteria, says the soil is sick, and he proceeds to doctor it according to his own notion of what ails it. First perhaps he tries running in strike breakers. He goes to one of the firms that makes a business of supplying nitrogen-fixing bacteria from the scabs or nodules of the clover roots, and scatters these colonies over the field. But if the living conditions remain bad, the newcomers will soon quit work too, and the farmer loses his money. If he is wise, then, he will remedy the conditions, putting a better ventilation system in his soil, perhaps, or neutralizing the sourness by means of lime, or killing off the amoeboid banditti that prey upon the peaceful bacteria engaged in the nitrogen industry. It is not an easy job that the farmer has in keeping billions of subterranean servants contented and working together, but if he does not succeed at this, he wastes his seed and labor. The layman regards the soil as a platform or anchoring place on which to set plants. He measures its value by its superficial area without considering its contents, which is as absurd as to estimate a man's wealth by the size of his safe. The difference in point of view is well illustrated by the old story of the city chap who was showing his farmer uncle the sights of New York. When he took him to Central Park, he tried to astonish him by saying, "This land is worth $500,000 an acre." The old farmer dug his toe into the ground, kicked out a clod, broke it open, looked at it, spit on it, and squeezed it in his hand, and then said, "Don't you believe it, 'tain't worth $10 an acre. Mighty poor soil, I call it." Both were right. The modern agriculturist realizes that the soil is a laboratory for the production of plant food, and he ordinarily takes more pains to provide a balanced ration for it than he does for his family. Of course, the necessity of feeding the soil has been known ever since man began to settle down, and the ancient methods of maintaining its fertility, though discovered accidentally and followed blindly, were sound and efficacious. Virgil, who like Liberty Hyde Bailey was fond of publishing agricultural bulletins in poetry, wrote 2000 years ago, "But sweet vicissitudes of rest and soil make easy labor and renew the soil. Yet sprinkle sordid ashes all around, and load with fattening dung thy fallow soil." The ashes supplied the potash and the dung the nitrate and phosphate. Long before the discovery of the nitrogen-fixing bacteria, the custom prevailed of sowing pea-like plants every third year and then plowing them under to enrich the soil. But such local supplies were always inadequate, and as soon as deposits of fertilizers were discovered anywhere in the world, they were drawn upon. The richest of those was the Chincha Islands off the coast of Peru, where millions of penguins and pelicans had lived in a most untidy manner for untold centuries. The guano composed of the excrement of the birds, mixed with the remains of dead birds and the fishes they fed upon, was piled up to a depth of 120 feet. From this Isle of Penguins, which is not that described by Anatole France, $1 billion worth of guano was taken and the deposit was soon exhausted. Then the attention of the world was directed to the mainland of Peru and Chile, where similar guano deposits had been accumulated and, not being washed away on account of the lack of rain, had been deposited as sodium nitrate, or saltpeter. These beds were discovered by a German, Tadeo Heinke, in 1809, but it was not until the last quarter of the century that the nitrates came into common use as a fertilizer. Since then, more than 53 million tons have been taken out of these beds, and the exportation has risen to a rate of 2.5 million to 3 million tons a year. How much longer they will last is a matter of opinion, and opinion is largely influenced by whether you have your money invested in Chilean nitrate stock or in one of the new synthetic processes for making nitrates. The United States Department of Agriculture says the nitrate beds will be exhausted in a few years. On the other hand, the Chilean Inspector General of Nitrate Deposits, in his latest official report, says that they will last for 200 years at the present rate and that then there are incalculable areas of low-grade deposits containing less than 11% to be drawn upon. Anyhow, the South American beds cannot long supply the world's needs of nitrates, and we shall sometime be starving unless creative chemistry comes to the rescue. In 1898, Sir William Crookes, the discoverer of the Crookes tubes, the radiometer, and radiant matter, startled the British Association for the Advancement of Science by declaring that the world was nearing the limit of wheat production, and that by 1931 the bread eaters, the Caucasians, would have to turn to other grains or restrict their population while the rice and millet eaters of Asia would continue to increase. Sir William was laughed at then as a sensationalist. He was, but his sensations were apt to prove true, and it is already evident that he was too near right for comfort. Before we were halfway to the date he set, we had 2 wheatless days a week, though that was because we persisted in shooting nitrates into the air. The area producing wheat was by decades: the wheat fields of the world, 1881 to 90, 192 million acres; 1890 to 1900, 211 million; 1900 to 10, 242 million. Probable limit, 300 million. If 300 million acres can be brought under cultivation for wheat and the average yield raised to 20 bushels to the acre, that will give enough to feed a billion people if they eat 6 bushels a year, as do the English. Whether this maximum is correct or not, there is evidently some limit to the area which has suitable soil and climate for growing wheat. So we are ultimately thrown back upon Crookes' solution of the problem. That is, we must increase the yield per acre, and this can only be done by the use of fertilizers and especially by the fixation of atmospheric nitrogen. Crookes estimated the average yield of wheat at 12.7 bushels to the acre, which is more than it is in the new lands of the United States, Australia, and Russia, but less than in Europe, where the soil is well fed. What can be done to increase the yield may be seen from these figures. Gain in the yield of wheat in bushels per acre. Germany, from 1989 to 90, 19 bushels per acre. 1918, 35 bushels per acre. Belgium, from 1889 to 90, 30 bushels per acre. 1913, 35 bushels per acre. France, from 1889 to 90, 17 bushels per acre. 1913, 20 bushels per acre. United Kingdom, from 1889 to 90, 28 bushels per acre. 1913, 32 bushels per acre. United States, from 1889 to 90, 12 bushels per acre. 1913, 15 bushels per acre. The greatest gain was made in Germany, and we see a reason for it in the fact that the German importation of Chilean saltpeter was 55,000 tons in 1880 and 747,000 tons in 1913. In potatoes, too, Germany gets twice as big a crop from the same ground as we do, 223 bushels per acre instead of our 113 bushels. But the United States uses on the average only 28 pounds of fertilizer per acre, while Europe uses 200. It is clear that we cannot rely upon Chile, but make nitrates for ourselves as Germany had to in wartime. In the first chapter we considered the new methods of fixing the free nitrogen from the air, but the fixation of nitrogen is a new business in this country, and our chief reliance so far has been the coke ovens. When coal is heated in retorts or ovens for making coke or gas, a lot of ammonia comes off with the other products of decomposition and is caught in the sulfuric acid used to wash the gas as ammonium sulfate. Our American coke makers have been in the habit of letting this escape into the air, and consequently we have been losing some 700,000 tons of ammonium salts every year, enough to keep our land rich and give us all the explosives we should need. But now they are reforming and putting in ovens that save the byproducts such as ammonia and coal tar, so in 1916 we got from this source 325,000 tons a year. Germany had a natural monopoly of potash as Chile had a natural monopoly of nitrates. The agriculture of Europe and America has been virtually dependent upon these two sources of plant foods. Now, when the world was cleft in twain by the shock of August 1914, the Allied powers had the nitrates and the Central powers had the potash. If Germany had not had up her sleeve a new process for making nitrates, she could not long have carried on a war and doubtless would not have ventured upon it. But the outside world had no such substitute for the German potash salts and has not yet discovered one. Consequently, the price of potash in the United States jumped from $40 to $400, and the cost of food went up with it. Even after the stimulus of prices 10 times the normal and with chemists searching furnace crannies and badlands, the United States was able to scrape up less than 10,000 tons of potash in 1916, and this was barely enough to satisfy our needs for 2 weeks. Yet potash compounds are as cheap as dirt. Pick up a handful of gravel and you will be able to find much of it feldspar or other mineral containing some 10% of potash. Unfortunately, it is in combination with silica, which is harder to break up than a trust. But constant washing wears away stones, and the potash that the metallurgist finds too hard to extract in his hottest furnace is washed out in the course of time through the dropping of the gentle rain from heaven. All rivers run to the sea, and so the sea gets salt, all sorts of salts, principally sodium chloride, our table salt, and next magnesium, calcium, and potassium chlorides or sulfates in this order of abundance. But if we evaporate seawater down to dryness, all these are left in a mix together, and it is hard to sort them out. Only patient nature has time for it, and she only did on a large scale in one place, that is at Stassfurt, Germany. It seems that in the days when northwestern Prussia was undetermined whether it should be sea or land, it was flooded annually by sea water. As this slowly evaporated, the dissolved salts crystallized out at the critical points, leaving beds of various combinations. Each year there would be deposited 3 to 5 inches of salts within a thin layer of calcium sulfate or gypsum on top. Counting these annual layers, like the rings on a stump, we find that the Stassfurt beds were 10,000 years in the making. They were first worked for their salt, common salt, alone, but in 1837 the Prussian government began prospecting for new and deeper deposits and found, not the clean rock salt that they wanted, but bittern, largely magnesium sulfate or Epsom salt, which is not at all nice for table use. This stuff was first thrown away until it was realized that it was much more valuable for the potash it contains than was the rock salt they were after. Then the Germans began to purify the Stassfurt salts and market them throughout the world. They contain from 15 to 25% of magnesium chloride mixed with magnesium chloride in carnallite, with magnesium sulfate in kainite, and sodium chloride in sylvinite. More than 30,000 miners and workmen are employed in the Stassfurt works. There are some 70 distinct establishments engaged in the business, but they are in combination. In fact, they are compelled to be, for the German government is as anxious to promote trusts as the American government is to prevent them. Once the Stassfurt firms had a falling out and began a cutthroat competition, but the German government objects to its people cutting each other's throats. American dealers were getting unheard of bargains when the German government stepped in and compelled the competing corporations to recombine under threat of putting on an export duty that would eat up their profits. The advantages of such business cooperation are especially shown in opening up a new market for an unknown product, as in the case of the introduction of the Stassfurt salts into American agriculture. The farmer in any country is apt to be set in his ways, and when it comes to inducing him to spend his hard-earned money for chemicals that he never heard of and could not produce, he, quite rightly, has to be shown. Well, he was shown. It was, if I remember right, early in the 90s that the German Kali Syndicat began operations in America and the United States government became its chief advertising agent. In every state there was an agricultural experiment station, and these were provided liberally with illustrated literature on Stassfurt salts, with colored wall charts and sets of samples, and free sacks of salts for field experiments. The station men, finding that they could rely upon the scientific accuracy of the information supplied by Kali and that the experiments worked out well, became enthusiastic advocates of potash fertilizers. The station bulletins, which Uncle Sam was kind enough to carry free to all the farmers of the state, sometimes were worded so like the Kali Company advertising that the company might have raised a complaint of plagiarizing, but they never did. The Chilean nitrates, which are under British control, were later introduced by similar methods through the agency of the state agricultural experiment stations. As a result of all this missionary work, which cost the Kali Company $50,000 a year, the attention of a large proportion of American farmers was turned toward intensive farming, and they began to realize the necessity of feeding the soil that was feeding them. They grew dependent upon these two foreign and widely separated sources of supply. In the year before the war, the United States imported 1,000,000 tons of Stassfurt salts, for which the farmers paid more than $20 million. Then a declaration of American independence, the German embargo of 1915, cut us off from Stassfurt, and for 5 years we had to rely upon our own reserves. We have seen how Germany, shut off from Chile, solved the nitrogen problem for her fields and munition plants. It was not so easy for us, shut off from Germany, to solve the potash problem. There is no more lack of potash in the rocks than there is of nitrogen in the air, but the nitrogen is free and has only to be caught and combined, while the potash is shut up in a granite prison from which it is hard to get it free. It is not the percentage in the soil, but the percentage in the soil water that counts. A farmer with his potash locked up in silicates is like the merchant who has left the key of his safe at home in his other trousers. He may be solvent, but he cannot meet a sight draft. It is only solvent potash that passes current. In the days of our grandfathers we had not only national independence but household independence. Every homestead had its own potash plant and soap factory. The frugal housewife dumped the maple wood ashes of the fireplace into a hollow log set up on end in the backyard. Water poured over the ashes, leached out the lye, which drained into a bucket beneath. This gave her a solution of pearl ash or potassium carbonate whose concentration she tested with an egg as a hydrometer. In the meantime she had been saving up all the waste grease from the frying pan and pork rinds from the plate, and by trying out these she got her soap fat. Then on a day set apart for this disagreeable process in chemical technology she boiled the fat and the lye together and got soft soap, or as the chemist would call it, potassium stearate. If she wanted hard soap, she salted it out with brine. The sodium stearate, being less soluble, was precipitated to the top and cooled into a solid cake that could be cut into bars by pack thread. But the frugal housewife threw away in the waste water what we now consider the most valuable ingredients, the potash and the glycerin. But the old lye leach is only to be found in ruins on an abandoned farm, and we no longer burn wood at the rate of a log a night. In 1916, even under the stimulus of tenfold prices, the amount of potash produced as pearl ash was only 412 tons, and we need 300,000 tons in some form. It would, of course, be very desirable as a conservation measure if all the sawdust and waste wood were utilized by charring it in retorts. The gas makes a handy fuel. The tar washed from the gas contains a lot of valuable products, and potash can be leached out of the charcoal or from its ashes whenever it is burned. But this at best would not go far toward solving the problem of our national supply. There are other potash-bearing wastes that might be utilized. The cement mills which use feldspar in combination with limestone give off a potash dust, very much to the annoyance of their neighbors. This can be collected by running the furnace clouds into large settling chambers or long flutes, where the dust may be caught in bags or washed out by water sprays or thrown down by electricity. The blast furnaces for iron also throw off potash-bearing fumes. Our 6,000,000 ton crop of sugar beets contains some 12,000 tons of nitrogen, 4,000 tons of phosphoric acid, and 18,000 tons of potash, all of which is lost, except where the waste liquors from the sugar factory are used in irrigating the beet land. The beet molasses, after extracting all the sugar possible by means of lime, leaves a waste liquor from which the potash can be recovered by evaporation and charring and leaching the residue. The Germans get 5,000 tons of potassium cyanide and as much ammonium sulfate annually from the waste liquor of their beet sugar factories, and if it pays them to save this, it ought to pay us where potash is dearer. Various other industries can put in a bit when Uncle Sam passes around the contribution basket marked "Potash for the Poor." Wool wastes and fish refuse make valuable fertilizers, although they will not go far toward solving the problem. If we saved all our potash byproducts, they would not supply more than 15% of our needs. Though no potash beds comparable to those of Stassfurt have yet been discovered in the United States, yet in Nebraska, Utah, California, and other western states there are a number of alkali lakes, wet or dry, containing a considerable amount of potash mixed with soda salts. Of these deposits the largest is Searles Lake, California. Here there are some 12 square miles of salt crust some 70 feet deep, and the brine as pumped out contains about 4% of potassium chloride. The quantity is sufficient to supply the country for over 20 years, but it is not an easy or cheap job to separate the potassium from the sodium salts, which are 5 times more abundant. These being less soluble than the potassium salts, crystallize out first when the brine is evaporated. The final crystallization is done in vacuum pans, as in getting sugar from the cane juice. In this way the American Trona Corporation is producing some 4,500 tons of potash salts a month besides 1,000 tons of borax. The borax, which is contained in the brine to the extent of 1.5%, is removed from the fertilizer for a double reason. It is saleable by itself and it is detrimental to plant life. Another mineral source of potash is alunite, which is a sort of natural alum or double sulfate of potassium and aluminum with about 10% of potash. It contains a lot of extra alumina, but after roasting in a kiln, the potassium sulfate can be leached out. The alunite beds near Marysville, Utah, were worked for all they were worth during the war, but the process does not give potash cheap enough for our needs in ordinary times. The tourist going through Wyoming on the Union Pacific will have to the north of him what is marked on the map as the Leucite Hills. If he looks up the word in the unabridged that he carries in his satchel, he will find that leucite is a kind of lava and that it contains potash. But he will also observe that the potash is combined with alumina and silica, which are hard to get out and useless when you get them out. One of the lavas of the Leucite Hills, that named from its native state, Wyomingite, gives 57% of its potash in a soluble form on roasting with alunite, but this costs too much. The same may be said of all the potash feldspars and mica. They are abundant enough, but until we find a way of utilizing the byproducts, say the silica in cement and the aluminum as a metal, they cannot solve our problem. Since it is so hard to get potash from the land, it has been suggested that we harvest the sea. The experts of the United States Department of Agriculture have placed high hopes in the kelp or giant seaweed which floats in great masses in the Pacific Ocean, not far off from the California coast. This is harvested with ocean reapers run by gasoline engines and brought in barges to the shore where it may be dried and used locally as a fertilizer, or burned and the potassium chloride leached out of the charcoal ashes. But it is hard to handle the bulky, slimy seaweed cheaply enough to get out of it the small amount of potash it contains. So efforts are now being made to get more out of the kelp than the potash. Instead of burning the seaweed, it is fermented in vats, producing acetic acid vinegar. From the resulting liquid can be obtained lime acetate, potassium chloride, potassium iodide, acetone, ethyl acetate, used as a solvent for guncotton, and algin, a gelatin-like gum. This completes our survey of the visible sources of potash in America. This table shows how inadequate was the reaction of the United States to the war demand for potassium salts. The minimum yearly requirements of the United States are estimated to be 250,000 tons of potash. This completes our survey of the visible sources of potash in America. In 1917, under the pressure of the embargo and unprecedented prices, the output of potash, K2O, in various forms was raised to 32,573 tons, but this is only about a tenth as much as we needed. In 1918, potash production was further raised to 52,135 tons, chiefly through the increase of the output from natural brines to 39,255 tons, nearly twice what it was the year before. The rust in cotton and the resulting decrease in yield during the war are laid to lack of potash. Truck crops grown in soils deficient in potash do not stand transportation well. The Bureau of Animal Industry has shown in experiments in Aroostook County, Maine, that the addition of moderate amounts of potash doubled the yield of potatoes. Professor Ostwald, the great Leipzig chemist, boasted in the war, America went into the war like a man with a rope round his neck which is in his enemy's hands and is pretty tightly drawn. With its tremendous deposits, Germany has a world monopoly in potash, a point of immense value which cannot be reckoned too highly when once this war is going to be settled. It is in Germany's power to dictate which of the nations shall have plenty of food and which shall starve. If, indeed, some mineralogist or metallurgist will cut that rope by showing us a supply of cheap potash, we will erect him a monument as big as Washington's. But Ostwald is wrong in supposing that America is as dependent as Germany upon potash. The bulk of our food crops are at present raised without the use of any fertilizers whatever. As the cessation of Lorraine in 1871 gave Germany the phosphates she needed for fertilizers, so the retrocession of Alsace in 1919 gives France the potash she needed for fertilizers. 10 years before the war, a bed of potash was discovered in the forest of Monnebruck near Hartmannsweilerkopf, the peak for which French and Germans contested so fiercely and so long. The layer of potassium salts is 16½ feet thick and the total deposit is estimated to be 275 million tons of potash. At any rate, it is a formidable rival of Stassfurt and its acquisition by France breaks the German monopoly. When we turn to the consideration of the third plant food, we feel better. While the United States has no such monopoly of phosphates as Germany had of potash and Chile had of nitrates, we have an abundance and to spare. Whereas we formerly imported about $17 million worth of potash from Germany and $20 million worth of nitrates from Chile a year, we exported $7 million worth of phosphates. Whoever it was who first noticed that the grass grew thicker around a buried bone, he lived so long ago that we cannot do honor to his powers of observation. But ever since then, whenever it was, old bones have been used as a fertilizer. But we long ago used up all the buffalo bones we could find on the prairies, and our packing houses could not give us enough bone meal to go around. So we have had to draw upon the old boneyards of prehistoric animals. Deposits of lime phosphate of such origin were found in South Carolina in 1870 and in Florida in 1888. Since then, the industry has developed with amazing rapidity until in 1913 the United States produced over 3 million tons of phosphates, nearly half of which was sent abroad. The chief source at present is the Florida pebbles, which are dredged up from the bottoms of lakes and rivers or washed out from the banks of streams by a hydraulic jet. The gravel is washed free from the sand and clay, screened and dried, and then is ready for shipment. The rock deposits of Florida and South Carolina are more limited than the pebble beds and may be exhausted in 25 or 30 years. But Tennessee and Kentucky have a lot in reserve, and behind them are Idaho, Wyoming, and other western states with millions of acres of phosphate land. So in this respect we are independent. But even here the war hit us hard, for the calcium phosphate as it comes from the ground is not altogether available because it is not very soluble and the plants can only use what they can get in the water that they suck up from the soil. But if the phosphate is treated with sulfuric acid, it becomes more soluble, and this product is sold as superphosphate. The sulfuric acid is made mostly from iron pyrite, and this we have been content to import, over 800,000 tons of it a year, largely from Spain, although we have an abundance at home. Since the shortage of shipping shut off the foreign supply, we are using more of our own pyrite and also our deposits of native sulfur along the Gulf Coast. But as a consequence of this, sulfuric acid during the war went up from $5 to $25 a ton, and acidulated phosphates rose correspondingly. Germany is short on natural phosphates as she is long on natural potash, but she has made up for it by utilizing a byproduct of her steelworks. When phosphorus occurs in iron ore, even in minute amounts, it makes the steel brittle. Much of the iron ores of Alsace-Lorraine were formerly considered unworkable because of this impurity, but shortly after Germany took these provinces from France in 1871, a method was discovered by two British metallurgists, Thomas and Gilchrist, by which the phosphorus is removed from the iron in the process of converting it into steel. This consists in lining the crucible or converter with lime and magnesia, which takes up the phosphorus from the melted iron. This slag lining, now rich in phosphates, can be taken out and ground up for fertilizer. So the phosphorus which used to be a detriment is now an additional source of profit, and this British invention has enabled Germany to make use of the territory she stole from France to outstrip England in the steel business. In 1910, Germany produced 2,000,000 tons of Thomas slag, while only 160,000 tons were produced in the United Kingdom. The open hearth process, now chiefly used in the United States, gives an acid instead of a basic phosphate slag, not suitable as a fertilizer. The iron ore of America, with the exception of some of the southern ores, carries so small a percentage of phosphorus as to make a basic process inadvisable. Recently, the Germans have been experimenting with a combined fertilizer, Schroeder's potassium phosphate, which is said to be as good as Thomas slag for phosphates and as good as Stassfurt salts for potash. The American Cyanamid Company is just putting out a similar product, Ammo-Phos, in which the ammonia can be varied from 13 to 20% and the phosphoric acid from 20 to 47%, so as to give the proportions desired for any crop. We have then the possibility of getting the three essential plant foods all together in one compound with the elimination of most of the extraneous elements such as lime and magnesia, chlorides and sulfates. For the last 300 years, the American people have been living on the unearned increment of the unoccupied land. But now that all our land has been staked out in homesteads, and we cannot turn to new soil when we have used up the old, we must learn, as the older races have learned, how to keep up the supply of plant food. Only in this way can our population increase and prosper. As we have seen, the phosphate question need not bother us, and we can see our way clear toward solving the nitrate question. We gave the government $20 million to experiment on the production of nitrates from the air, and the results will serve for fields as well as firearms. But the question of an independent of cheap potash is still unresolved. End of chapter 3. Section 4, Chapter 4, Part 1 of Creative Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adam Marsatich, Alexandria, Virginia, 2010. Creative Chemistry by Edwin E. Slosson. Chapter 4. Coal Tar Colors. If you put a bit of soft coal into a test tube, or if you haven't a test tube, into a clay tobacco pipe and lute it over with clay and heat it, you will find a gas coming out of the end of the tube that will burn with a yellow smoky flame. After all the gas comes off, you will find in the bottom of the test tube a chunk of dry, porous coke. These, then, are the two main products of the destructive distillation of coal. But if you are an unusually observant person, that is, if you are a born chemist with an eye to byproducts, you will notice along in the middle of the tube, where it is neither too hot nor too cold, some dirty drops of water and some black sticky stuff. If you are just an ordinary person, you won't pay any attention to this, because there is only a little of it and because what you are after is the coke and gas. You regard the nasty, smelly mess that comes in between as merely a nuisance because it clogs up and spoils your nice clean tube. Now that is the way the gas makers and coke makers, being for the most part ordinary persons and not born chemists, used to regard the water and tar that got into their pipes. They washed it out so as to have the gas clean and then ran it into the creek. But the neighbors, especially those who fished in the stream below the gas works, made a fuss about spoiling the water, so the gas men gave away the tar to the boys for use in celebrating the 4th of July and election night, or sold it for roofing. But this same tar, which for 100 years was thrown away, and nearly half of which is thrown away yet in the United States, turns out to be one of the most useful things in the world. It is one of the strategic points in war and commerce. It wounds and heals. It supplies munitions and medicines. It is like the magic purse of Fortunatus, from which anything wished for could be drawn. The chemist puts his hand into the black mass and draws out all the colors of the rainbow. The evil-smelling substance beats the rose in the production of perfume and surpasses the honeycomb in sweetness. Bishop Berkeley, after having proved that all matter was in your mind, wrote a book to prove that wood tar would cure all diseases. Nobody reads it now. The name is enough to frighten them off. Cyrus, a chain of philosophical reflections and inquiries concerning the virtues of tar water. He had a sort of mystical idea that tar contained the quintessence of the forest, the purified spirit of the trees, which could somehow revive the spirit of man. People said he was crazy on the subject, and doubtless he was, but the interesting thing about it is that not even his active and ingenious imagination could begin to suggest all of the strange things that can be got out of tar, whether wood or coal. The reason why tar supplies all sorts of useful material is because it is indeed the quintessence of the forests of untold millenniums if it is coal tar. If you are acquainted with a village tinker, one of those all-round mechanics who still survive in this age of specialization and can mend anything from a baby carriage to an automobile, you will know that he has on the floor of his back shop a heap of broken machinery from which he can get almost anything he wants: a copper wire, a zinc plate, a brass screw, or a steel rod. Now coal tar is the scrap heap of the vegetable kingdom. It contains a little of almost everything that makes up trees. But you must not imagine that all that comes out of coal tar is contained in it. There are only about a dozen primary products extracted from coal tar, but from these the chemist is able to build up hundreds of thousands of new substances. This is true creative chemistry, for most of these compounds are not to be found in plants and never existed before they were made in the laboratory. It used to be thought that organic compounds, the products of vegetable and animal life, could only be produced by organized beings, that they were created out of inorganic matter by the magic touch of some vital principle. But since the chemist has learned how, he finds it easier to make organic than inorganic substances, and he is confident that he can reproduce any compound that he can analyze. He can not only imitate the manufacturing processes of the plants and animals, but he can often beat them at their own game. When coal is heated in the open air, it is burned up, and nothing but the ashes is left. But heat the coal in an enclosed vessel, say a big fireclay retort, and it cannot burn up because the oxygen of the air cannot get to it. So it breaks up. All parts of it that can be volatilized at a high heat pass off through the outlet pipe and nothing is left in the retort but coke, that is, carbon with the ash it contains. When the escaping vapors reach a cool part of the outlet pipe, the oily and tarry matter condenses out. Then the gas is passed up through a tower down which water spray is falling and thus is washed free from ammonia and everything else that is soluble in water. The process is called destructive distillation. What products come off depends not only upon the composition of the particular variety of coal used, but upon the heat, pressure, and rapidity of distillation. The way you run it depends upon what you are most anxious to have. If you want illuminating gas, you will leave it in the benzene. If you are after the greatest yield of tar products, you impoverish the gas by taking out the benzene and get a blue instead of a bright yellow flame. If all you are after is cheap coke, you do not bother about the byproducts, but let them escape and burn as they please. The tourist passing across the coal region at night could see through his car window the flames of hundreds of old-fashioned beehive coke ovens, and if he were of economical mind he might reflect that this display of fireworks was costing the country $75 million a year besides consuming the irreplaceable fuel supply of the future. But since the gas was not needed outside of the cities, and since the coal tar, if it could be sold at all, brought only a cent or two a gallon, how could the coke makers be expected to throw out their old beehive ovens and put in the expensive retorts and towers necessary to the recovery of the byproducts? But within the last 10 years the byproduct ovens have come into use and now nearly half our coke is made in them. Although the products of destructive distillation vary within wide limits, yet the following table may serve to give an idea of what may be got from a ton of soft coal. 1 ton of coal may give gas 12,000 cubic feet, liquor, washings, ammonium sulfate 7 to 25 pounds, tar 120 pounds, benzene 10 to 20 pounds, toluene 3 pounds, xylene 1½ pounds, phenol 1/2 pound, naphthalene 3/8 pound, anthracene 1/4 pound, pitch 80 pounds, coke 1,200 to 1,500 pounds. When the tar is redistilled we get, among other things, the 10 crudes which are fundamental material for making dyes. Their names are benzene, toluene, xylene, phenol, cresol, naphthalene, anthracene, methyl anthracene, phenanthracene and carbazole. There, I had to introduce you to the whole receiving line, but now that the ceremony is over we are at liberty to do as we do at a reception, meet our old friends, get acquainted with one or two more, and turn our backs on the rest. Two of them, I am sure, you've met before, phenol, which is common carbolic acid, and naphthalene, which we use for mothballs. But notice one thing in passing, that not one of them is a dye. They are all colorless liquids or white solids. Also, they have an indescribable odor. All odors that you don't know are indescribable, which gives them and their progeny, even when odorless, the name of aromatic compounds. The most important of the 10, because he is the father of the family, is benzene, otherwise called benzol, but must not be confused with benzine, spelled with an I, which we use to burn and clean our clothes with. Benzine is a kind of gasoline, but benzene, alias benzol, has quite another constitution, although it looks and burns the same. Now, the search for the constitution of benzene is one of the most exciting chapters in chemistry, also one of the most intricate chapters, but, in spite of that, I believe I can make the main point of it clear even to those who have never studied chemistry, provided they retain their childish liking for puzzles. It is really much like putting together the old 6-block Chinese puzzle. The chemist can work better if he has a picture of what he is working with. Now his unit is the molecule, which is too small even to analyze with the microscope, no matter how high powered. So he makes up a sort of diagram of the molecule, and since he knows the number of atoms, and that they are somehow attached to one another, he represents each atom by the first letter of its name, and the points of attachment or bonds by straight lines connecting the atoms of the different elements. Now it is one of the rules of the game that all the bonds must be connected or hooked up with atoms at both ends, that there shall be no free hands reaching out into empty space. Carbon, for instance, has 4 bonds and hydrogen only 1. They unite, therefore, in the proportion of 1 atom of carbon to 4 of hydrogen, or CH4, which is methane or marsh gas, and obviously the simplest of the hydrocarbons. But we have more complex hydrocarbons such as C6H14, known as hexane. Now if you try to draw the diagrams or structural formulas of these two compounds, you will easily get methane and hexane. Each carbon atom, you see, has its 4 hands outstretched and duly grasped by one-handed hydrogen atoms or by neighboring carbon atoms in the chain. We can have such chains as long as you please, 30 or more in a chain. They are all contained in kerosene and paraffin. So far, the chemist found it easiest to construct diagrams that would satisfy his sense of the fitness of things. But when he found that benzene had the composition C6H6, he was puzzled. If you try to draw the picture of C6H6, you will get something like this: a carbon chain with 8 empty bonds, which is an absurdity because more than half of the carbon hands are waving wildly around, asking to be held by something. Benzene, C6H6, evidently is like hexane, C6H14, in having a chain of 6 carbon atoms, but it has dropped its H's like an Englishman. 8 of the H's are missing. Now one of the men who was worried over this benzene puzzle was the German chemist, Kekulé. One evening after working over the problem all day, he was sitting by the fire trying to rest, but he could not throw it off his mind. The carbon and the hydrogen atoms danced like imps on the carpet, and as he watched them through his half-closed eyes he suddenly saw that the chain of 6 carbon atoms had joined at the ends and formed a ring, while the 6 hydrogen atoms were holding on to the outside hands in this fashion: 6 carbons linked in a circle with hydrogens around, double bonds between 3 of the carbons. Professor Kekulé saw at once that the demons of his subconscious self had furnished him with a clue to the labyrinth, and so it proved. We need not suppose that the benzene molecule, if we could see it, would look anything like this diagram of it, but the theory works, and that is all the scientist asks of any theory. By its use thousands of new compounds have been constructed which have proved of inestimable value to man. The modern chemist is not a discoverer, he is an inventor. He sits down at his desk and draws a Kekulé ring, or rather hexagon. Then he rubs out an H and hooks a nitro group, NO2, onto the carbon in place of it. Next he rubs out the O2 of the nitro group and puts in H2. Then he hitches on such other elements or carbon chains and rings as he likes. He works like an architect designing a house, and when he gets a picture of the proposed compounds to suit him, he goes into the laboratory to make it. First he takes down the bottle of benzene and boils up some of this with nitric acid and sulfuric acid. This he puts into the nitro group and makes nitrobenzene, C6H5NO2. He treats this with hydrogen, which displaces the oxygen and gives C6H5NH2, or aniline, which is the basis of so many of these compounds that they are all commonly called the aniline dyes. But aniline itself is not a dye. It is a colorless or brownish oil. It is not necessary to follow our chemist any farther now that we have seen how he works, but before we pass on we will just look at one of his products, not one of the most complicated, but still complicated enough. The name of this is sodium ditollyl disazo beta-naphthylamine 6-sulfonic beta-naphthylamine 3,6-disulfonate. These chemical names of organic compounds are discouraging to the beginner and amusing to the layman, but that is because neither of them realizes that they are not really words but formulas. They are hyphenated because they come from Germany. The name given above is no more of a mouthful than A square plus 2AB plus B square, or Third Assistant Secretary of War to the President of the United States of America. The trade name of this dye is Brilliant Congo, but while that is handier to say, it does not mean anything. Nobody but an expert in dyes would know what it was, while from the formula name any chemist familiar with such compounds could draw its picture, tell how it would behave, and what it was made from, or even make it. The old alchemist was a secretive and pretentious person, and used to invent queer names for the purpose of mystifying and awing the ignorant, but the chemist in dropping the "al" has dropped the idea of secrecy, and his names, though equally appalling to the layman, are designed to reveal and not to conceal. From this brief explanation the reader who has not studied chemistry will, I think, be able to get some idea of how these very intricate compounds are built up step by step. A completed house is hard to understand, but when we see the mason laying one brick on top of another, it does not seem so difficult, although if we tried to do it we should not find it so easy as we think. Anyhow, let me give you a hint. If you want to make a good impression on a chemist, don't tell him that he seems to you a sort of magician, master of a black art, and all that nonsense. The chemist has been trying for 300 years to live down the reputation of being inspired of the devil, and it makes him mad to have his past thrown up at him in this fashion. If his tactless admirers would stop saying, "It is all a mystery and a miracle to me, and I cannot understand it," and pay attention to what he is telling them, they would understand it and would find that it is no more of a mystery or a miracle than anything else. You can make an electrician mad in the same way by interrupting his explanation of a dynamo by asking, "But you cannot tell me what electricity really is." The electrician does not care a rap what electricity really is, if there really is any meaning to that phrase. All he wants to know is what he can do with it. The tar obtained from the gas plant or the coke plant has now to be redistilled, giving off the 10 "crudes" already mentioned and leaving in the still 65% of pitch, which may be used for roofing, paving and the like. The 10 primary products or crudes are then converted into secondary products or intermediates by processes like that for the conversion of benzene into aniline. There are some 300 of these intermediates in use, and from them are built up more than 3 times as many dyes. The year before the war, the American Custom House listed 5,674 distinct brands of synthetic dyes imported, chiefly from Germany, but some of these were trade names for the same product made by different firms, or represented by different degrees of purity or form of preparation. Although the number of possible products is unlimited and over 5,000 dyes are known, yet only about 900 are in use. We can summarize the situation so: coal tar goes to 10 crudes, goes to 300 intermediates, goes to 900 dyes, goes to 5,000 brands. Or, to borrow the neat simile used by Dr. Bernard C. Hesse, it is like cloth making, where 10 fibers make 300 yarns, which are woven into 900 patterns. The advantage of the artificial dyestuffs over those found in nature lies in their variety and adaptability. Practically any desired tint or shade can be made for any particular fabric. If my lady wants a new kind of green for her stockings or her hair, she can have it. Candies and jellies and drinks can be made more attractive and therefore more appetizing by varied colors. Easter eggs and Easter bonnets take on new and brighter hues. More and more the chemist is becoming the architect of his own fortunes. He does not make discoveries by picking up a beaker and pouring into it a little from each bottle on the shelf to see what happens. He generally knows what he is after, and he generally gets it, although he is still often baffled and occasionally happens on something quite unexpected and perhaps more valuable than what he was looking for. Columbus was looking for India when he ran into an obstacle that proved to be America. William Henry Perkin was looking for quinine when he blundered into that rich and undiscovered country, the aniline dyes. William Henry was a queer boy. He had rather listen to a chemistry lecture than eat. When he was attending the City of London School at the age of 13, there was an extra course of lectures on chemistry given at the noon recess, so he skipped his lunch to take them in. Hearing that a German chemist named Hofmann had opened a laboratory in the Royal College of London, he headed for that. Hofmann obviously had no fear of forcing the young intellect prematurely. He perhaps had never heard that the tender petals of the adolescent mind must be allowed to open slowly. He admitted young Perkin at the age of 15 and started him on research at the end of his second year. An American student nowadays thinks he is lucky if he gets started on his research 5 years older than Perkin. Now, if Hofmann had studied pedagogical psychology, he would have been informed that nothing chills the ardor of the adolescent mind like being set at tasks too great for its powers. If he had heard this and believed it, he would not have allowed Perkin to spend 2 years in fruitless endeavors to isolate phenanthrene from coal tar and to prepare artificial quinine, and in that case Perkin would never have discovered the aniline dyes. But Perkin, so far from being discouraged, set up a private laboratory so he could work overtime. While working here during the Easter vacation of 1856, the date is as well worth remembering as 1066, he was oxidizing some aniline oil when he got what chemists most detest, a black tarry mass, instead of nice clean crystals. When he went to wash this out with alcohol, he was surprised to find that it gave a beautiful purple solution. This was mauve, the first of the aniline dyes. The funny thing about it was that when Perkin tried to repeat the experiment with purer aniline, he could not get his color. It was because he was working with impure colors, with aniline containing a little toluidine, that he discovered mauve. It was, as I said, a lucky accident, but it was not accidental that the accident happened to the young fellow who spent his noonings and vacations at the study of chemistry. A man may not find what he is looking for, but he never finds anything unless he is looking for something. Mauve was a product of creative chemistry, for it was a substance that had never existed before. Perkin's next great triumph, 10 years later, was in rivaling nature in the manufacture of one of her own choice products. This is alizarin, the coloring matter contained in the madder root. It was an ancient and oriental dyestuff known as Turkey red, or by its Arabic name of alizari. When madder was introduced into France, it became a profitable crop, and at one time 500,000 tons a year were raised. A couple of French chemists, Robiquet and Collin, extracted from madder its active principle, alizarin, in 1828, but it was not until 40 years later that it was discovered that alizarin had for its base one of the coal tar products, anthracene. Then came a neck-and-neck race between Perkin and his German rivals to see which could discover a cheap process for making alizarin from anthracene. The German chemists beat him to the patent office by 1 day. Graebe and Liebermann filed their application for a patent on the sulfuric acid process as number 1936 on June 25, 1869. Perkin filed his for the same process as number 1948 on June 26. It had required 20 years to determine the constitution of alizarin, but within 6 months from its first synthesis, the commercial process was developed, and within a few years the sale of artificial alizarin reached $8 million annually. The madder fields of France were put to other uses, and even the French soldiers became dependent on made-in-Germany dyes for their red trousers. The British soldiers were placed in a similar situation as regards their red coats when after 1878 the Azo Scarlets put the cochineal bug out of business. End of chapter 4, part 1. Section 5, Chapter 4, Part 2 of 2, of Creative Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Adam Marsatich, Alexandria, Virginia, 2010. Creative Chemistry by Edwin E. Slosson. Section 5. Chapter 4, Part 2 of 2. The modern chemist has robbed royalty of its most distinctive insignia, Tyrian purple. In ancient times to be porphyrogene, that is, born to the purple, was like admission to the Almanach de Gotha at the present time. For only princes or their wealthy rivals could afford to pay $600 a pound for crimsoned linen. The precious dye is secreted by a snail-like shellfish off the eastern coast of the Mediterranean. From a tiny sac behind the head, a drop of thick whitish liquid, smelling like garlic, can be extracted. If this is spread upon a cloth of any kind and exposed to air and sunlight, it turns first green, next blue, and then purple. Section 4, Chapter 4, Part 1, of Creative Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Adam Marsatich, Alexandria, Virginia, 2012. Creative Chemistry by Edwin E. Slosson. If the cloth is washed with soap, that is, set by alkali, it becomes a fast crimson, such as Catholic cardinals still wear as princes of the church. The Phoenician merchants made fortunes out of their monopoly, but after the fall of Tyre it became one of the lost arts, and accordingly considered by those whose faces are set toward the past as much more wonderful than any of the new arts. But in 1909 Friedlander put an end to the superstition by analyzing Tyrian purple and finding that it was already known. It was the same as a dye that had been prepared 5 years before by Sachs, but had not come into commercial use because of its inferiority to others in the market. It required 12,000 of the mollusks to supply the little material needed for analysis. But once the chemist had identified it, he did not need to bother the Murex further, for he could make it by the ton if he wanted to. The coloring principle turned out to be a dibrom indigo, that is, the same as the substance extracted from the Indian plant, but with the addition of 2 atoms of bromine. Why a particular kind of a shellfish should have got the habit of extracting this rare element from seawater and stowing it away in this peculiar form is one of those things no fellow can find out. But according to the chemist, the Murex mollusk made a mistake in hitching the bromine to the wrong carbon atoms. He finds, as he would word it, that the 6,6-dibrom indigo secreted by the shellfish is not so good as the 5,5-dibrom indigo now manufactured at a cheap rate and in unlimited quantity. But we must not expect too much of a mollusk's mind. In their cheapness lies the offense of the aniline dyes in the minds of some people. Our modern aristocrats would delight to be entitled porphyrogeniti and to wear exclusive gowns of purple and scarlet from the Isles of Elisha, as was done in Ezekiel's time. But when any shop girl or sailor can wear the royal color, it spoils its beauty in their eyes. Applied science accomplishes a real democracy such as legislation has ever failed to establish. Any kind of dye found in nature can be made in the laboratory whenever its composition is understood, and usually it can be made cheaper and purer than it can be extracted from the plant. But to work out a profitable process for making it synthetically is sometimes a task requiring high skill, persistent labor, and heavy expenditure. One of the latest and most striking of these achievements of synthetic chemistry is the manufacture of indigo. Indigo is one of the oldest and fastest of the dyestuffs. To see that it is both ancient and lasting, look at the unfaded blue cloths that enwrap an Egyptian mummy. When Caesar conquered our British ancestors, he found them tattooed with woad, the native indigo. But the chief source of indigo was, as the name implies, India. In 1897, nearly 1,000,000 acres in India were growing the indigo plant, and the annual value of the crop was $20 million. Then the fall began, and by 1914 India was producing only $300,000 worth. What had happened to destroy this profitable industry? Some blight or insect? No, it was simply that Badische Anilin und Soda Fabrik had worked out a special process for making artificial indigo. That indigo, on breaking up, gave off aniline was discovered as early as 1840. In fact, that was how aniline got its name, for when Fritsch distilled indigo with caustic soda, he called the colorless distillate aniline, from the Arabic name for indigo, anil or al-nil, that is, the blue stuff. But how to reverse the process and get indigo from aniline puzzled chemists for more than 40 years, until finally it was solved by Adolf von Baeyer of Munich, who died in 1917 at the age of 84. He worked on the problem of the constitution of indigo for 15 years and discovered several ways of making it. It is possible to start from benzene, toluene, or naphthalene. The first process was the easiest, but if you will refer to the products of the distillation of tar, you will find that the amount of toluene produced is less than the naphthalene, which is hard to dispose of. That is, if a dye factory had worked out a process for making indigo from toluene, it would not be practicable because there was not enough toluene produced to supply the demand for indigo. So the more complicated naphthalene process was chosen in preference to the others in order to utilize this byproduct. The Badische Anilin und Soda Fabrik spent $5 million and 17 years in chemical research before they could make indigo, but they gained a monopoly, or to be exact, 96% of the world's production. 100 years ago, indigo cost as much as $4 a pound. In 1914, we were paying 15 cents a pound for it. Even the pauper labor of India could not compete with the German chemists at that price. At the beginning of the present century, Germany was paying more than $3 million a year for indigo. 14 years later, Germany was selling indigo to the amount of $12.6 million. Besides its cheapness, artificial indigo is preferable because it is of uniform quality and greater purity. Vegetable indigo contains from 40 to 80% of impurities, among them various other tinctorial substances. Artificial indigo is made pure and of any desired strength, so the dyers can depend on it. The value of the aniline colors lies in their infinite variety. Some are fast, some will fade, some will stand wear and weather as long as the fabric, some will wash out on the spot. Dyes can be made that will attach themselves to wool, silk, or to cotton and give it any shade of any color. The period of discovery by accident has long gone by. The chemist nowadays decides first just what kind of a dye he wants and then goes to work systematically to make it. He begins by drawing a diagram of the molecule, double linking nitrogen or carbon and oxygen atoms to give the required intensity, putting in acid or basic radicals to fasten it to the fiber, shifting the color back and forth along the spectrum at will by introducing methyl groups until he gets it just to his liking. Art can go ahead of nature in the dyestuff business. Before man found that he could make all the dyes he wanted from the tar he had been burning up at home, he searched the wide world over to find colors by which he could make himself, or his wife, garments as beautiful as those that arrayed the flower, the bird, and the butterfly. He sent divers down into the Mediterranean to rob the murex of his purple. He sent ships to the New World to get Brazil wood and to the Oldest World for indigo. He robbed the lady cochineal of her scarlet coat. Why these peculiar substances were formed only by these particular plants, mussels, and insects it is hard to understand. I don't know that Mrs. Cacti Coccus derived any benefit from her scarlet uniform when khaki would be safer, and I can't imagine that to a shellfish it was of advantage to turn red as it rots, or to an indigo plant that its leaves in decomposing should turn blue. But anyhow, it was man that took advantage of them until he learned how to make his own dyestuffs. Our independent ancestors got along so far as possible with what grew in the neighborhood. Sweet apple bark gave a fine saffron yellow. Ribbons were given the hue of the rose by pokeberry juice. The Confederates in their butternut-colored uniform were almost as invisible as if in khaki or feldgrau. Madder was cultivated in the kitchen garden. Only logwood from Jamaica and indigo from India had to be imported. That we are not so independent today is our own fault, for we waste enough coal tar to supply ourselves and the other countries with all the new dyes needed. It is essentially a question of economy and organization. We have forgotten how to economize, but we have learned how to organize. The British government gave the discoverer of mauve a title, but it did not give him any support in his endeavors to develop the industry, although England led the world in textiles and needed more dyes than any other country. So in 1874 Sir William Perkin relinquished the attempt to manufacture the dyes he had discovered because, as he said, Oxford and Cambridge refused to educate chemists or to carry on research. Their students, trained in the classics for the profession of being a gentleman, showed a decided repugnance to the laboratory on account of its bad smells. So when Hofmann went home, he virtually took the infant industry along with him to Germany, where PhDs were cheap and plentiful and not afraid of bad smells. There the business throve amazingly, and by 1914 the Germans were manufacturing more than 3/4 of all the coal tar products of the world and supplying material for most of the rest. The British cursed the universities for thus imperiling the nation through their narrowness and neglect. But this accusation, though natural, was not altogether fair, for at least half the blame should go to the British dyer, who did not care where his colors came from so long as they were cheap. When finally the universities did turn over a new leaf and began to educate chemists, the manufacturers would not employ them. Before the war, 6 English factories producing dyestuffs employed only 35 chemists altogether, while one German color works, the Hochster Farbwerk, employed 307 expert chemists and 74 technologists. This firm united with the 6 other leading dye companies of Germany on January 1, 1916, to form a trust to last for 50 years. During this time, they will maintain uniform prices and uniform wage scales and hours of labor, and exchange patents and secrets. They will divide the foreign business pro rata and share the profits. The German chemical works made big profits during the war, mostly from munitions and medicines, and will be, through this new combination, in a stronger position than ever to push the export trade. As a consequence of letting the dye business get away from her, England found herself in a fix when war broke out. She did not have dyes for her uniforms and flags, and she did not have drugs for her wounded. She could not take advantage of the blockade to capture the German trade in Asia and South America, because she could not color her textiles. A blue cotton dyestuff that sold before the war at 60 cents a pound brought $34 a pound. A bright pink rhodamine, formerly quoted at $1 a pound, jumped to $48. When one keg of dye ordinarily worth $15 was put up at a forced auction sale in 1915, it was knocked down at $1,500. The Highlanders could not get the colors for their kilts until some German dyes were smuggled into England. The textile industries of Great Britain, that brought in $1 billion a year and employed 1.5 million workers, were crippled for lack of dyes. The demand for high explosives from the front could not be met because these are largely coal tar products. Picric acid is both a dye and an explosive. It is made from carbolic acid, and the famous trinitrotoluene is made from toluene, both of which you will find in the list of the 10 fundamental crudes. Both Great Britain and the United States realized the danger of allowing Germany to recover her former monopoly, and both have shown a readiness to cast overboard their traditional policies to meet this emergency. The British government has discovered that a country without a tariff is a land without walls. The American government has discovered that an industry is not benefited by being cut up into small pieces. Both governments are now doing all they can to bring up big concerns and to provide them with protection. The British government assisted in the formation of a national company for the manufacture of synthetic dyes by taking 1/6 of the stock and providing $500,000 for a research laboratory. But this effort is now reported to be a great failure because the government put it in charge of the politicians instead of the chemists. The United States, like England, has become dependent upon Germany for its dyestuffs. We imported 9/10 of what we used, and most of those that were produced here were made from imported intermediates. When the war broke out, there were only 7 firms and 528 persons employed in the manufacture of dyes in the United States. One of these, the Scholl Cope Aniline and Chemical Works of Buffalo, deserves mention, for it had stuck it out ever since 1879. and in 1914 was making 106 dyes. In June 1917 this firm, with the encouragement of the Government Bureau of Foreign and Domestic Commerce, joined with some of the other American producers to form a trade combination, the National Aniline and Chemical Company. The DuPont Company also entered the field on an extensive scale, and soon there were 118 concerns engaged in it with great profit. During the war, $200 million was invested in the domestic dyestuff industry. To protect this industry, Congress put on a specific duty of 5 cents a pound and an ad valorem duty of 30% on imported dyestuffs. But if, after 5 years, American manufacturers are not producing 60% in value of the domestic consumption, the protection is to be removed. For some reason, not clearly understood and therefore hotly discussed, Congress at the last moment struck off the specific duty from two of the most important of the dyestuffs, indigo and alizarin, as well as from all medicinals and flavors. The manufacture of dyes is not a big business, but it is a strategic business. Heligoland is not a big island, but England would have been glad to buy it back during the war at a high price per square yard. American industries employing over 2 million men and women and producing over $3 billion worth of products a year are dependent upon dyes. Chief of these is of course textiles, using more than half the dyes. Next come leather, paper, paint, and ink. We have been importing more than $12 million worth of coal tar products a year, but the cottonseed oil we exported in 1912 would alone suffice to pay that bill twice over. But although the manufacture of dyes cannot be called a big business in comparison with some others, it is a paying business when well managed. The German concerns paid on average 22% dividends on their capital and sometimes as high as 50%. Most of the standard dyes have been so long in use that the patents are off and the processes are well enough known. We have the coal tar and we have the chemists, so there seems no good reason why we should not make our own dyes, at least enough of them so we will not be caught napping as we were in 1914. It was decidedly humiliating for our government to have to beg Germany to sell us enough colors to print our stamps and greenbacks and then have to beg Great Britain for permission to bring them over by Dutch ships. The raw material for the production of coal tar products we have in abundance if we will only take the trouble to save it. In 1914, the crude light oil collected from the coke ovens would have produced only about 4.5 million gallons of benzol and 1.5 million gallons of toluol, but in 1917 this output was raised to 40.2 million gallons of benzol and 10.2 million of toluol. The toluol was used mostly in the manufacture of trinitrotoluol for use in Europe. When the war broke out in 1914, it shut off our supply of phenol, carbolic acid, for which we were dependent upon foreign sources. This threatened not only to afflict us with headaches by depriving us of aspirin, but also remove the consolation of music, for phenol is used in making phonographic records. Mr. Edison, with his accustomed energy, put up a factory within a few weeks for the manufacture of synthetic phenol. When we entered the war, the need for phenol became yet more imperative, for it was needed to make picric acid for filling bombs. This demand was met, and in 1917 there were 15 new plants turning out 64,146,499 pounds of phenol valued at $23,719,805. Some of the coal products, as we see, serve many purposes. For instance, picric acid appears in 3 places in this book. It is a high explosive. It is a powerful and permanent yellow dye, as anyone who has touched it knows. Thirdly, it is used as an antiseptic to cover burned skin. Other coal dyes are used for the same purpose: malachite green, brilliant green, crystal violet, ethyl violet, and Victoria blue. So a patient in a military hospital is decorated like an Easter egg. During the last 5 years, surgeons have unfortunately had unprecedented opportunities for the study of wounds, and fortunately they have been unprecedentedly successful in finding improved methods of treating them. In former wars, a serious wound meant usually death or amputation. Now nearly 90% of the wounded are able to continue in the service. The reason for this improvement is that medicines are now being made to order instead of being gathered from China to Peru. The old herb doctor picked up any strange plant that he could find and tried it on any sick man that would let him. This empirical method, though hard on the patients, resulted in the course of 5,000 years in the discovery of a number of useful remedies. But the modern medicine man, when he knows the cause of the disease, is usually able to devise ways of counteracting it directly. For instance, he knows, thanks to Pasteur and Metchnikoff, that the cause of wound infection is the bacterial enemies of man, which swarm by the million into any breach in his protective armor, the skin. Now, when a breach is made in a line of entrenchments, the defenders rush troops to the threatened spot for 2 purposes: constructive and destructive, engineers and warriors, the former to build up the rampart with sandbags, the latter to kill the enemy. So when the human body is invaded, the blood brings to the breach 2 kinds of defenders. One is the cerium, which neutralizes the bacterial poison and by coagulating forms a new skin or scab over the exposed flesh. The other is the phagocytes or white corpuscles, the free lances of our corporeal militia, which attack and kill the invading bacteria. The aim of the physician is then to aid these defenders as much as possible without interfering with them. Therefore, the antiseptic he is seeking is one that will assist the serum in protecting and repairing the broken tissues and will kill the hostile bacteria without killing the friendly phagocytes. Carbolic acid, the most familiar of the coal tar antiseptics, will destroy the bacteria when it is diluted with 250 parts of water, but unfortunately it puts a stop to the fighting activities of the phagocytes when it is only half that strength, or 1 to 500, so it cannot destroy the infection without hindering the healing. In this search for substances that would attack a specific disease germ, one of the leading investigators was Professor Paul Ehrlich, a German physician of the Hebrew race. He found that aniline dyes were useful for staining slides under the microscope, for they would pick out particular cells and leave others uncolored, and from this starting point he worked out organic and metallic compounds which would destroy the bacteria and parasites that cause some of the most dreadful of diseases. A year after the war broke out, Professor Ehrlich died while working in his laboratory on how to heal with coal tar compounds the wounds inflicted by explosives from the same source. One of the most valuable of the aniline antiseptics employed by Ehrlich is flavine, or, if the reader prefers to call it by its full name, diaminomethyl acridinium chloride. Flavine, as its name implies, is a yellow dye and will kill the germs causing ordinary abscesses when in solution as dilute as 1 part of the dye to 200,000 parts of water. But it does not interfere with the bactericidal action of the white blood corpuscles unless the solution is 400 times as strong as this, that is 1 part in 500. Unlike carbolic acid and other antiseptics, it is said to stimulate the serum instead of impairing its activity. Another antiseptic of the coal tar family, which has recently been brought into use by Dr. Dakin of the Rockefeller Institute, is that called by European physicians chloramine T and by American physicians chlorazine and by chemists para-toluene sodium sulfochloramide. This may serve to illustrate how a chemist is able to make such remedies as the doctor needs, instead of depending upon the accidental byproducts of plants. On an earlier page I explained how, by starting with the simplest of ring compounds, the benzene of coal tar, we could get aniline. Suppose we go a step further and boil the aniline oil with acetic acid, which is the acid of vinegar minus its water. This easy process gives us acetanilide, which when introduced into the market some years ago under the name of antifebrin made a fortune for its makers. The making of medicines from coal tar began in 1874 when Colby made salicylic acid from carbolic acid. Salicylic acid is a rheumatism remedy and had previously been extracted from willow bark. If now we treat salicylic acid with concentrated acetic acid, we get aspirin. From aniline again are made phenacetin, antipyrin, and a lot of other drugs that have become altogether too popular as headache remedies, say rather headache relievers. Another class of synthetics equally useful and likewise abused are the soporifics, such as sulfonal, veronal, and medinol. When it is not desired to put the patient to sleep, but merely to render insensible a particular place, as when a tooth is to be pulled, cocaine may be used. This, like alcohol and morphine, has proved a curse as well as a blessing, and its sale has had to be restricted because of the many victims to the habit of using this drug. Cocaine is obtained from the leaves of the South American coca tree, but can be made artificially from coal tar products. The laboratory is superior to the forest because other forms of local anesthetics, such as eucaine and novocaine, can be made that are better than the natural alkaloid because more effective and less poisonous. I must not forget to mention another lot of coal tar derivatives in which some of my readers will take a personal interest. That is the photographic developers. I am old enough to remember when we used to develop our plates in ferrous sulfate solution, and you never saw nicer negatives than we got with it. But when pyrogallic acid came in, we switched over to that, even though it did stain our fingers and sometimes our plates. Later came a swarm of new organic reducing agents under various fancy names, such as metol, hydro, short for hydroquinone, and icongen, the image maker. Every fellow fixed up his own formula and called his fellow members of the Camera Club fools for not adopting it, though he secretly hoped they would not. Under the double stimulus of patriotism and high prices, the American drug and dyestuff industry developed rapidly. In 1917, about as many pounds of dyes were manufactured in America as were imported in 1913, and our exports of American-made dyes exceeded in value our imports before the war. In 1914, the output of American dyes was valued at $2.5 million. In 1917, it amounted to over $50 million. This does not mean that the problem was solved, for our home products were not equal in variety and sometimes not in quality to those made in Germany. Many valuable dyes were lacking and the cost was of course much higher. Whether the American industry can compete with the foreign in an open market and on equal terms is impossible to say, because such conditions did not prevail before the war and they are not going to prevail in the future. Formerly the large German cartels through their agents and branches in this country kept the business in their own hands, and now the American manufacturers are determined to maintain the independence they have acquired. They will not depend hereafter upon the tariff to cut off competition, but have adopted more effective measures. The 4,500 German chemical patents that had been seized by the alien property custodian were sold by him for $250,000 to the Chemical Foundation, an association of American manufacturers organized for the Americanization of such institutions as may be effected thereby, for the exclusion or elimination of alien interests hostile or detrimental to said industries, and for the advancement of chemical and allied science and industry in the United States. The foundation has a large fighting fund so that it may be able to commence immediately and prosecute with the utmost vigor infringement proceedings whenever the first German attempt shall hereafter be made to import into this country. So much mystery has been made of the achievements of German chemists, as though the Teutonic brain had a special lobe for that faculty, lacking in other craniums, that I want to quote what Dr. Hesse says about his first impressions of a German laboratory of industrial research. Directly after graduating from the University of Chicago in 1896, I entered the employ of the largest coal tar dye works in the world at its plant in Germany, and indeed in one of the research laboratories. This was my first trip outside the United States, and it was, of course, an event of the first magnitude for me to be in Europe, and, as a chemist, to be in Germany, in a German coal tar dye plant, and to cap it all, in its research laboratory, a real sanctum sanctorum for chemists. In a short time the daily routine wore the novelty off my experience, and I then settled down to calm analysis and dispassionate appraisal of my surroundings, and to compare what was actually before and around me with my expectations. I found that the general laboratory equipment was no better than what I had been accustomed to, that my colleagues had no better fundamental training than I had enjoyed, nor any better fact or manipulative equipment than I, that those in charge of the work had no better general intellectual equipment nor any more native ability than had my instructors. In short, there was nothing new about it all, nothing that we did not have back home, nothing, except the specific problems that were engaging their attention, and the special opportunities of attacking them. Those problems were of no higher order of complexity than those I had been accustomed to for years. In fact, most of them were not very complex from a purely intellectual viewpoint. There was nothing inherently uncanny, magical, or wizardly about their occupation whatever. It was nothing but plain hard work and keeping everlastingly at it. Now, what was the actual thing behind that chemical laboratory that we did not have at home? It was money, willing to back such activity, convinced that in the final outcome a profit would be made, money, willing to take university graduates expecting from them no special knowledge other than a good and thorough grounding in scientific research, and provide them with opportunity to become specialists suited to the factory's needs. It is evidently not impossible to make the United States self-sufficient in the matter of coal tar products. We've got the tar, we've got the men, we've got the money too. Whether such a policy would pay us in the long run, or whether it is necessary as a measure of military or commercial self-defense, is another question that cannot here be decided. But whatever share we may have in it, the coal tar industry has increased the economy of civilization and added to the wealth of the world by showing how a waste byproduct could be utilized for making new dyes and valuable medicines, a better use for tar than as fuel for political bonfires and as clothing for the nakedness of social outcasts. End of chapter 4, part 2 of 2. End of section 5. Section 6, Chapter 5 of Creative Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adam Marsatich, Alexandria, Virginia, 2010. Creative Chemistry by Edwin E. Slosson. Chapter 5. Synthetic Perfumes and Flavors. The primitive man got his living out of such wild plants and animals as he could find. Next he, or more likely his wife, began to cultivate the plants and tame the animals so as to ensure a constant supply. This was the first step toward civilization, for when men had to settle down in a community, civitas, they had to ameliorate their manners and make laws protecting land and property. In this settled and orderly life the plants and animals improved as well as man, and returned 100-fold for the pains that their master had taken in their training. But still man was dependent upon the chance bounties of nature. He could select, but he could not invent. He could cultivate, but he could not create. If he wanted sugar, he had to send to the West Indies. If he wanted spices, he had to send to the East Indies. If he wanted indigo, he had to send to India. If he wanted a febrifuge, he had to send to Peru. If he wanted a fertilizer, he had to send to Chile. If he wanted rubber, he had to send to the Congo. If he wanted rubies, he had to send to Mandalay. If he wanted otto of roses, he had to send to Turkey. Man was not yet master of his environment. This period of cultivation, the second stage of civilization, began before the dawn of history and lasted until recent times. We might almost say up to the 20th century, for it was not until the fundamental laws of heredity were discovered that man could originate new species of plants and animals according to a predetermined plan by combining such characteristics as he desired to perpetuate. and it was not until the fundamental laws of chemistry were discovered that man could originate new compounds more suitable to his purpose than any to be found in nature. Since the progress of mankind is continuous, it is impossible to draw a date line, unless a very jagged one, along the frontier of human culture, but it is evident that we are just entering upon the third era of evolution in which man will make what he needs instead of trying to find it somewhere. The new epoch has already dawned, yet already a man may stay at home in New York or London and make his own rubber and rubies, his own indigo and otto of roses. More than this, he can make gems and colors and perfumes that never existed since time began. The man of science has signed a declaration of independence of the lower world, and we are now in the midst of the revolution. Our eyes are dazzled by the dawn of the new era. We know what the hunter and the horticulturist have already done for man, but we cannot imagine what the chemist can do. If we look ahead through the eyes of one of the greatest French chemists, Berthelot, this is what we shall see. The problem of food is a chemical problem. Whenever energy can be obtained economically, we can begin to make all kinds of aliment. With carbon borrowed from carbonic acid, hydrogen taken from the water, and oxygen and nitrogen drawn from the air, the day will come when each person will carry for his nourishment his little nitrogenous tablet, his pat of fatty matter, his package of starch or sugar, his vial of aromatic spices, suited to his personal taste, all manufactured economically and in unlimited quantities, all independent of irregular seasons, drought and rain, of the heat that winters the plant, and of frost that blights the fruit, all free from pathogenic microbes, the origin of epidemics and the enemies of human life. On that day chemistry will have accomplished a worldwide revolution that cannot be estimated. There will no longer be hills covered with vineyards and fields filled with cattle. Man will gain in gentleness and morality because he will cease to live by the carnage and destruction of living creatures. The earth will be covered with grass, flowers and woods, and in it the human race will dwell in the abundance and joy of the legendary age of gold, provided that a spiritual chemistry has been discovered that changes the nature of man as profoundly as our chemistry transforms material nature. But this is looking so far into the future that we can trust no man's eyesight, not even Berthelot's. There is apparently no impossibility about the manufacture of synthetic food, but at present there is no apparent probability of it. There is no likelihood that the laboratory will ever rival the wheat field. The cornstalk will always be able to work cheaper than the chemist in the manufacture of starch. But in rarer and choicer products of nature, the chemist has proved his ability to compete and even to excel. What have been from the dawn of history to the rise of synthetic chemistry the most costly products of nature? What could tempt a merchant to brave the perils of a caravan journey over the deserts of Asia beset with Arab robbers? What induced the Portuguese and Spanish mariners to risk their frail barks on perilous waters of the Cape of Good Hope or the Horn? The chief prizes were perfumes, spices, drugs, and gems. And why were these rather than what now constitutes the bulk of oversea and overland commerce? Because they were precious, portable, and imperishable. If the merchant got back safe after a year or two with a little flask of otto of roses, a package of camphor, and a few pearls concealed in his garments, his fortune was made. If a single ship of the argosy sent out from Lisbon came back with a load of sandalwood, indigo, or nutmeg, it was regarded as a successful venture. You know from reading the Bible, or if not that, from your reading of Arabian Nights, that a few grains of frankincense, or a few drops of perfumed oil, were regarded as gifts worthy the acceptance of a king or a god. These products of the Orient were equally in demand by the toilet and the temple. The unctorium was an adjunct of the Roman bathroom. Kings had to be greased and fumigated before they were thought fit to sit upon a throne. There was a theory, not yet altogether extinct, that medicines brought from a distance were most efficacious, especially if, besides being expensive, they tasted bad, like myrrh, or smelled bad, like asafoetida. And if these failed to save the princely patient, he was embalmed in aromatics, or, as we now call them, antiseptics of the benzene series. Today, as always, men are willing to pay high for the titillation of the senses of smell and taste. The African savage will trade off an ivory tusk for a piece of soap reeking with synthetic musk. The clubman will pay $10 for a bottle of wine which consists mostly of water with about 10% of alcohol, worth a cent or two, but contains an unweighable amount of the bouquet that can only be produced on the sunny slopes of Champagne or in the valley of the Rhine. But very likely the reader is quite as extravagant, for one buys the natural violet perfumery, he is paying at the rate of more than $10,000 a pound for the odoriferous oil it contains. The rest is mere water and alcohol. But you would not want the pure undiluted oil if you could get it, for it is unendurable. A single whiff of it paralyzes your sense of smell for a time, just as a loud noise deafens you. Of the 5 senses, 3 are physical and 2 chemical. By touch, we discern pressures and surface textures. By hearing, we receive impressions of certain air waves, and by sight of certain ether waves. But smell and taste lead us to the heart of the molecule and enable us to tell how the atoms are put together. These twin senses stand like sentries at the portals of the body, where they closely scrutinize everything that enters. Sounds and sights may be disagreeable, but they are never fatal. A man can live in a boiler factory or in a cubist art gallery, but he cannot live in a room containing hydrogen sulfide, since it is more important to be warned of danger than guided to delights. Our senses are made more sensitive to pain than pleasure. We can detect by the smell 1/2,000,000th of a milligram of oil of roses or musk, but we can detect 1/2,000,000,000th of a milligram of mercaptan, which is the vilest smelling compound that man has so far invented. If you do not know how much a milligram is, consider a drop picked up by the point of a needle and imagine that divided into 2,000,000,000 parts. Also, try to estimate the weight of the odorous particles that guide a dog to the fox or warn a deer of the presence of man. The unaided nostril can rival the spectroscope in the detection and analysis of unweighable amounts of matter. What we call flavor or savor is a joint effect of taste and odor in which the latter predominates. There are only 4 tastes of importance: acid, alkaline, bitter, and sweet. The acid or sour taste is the perception of hydrogen atoms charged with positive electricity. The alkaline or soapy taste is the perception of hydroxyl radicals charged with negative electricity. the bitter and sweet tastes and all the odors dependent upon the chemical constitution of the compound, but the laws of the relation have not yet been worked out. Since these sense organs, the taste and smell buds, are sunk in the moist mucous membrane, they can only be touched by substances soluble in water, and to reach the sense of smell they must also be volatile so as to be diffused in the air inhaled by the nose. The taste of food is mostly due to the volatile odors of it that creep up the back stairs into the olfactory chamber. A chemist given an unknown substance would have to make an elementary analysis and some tedious tests to determine whether it contained methyl or ethyl groups, whether it was an aldehyde or an ester, whether the carbon atoms were singly or doubly linked, and whether it was an open chain or closed. But let him get a whiff of it, and he can give instantly a pretty shrewd guess as to these points. His nose knows. Although the chemist does not yet know enough to tell for certain from looking at the structural formula what sort of odor the compound would have, or whether it would have any, yet we can divide odoriferous substances into classes according to their constitution. What are commonly known as fruity odors belong mostly to what the chemist calls the fatty or aliphatic series. For instance, we may have in a ripe fruit an alcohol, say ethyl or common alcohol, and an acid, say acetic or vinegar, and a combination of these, the ester or organic salt, in this case ethyl acetate, which is more odorous than either of its components. These esters of the fatty acids give the characteristic savor to many of our favorite fruits, candies, and beverages. The pear flavor, amyl acetate, is made from acetic acid and amyl alcohol, although amyl alcohol, fusel oil, has a detestable smell. Pineapple is ethyl butyrate, but the acid part of it, butyric acid, is what gives Limburger cheese its aroma. These essential oils are easily made in the laboratory, but cannot be extracted from the fruit for separate use. If the carbon chain contains one or more double linkages, we get the flowery perfumes. For instance, here is the symbol of geraniol, the chief ingredient of otto of roses. Left parenthesis CH3, right parenthesis 2, C, double bond, CH, CH2, CH2, C, left parenthesis, CH3, right parenthesis, 2, double bond, CH, CH2OH. The rose would smell as sweet under another name, but it may be questioned whether it would stand being called by the name of dimethyl 2,6-octadiene 2,6-all-8. Geraniol by oxidation goes into the aldehyde, citral, which occurs in lemons, oranges, and verbena flowers. Another compound of this group, linalool, is found in lavender, bergamot, and many flowers. Geraniol, as you would see if you drew up its structural formula in the way I described in the last chapter, contains a chain of 6 carbon atoms, that is, the same number as make a benzene ring. Now, if we shake up geraniol and other compounds of this group, the diolefins, with diluted sulfuric acid, the carbon chain hooks up to form a benzene ring, but with the other carbon atoms stretched across it, rather too complicated to depict here. These bridged rings of the formula C5H8, or some multiple of that, constitute the important group of the terpenes, which occur in turpentine and such wild and woodsy things as sage, lavender, caraway, pine needles, and eucalyptus. Going further in this direction, we are led into the realm of the heavy oriental odors, patchouli, sandalwood, cedar, cubebs, ginger, and camphor. Camphor can now be made directly from turpentine, so we may be independent of Formosa and Borneo. When we have a 6-carbon ring without double linkings, cycloaliphatic, or with one or two such, we get soft and delicate perfumes like the violet, ionone, and irone. But when these pass into the benzene ring, with its 3 double linkages, the odor becomes more powerful and so characteristic that the name aromatic compound has been extended to the entire class of benzene derivatives, although many of them are odorless. The essential oils of jasmine, orange blossoms, musk, heliotrope, tuberose, ylang ylang, etc. consist mostly of this class and can be made from the common source of aromatic compounds, coal tar. The synthetic flavors and perfumes are made in the same way as the dyes by starting with some coal tar product or other crude material and building up the molecule to the desired complexity. For instance, let us start with phenol, the ill-smelling and poisonous carbolic acid of disagreeable associations and evil fame. Treat this to soda water and it is transformed into salicylic acid, a white odorless powder, used as a preservative and as a rheumatism remedy. Add to this methyl alcohol, which is obtained by the destructive distillation of wood and is much more poisonous than ordinary ethyl alcohol. The alcohol and the acid heated together will unite with the aid of a little sulfuric acid and we get what the chemists call methyl salicylate and other people call oil of wintergreen, the same as is found in wintergreen berries and birch bark. We have inherited a taste for this from our pioneer ancestors and we use it extensively to flavor our soft drinks, gum, toothpaste, and candy, but the Europeans have not yet found out how nice it is. But, starting with phenol again, let us heat it with caustic alkali and chloroform. This gives us 2 new compounds of the same composition, but differing a little in the order of the atoms. If you refer back to the diagram of the benzene ring, which I gave in the last chapter, you will see that there are 6 hydrogen atoms attached to it. Now any or all of these hydrogen atoms may be replaced by other elements or groups, and what the product is depends not only on what the new elements are, but where they are put. It is like spelling words. The 3 letters T, R, and A mean very different things according to whether they are put together as art, tar, or rat. Or, to take a more apposite illustration, every hostess knows that the success of her dinner depends upon how she seats her guests around the table. So in the case of aromatic compounds, a little difference in the seating arrangement around the benzene ring changes the character. The 2 derivatives of phenol, which we are now considering, have 2 substituting groups. One is OH, called the hydroxyl group. The other is CHO, called the aldehyde group. If these are opposite, called the para position, we have an odorless white solid. If they are side by side, called the ortho position, we have an oil with the odor of meadowsweet. Treating the odorless solid with methyl alcohol, we get audipine or acinic aldehyde, which is the perfume of hawthorn blossoms. But treating the other of the twin products, the fragrant oil, with dry acetic acid, Perkins reaction, we get coumarin, which is the perfume part of the tonka or tonkin beans that our forefathers used to carry in their snuff boxes. 1 ounce of coumarin is equal to 4 pounds of tonka beans. It smells sufficiently like vanilla to be used as a substitute for it in cheap extracts. In perfumery it is known as new mown hay. You may remember what I said on a former page about the career of William Henry Perkin, the boy who loved chemistry better than eating, and how he discovered the coal tar dyes. Well, it is also to his ingenious mind that we owe the starting of the coal tar perfume business, which has had almost as important a development. Perkin made coumarin in 1868, but this, like the dye industry, escaped from English hands and flew over the North Sea. Before the war, Germany was exporting $1.5 million worth of synthetic perfumes a year. Part of these went to France, where they were mixed up and put in fancy bottles with French names and sold to Americans at fancy prices. The real vanilla flavor, vanillin, was made by Tiemann in 1874. At first, it sold for nearly $800 a pound, but now it may be had for 10. How extensively it is now used in chocolate, ice cream, soda water, cakes and the like, we all know. It should be noted that coumarin and vanillin, however they may be made, are not imitations, but identical with the chief constituent of the tonka and vanilla beans and, of course, are equally wholesome or harmless. But the nice palate can distinguish a richer flavor in the natural extracts, for they contain small quantities of other savory ingredients. A true perfume consists of a large number of odoriferous chemical compounds mixed in such proportions as to produce a single harmonious effect upon the sense of smell. In a fine brand of perfume may be compounded a dozen or 20 different ingredients, and these, if they are natural essences, are complex mixes of a dozen or so distinct substances. Perfumery is one of the fine arts. The perfumer, like the orchestra leader, must know how to combine and coordinate his instruments to produce a desired sensation. A Wagnerian opera requires 103 musicians. A Strauss opera requires 112. Now, if the concert manager wants to economize, he will insist upon cutting down on the most expensive musicians by dropping out some of the others, say the supernumerary violinist and the man who blows a single blast or strikes a triangle once in the course of the evening. Only the trained ear will detect the difference, and the manager can make more money. Suppose our mercenary impresario were unable to get into the concert hall of his famous rival. He would then listen outside the window and analyze the sound in this fashion. 50% of the sound is made by the tuba, 20% by the bass drum, 15% by the cello, and 10% by the clarinet. There are some other instruments, but they are not loud, and I guess if we can leave them out, nobody will know the difference. So he makes up his orchestra out of these four alone, and many people do not know the difference. The cheap perfumer goes about it in the same way. He analyzes, for instance, the otto of oil of roses, which cost during the war $400 a pound, if you could get it at any price, and he finds that the chief ingredient is geraniol, costing only $5, and next is citronellol, costing $20, then comes nerol and others. So he makes up a cheap brand of perfumery out of 3 or 4 such compounds. But the genuine oil of roses, like other natural essences, contains a dozen or more constituents, and to leave many of them out is like reducing an orchestra to a few loud-sounding instruments or a painting to a 3-color print. A few years ago an attempt was made to make music electrically by producing separately each kind of sound vibration contained in the instruments imitated. Theoretically that seems easy, but practically the tone was not satisfactory because the tones and overtones of a full orchestra, or even of a single violin, are too numerous and complex to be reproduced individually. So the synthetic perfumes have not driven out the natural perfumes, but, on the contrary, have aided and stimulated the growth of flowers for essences. The otto or attar of roses, favorite of the Persian monarchs and romances, has in recent years come chiefly from Bulgaria. But wars are not made with rose water, and the Bulgars for the last 5 years have been engaged in other business than cultivating their own gardens. The alembic or still was invented by the Arabian alchemists for the purpose of obtaining the essential oil or attar of roses. But distillation, even with the aid of steam, is not altogether satisfactory. For instance, the distilled rose oil contains anywhere from 10 to 74% of a paraffin wax, stearopten, that is odorless, and, on the other hand, phenyl ethyl alcohol, which is an important constituent of the scent of roses, is broken up in the process of distillation. So the perfumer can improve on the natural or rather the distilled oil by leaving out part of the paraffin and adding the missing alcohol. But even the imported article taken direct from the still is not always genuine, for the wily Bulgar sometimes increases the yield by sprinkling his roses in the vat with synthetic geraniol, just as the wily Italian pours a barrel of American cottonseed oil over his olives in the press. Another method of extracting the scent of flowers is by enfleurage, which takes advantage of the tendency of fats to absorb odors. You know how butter set beside fish in the icebox will get a fishy flavor. In enfleurage, moist air is carried up a tower, passing alternately over trays of fresh flowers, say violets, and over glass plates covered with a thin layer of lard. The perfumed lard may then be used as a pomade or the perfume may be extracted by alcohol. But many sweet flowers do not readily yield an essential oil, so in such cases we have to rely altogether upon more or less successful substitutes. For instance, the perfumes sold under the names of heliotrope, lily of the valley, lilac, cyclamen, honeysuckle, sweet pea, arbutus, mayflower, and magnolia are not produced from these flowers, but are simply imitations made from other essences, synthetic or natural. Among the 1,000 flowers that contribute to the eau de mille fleurs are the civet cat, the musk deer, and the sperm whale. Some of the published formulas for Jockey Club call for civet or ambergris, and those of lavender water for musk and civet. The less said about the origin of these 3 animal perfumes, the better. Fortunately, they are becoming too expensive to use and are being displaced by synthetic products more agreeable to a refined imagination. The musk deer may now be saved from extinction since we can make trinitrobutylxylene from coal tar. This synthetic musk passes muster to human nostrils, but a cat will turn up her nose at it. The synthetic musk is not only much cheaper than the natural, but a dozen times as strong, or let us say, goes a dozen times as far, for nobody wants it any stronger. Such powerful scents as these are only pleasant when highly diluted, yet they are, as we have seen, essential ingredients of the finest perfumes. For instance, the natural oil of jasmine and other flowers contain traces of indols and skatols which have most disgusting odors. Though our olfactory organs cannot detect their presence, yet we perceive their absence, so they have to be put into the artificial perfume. Just so a brief but violent discord in a piece of music or a glaring color contrast in a painting may be necessary to the harmony of the whole. It is absurd to object to artificial perfumes, for practically all perfumes now sold are artificial in the sense of being compounded by the art of the perfumer, and whether the materials he uses are derived from the flowers of yesteryear or of Carboniferous era is nobody's business but his, and he does not tell. The materials can be purchased in the open market. Various recipes can be found in the books. But every famous perfumer guards well the secret of his formulas and hands it as a legacy to his posterity. The ancient Roman family of Frangipani has been made immortal by one such hereditary recipe. The Farina family still claims to have the exclusive knowledge of how to make eau de cologne. This famous perfume was first compounded by an Italian, Giovanni Maria Farina, who came to Cologne in 1709. It soon became fashionable and was for a time the only scent allowed at some of the German courts. The various published recipes contain from 6 to a dozen ingredients, chiefly the oils of neroli, rosemary, bergamot, lemon, and lavender dissolved in very pure alcohol and allowed to age like wine. The invention, in 1895, of artificial neroli, orange flowers, has improved the product. French perfumery, like the German, had its origin in Italy, when Catherine de' Medici came to Paris as the bride of Henry II. She brought with her, among other artists, her perfumer, Sieur Tuberelli, who established himself in the flowery land of Grasse. Here for 400 years the industry has remained rooted, and the family formulas have been handed down from generation to generation. In the city of Grasse there were at the outbreak of the war 50 establishments making perfumes. The French perfumer does not confine himself to a single sense. He appeals as well to sight and sound and association. He adds to the attractiveness of his creation by a quaintly shaped bottle, an artistic box, and an enticing name, such as Dans les Nuits, Le Coeur de Jeannette, Note de Chine, Un Air Embaumé, Les Vertiges, Bon Vieux Temps, La Huée Bleuée, Nuit d'Amour, Quelques Fleurs, Jerquis. The requirements of a successful scent are very strict. A perfume must be lasting, but not strong. All its ingredients must continue to evaporate in the same proportion, otherwise it will change odor and deteriorate. Scents kill another as colors do. The minutest trace of some impurity or foreign odor may spoil the whole effect. To mix the ingredients in a vessel of any metal but aluminum, or even to filter through a tin funnel, is likely to impair the perfume. The odoriferous compounds are very sensitive and unstable bodies. Otherwise they would have no effect upon the olfactory organ. The combination that would be suitable for a toilet water would not be good for a talcum powder and might spoil in a soap. Perfumery is used even in the scentless powders and soaps. In fact, it is now used more extensively, if less intensively, than ever before in the history of the world. During the unwashed ages, commonly called the Dark Ages, between the destruction of the Roman baths and the construction of the modern bathroom, the art of the perfumer, like all the fine arts, suffered an eclipse. The odor of sanctity was in highest esteem, and what that odor was may be imagined from reading the lives of the saints. But in the course of centuries the refineries of life began to seep back into Europe from the East by means of the Arabs and Crusaders, and chemistry, then chiefly the art of cosmetics, began to revive. When science, the greatest democratizing agent on earth, got into action, it elevated the poor to the ranks of kings and priests in the delights of the palate and the nose. We should not despise these delights, for the pleasure they confer is greater, in amount at least, than that of the so-called higher senses. We eat 3 times a day, some of us drink oftener. Few of us visit the concert hall or the art gallery as often as we do the dining room. Then, too, these primitive senses have a stronger influence upon our emotional nature than those acquired later in the course of evolution. As Kipling puts it, "Smells are surer than sounds or sights to make your heartstrings crack." End of chapter 5. End of section 6. Section 7, Chapter 6 of Creative Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adam Marsatich, Alexandria, Virginia, 2010. Creative Chemistry by Edwin E. Slosson. Chapter 6. Cellulose. Organic compounds, on which our life and living depend, consist chiefly of 4 elements: carbon, hydrogen, oxygen, and nitrogen. These compounds are sometimes hard to analyze, but when once the chemist has ascertained their constitution, he can usually make them out of their elements, if he wants to. He will not want to do it as a business unless it pays, and it will not pay unless the manufacturing process is cheaper than the natural process. This depends primarily upon the cost of the crude materials. What then is the market price of these 4 elements? Oxygen and nitrogen are free as air, and as we have seen in the 2nd chapter, their direct combination by the electric spark is possible. Hydrogen is free in the form of water, but expensive to extricate by means of the electric current. But we need more carbon than anything else, and where shall we get that? Bits of crystallized carbon can be picked up in South Africa and elsewhere, but those who can afford to buy them prefer to wear them rather than use them in making synthetic food. Graphite is rare and hard to melt. We must then have recourse to the compounds of carbon. The simplest of these, carbon dioxide, exists in the air, but only 4 parts in 10,000 by volume. To extract the carbon and get it into combination with the other elements would be a difficult and expensive process. Here, then, we must call in cheap labor, the cheapest of all laborers, the plants. Pine trees on the highlands and cotton plants on the lowlands keep their green traps set all the day long and with the captured carbon dioxide build up cellulose. If, then, man wants free carbon, he can best get it by charring wood in a kiln or digging up that which has been charred in nature's kiln during the Carboniferous era. But there is no reason why he should want to go back to elemental carbon when he can have it already combined with hydrogen in the remains of modern or fossil vegetation. The synthetic products on which modern chemistry prides itself, such as vanillin, camphor, and rubber, are not built up out of their elements CH and O, although they might be as a laboratory stunt. Instead of that, the raw material of the organic chemist is chiefly cellulose, or the products of its recent or remote destructive distillation, tar and oil. It is unnecessary to tell the reader what cellulose is, since he now holds a specimen of it in his hand, pretty pure cellulose except for the sizing and the specks of carbon that mar the whiteness of its surface. The utilization of cellulose is the chief cause of the difference between the modern world and the ancient, for what is called the invention of printing is essentially the inventing of paper. The Romans made type to stamp their coins and lead pipes with, and if they had had paper to print upon, the world might have escaped the Dark Ages. But the clay tablets of the Babylonians were cumbersome. The wax tablets of the Greeks were perishable. The papyrus of the Egyptians was fragile. Parchment was expensive and penning was slow, so it was not until literature was put on a paper basis that democratic education became possible. At the present time, sheepskin is only used for diplomas, treaties, and other antiquated documents. And even if your diploma is written in Latin, it is likely to be made of sulfated cellulose. The textile industry has followed the same law of development that I have indicated in the other industries. Here again we find the three stages of progress. 1. Utilization of natural products. 2. Cultivation of natural products. 3. Manufacture of artificial products. The ancients were dependent upon plants, animals, and insects for their fibers. China used silk, Greece and Rome used wool, Egypt used flax, and India used cotton. In the course of cultivation for 3,000 years, the animal and vegetable fibers were lengthened and strengthened and cheapened. But at last man has risen to the level of the worm and can spin threads to suit himself. He can now rival the wasp in the making of paper. He is no longer dependent upon the flax and the cotton plant, but grinds up trees to get his cellulose. A New York newspaper uses up nearly 2,000 acres of forest a year. The United States grinds up about 5,000,000 cords of wood a year in the manufacture of pulp for paper and other purposes. In making mechanical pulp, the blocks of wood, mostly spruce and hemlock, are simply pressed sidewise of the grain against wet grindstones. But in wood fiber the cellulose is in part combined with lignin, which is worse than useless. To break up the lignocellulose, combine chemicals are used. The logs for this are not ground fine, but cut up by disc chippers. The chips are digested for several hours under heat and pressure with acid or alkali. There are three processes in vogue. In the most common process, the reagent is calcium sulfite, made by passing sulfur fumes, SO2, into lime water. In another process, a solution of caustic of soda is used to disintegrate the wood. The third, known as the sulfate process, should rather be called the sulfide process, since the active agent is an alkaline solution of sodium sulfide made by roasting sodium sulfate with the carbonaceous matter extracted from the wood. This sulfate process, though the most recent of the three, is being increasingly employed in this country, for by means of it the resinous pine wood of the South can be worked up and the final product, known as kraft paper because it is strong, is used for wrapping. But whatever the process, we get nearly pure cellulose, which, as you can see by examining this page under a microscope, consists of a tangled web of thin white fibers, the remains of the original cell walls. Owing to the severe treatment it has undergone, wood pulp paper does not last so long as the linen rag paper used by our ancestors. The pages of the newspapers, magazines, and books printed nowadays are likely to become brown and brittle in a few years, no great loss for the most part, since they have served their purpose, though it is a pity that a few copies of the worst of them could not be printed on permanent paper for preservation in libraries so that future generations could congratulate themselves on their progress in civilization. But in our absorption in the printed page we must not forget the other uses of paper. The paper clothing, so often prophesied, has not yet arrived. Even paper collars have gone out of fashion, if they ever were in. In Germany, during the war, paper was used for socks, shirts, and shoes, as well as handkerchiefs and napkins, but it could not stand wear and washing. Our sanitary engineers have set us to drinking out of sharp-edged paper cups, and we blot our faces instead of wiping them. Twine is spun of paper and furniture made of the twine, a rival of rattan. Cloth and matting woven of paper yarn are being used for burlap and grass in the making of bags and suitcases. Here, however, we are not so much interested in manufactures of cellulose itself, that is, wood, paper, and cotton, as we are in its chemical derivatives. Cellulose, as we can see from the symbol C6H10O5, is composed of the three elements of carbon, hydrogen, and oxygen. These are present in the same proportion as in starch, C6H10O5, while glucose or grape sugar, C6H12O6, has one molecule of water more. But glucose is soluble in cold water and starch is soluble in hot, while cellulose is soluble in neither. Consequently, cellulose cannot serve us for food, although some of the vegetarian animals, notably the goat, have a digestive apparatus that can handle it. In Finland and Germany, birch wood pulp and straw were used not only as an ingredient of cattle food, but also put into war bread. It is not likely, however, that the human stomach, even under the pressure of famine, is able to get much nutriment out of sawdust. But by digesting with dilute acid, sawdust can be transformed into sugars, and these by fermentation into alcohol, so it would be possible for a man after he has read his morning paper to get drunk on it. If the cellulose, instead of being digested a long time in dilute acid, is dipped into a solution of sulfuric acid, 50 to 80%, and then washed and dried, it acquires a hard, tough, and translucent coating that makes it waterproof and greaseproof. This is the parchment paper that has largely replaced sheepskin. Strong alkali has a similar effect to strong acid. In 1844, John Mercer, a Lancashire calico printer, discovered that by passing cotton cloth or yarn through a cold 30% solution of caustic soda, the fiber is shortened and strengthened. For over 40 years little attention was paid to this discovery, but when it was found that if the material was stretched so that it could not shrink on drying, the twisted ribbons of the cotton fiber were changed into smooth-walled cylinders like silk, the process came into general use and nowadays much that passes for silk is mercerized cotton. Another step was taken when Cross of London discovered that when the mercerized cotton was treated with carbon disulfide it was dissolved into a yellow liquid. This liquid contains the cellulose in solution as a cellulose xanthate, and on acidifying or heating the cellulose is recovered in a hydrated form. If this yellow solution of cellulose is squirted out of tubes through extremely minute holes into acidulated water, each tiny stream becomes instantly solidified into a silky thread which may be spun and woven, like that ejected from the spinneret of the silkworm. The origin of natural silk, if we think about it, rather detracts from the pleasure of wearing it. And if he who needlessly sets foot upon a worm is to be avoided as a friend, we must hope that the advance of the artificial silk industry will be rapid enough to relieve us of the necessity of boiling thousands of baby worms in their cradles whenever we want silk stockings. On a plain rush hurdle a silkworm lay, when a proud young princess came that way. The haughty daughter of a lordly king threw a sidelong glance at the humble thing, little thinking she walked in pride in the winding sheet where the silkworm died. But so far we have not reached a stage where we can altogether dispense with the services of the silkworm. The viscose threads made by the process look as well as silk, but they are not so strong, especially when wet. Besides the viscose method, there are several other methods of getting cellulose into solution so that artificial fibers may be made from it. A strong solution of zinc chloride will serve and this process used to be employed for making the threads to be charred into carbon filaments for incandescent bulbs. Cellulose is also soluble in an ammoniacal solution of copper hydroxide. The liquid thus formed is squirted through a fine nozzle into a precipitating solution of caustic soda and glucose, which brings back the cellulose to its original form. In the chapter on explosives, I explained how cellulose treated with nitric acid in the presence of sulfuric acid was nitrated. The cellulose molecule having 3 hydroxyl OH groups can take up 1, 2, or 3 nitrate groups ONO2. The higher nitrates are known as gun cotton and form the basis of modern dynamite and smokeless powder. The lower nitrates, known as pyroxylin, are less explosive, although still very inflammable. All these nitrates are, like the original cellulose, insoluble in water, but unlike the original cellulose, soluble in a mixture of ether and alcohol. The solution is called collodion and is now in common use to spread a new skin over a wound. The Great War might be traced back to Nobel's cut finger. Alfred Nobel was a Swedish chemist and a pacifist. One day while working in the laboratory, he cut his finger as chemists are apt to do, and, again as chemists are apt to do, he dissolved some gun cotton in ether alcohol and swabbed it on the wound. At this point, however, his conduct diverges from the ordinary, for instead of standing idle impatiently waving his hand in the air to dry the film as most people, including chemists, are apt to do, he put his mind on it, and it occurred to him that this sticky stuff, slowly hardening to an elastic mass, might be just the thing he was hunting as an absorbent and solidifier of nitroglycerin. So instead of throwing away the extra collodion that he had made, he mixed it with nitroglycerin, and found that it set to a jelly. The blasting gelatin thus discovered proved to be so insensitive to shock that it could be safely transported or fired from a cannon. This was the first of the high explosives that have been the chief factor in modern warfare. But on the whole, collodion has healed more wounds than it has caused, besides being of infinite service to mankind otherwise. It has made modern photography possible, for the film we use in the camera and moving picture projector consists of a gelatin coating on a pyroxylin backing. If collodion is forced through fine glass tubes instead of through a slit, it comes out as a thread instead of a film. If the collodion jet is run into a vat of cold water, the ether and alcohol dissolve. If it is run into a chamber of warm air, they evaporate. The thread of nitrated cellulose may be rendered less inflammable by taking out the nitrate groups by treatment with ammonium or calcium sulfide. This restores the original cellulose, but now it is an endless thread of any desired thickness, whereas the native fiber was in size and length adapted to the needs of the cottonseed instead of the needs of man. The old motto, "If you want a thing done the way you want it, you must do it yourself," explains why the chemist has been called in to supplement the work of nature in catering to human wants. Instead of nitric acid, we may use strong acetic acid to dissolve the cotton. The resulting cellulose acetates are less inflammable than the nitrates, but they are more brittle and more expensive. Motion picture films made from them can be used in any hall without the necessity of imprisoning the operator in a fireproof box where if anything happens he can burn up all by himself without disturbing the audience. The cellulose acetates are being used for auto goggles and gas masks as well as for windows in leather curtains and transparent coverings for index cards. A new use that has lately become important is the varnishing of aeroplane wings, as it does not readily absorb water or catch fire, and makes the cloth taut and airtight. Aeroplane wings can be made of cellulose acetate sheets, as transparent as those of a dragonfly, and not easy to see against the sky. The nitrates, sulfates, and acetates are the salts or esters of the respective acids, but recently true ethers or oxides of cellulose have been prepared that may prove still better since they contain no acid radical and are neutral and stable. These are in brief the chief processes for making what is commonly but quite improperly called artificial silk. They are not the same substance as silkworm silk, and ought not to be, though they sometimes are sold as such. They are none of them as strong as the silk fiber when wet, although if I should venture to say which of the various makes weakens the most on wetting, I should get myself into trouble. I will only say that if you have a grudge against some fishermen, give them a fly line of artificial silk, most any kind. The nitrate process was discovered by Count Hilaire de Chardonnay while he was at the Polytechnic School of Paris and he devoted his life and his fortune trying to perfect it. Samples of the artificial silk were exhibited at the Paris Exposition in 1889, and 2 years later he started a factory at Besançon. In 1892 Cross and Bevan, English chemists, discovered the viscose or xanthate process, and later the acetate process. But although all four of these processes were invented in France and England, Germany reaped the most benefit from the new industry, which was bringing into that country $6,000,000 a year before the war. The largest producer in the world was the Vereinigte Glasstofffabriken of Elberfeld, which was paying annual dividends of 34% in 1914. The raw materials, as may be seen, are cheap and abundant, merely cellulose, salt, sulfur, carbon, air, and water. Any kind of cellulose can be used, cotton waste, rags, paper, or even wood pulp. The processes are various, the names of the products are numerous, and the uses are innumerable. Even the most inattentive must have noticed the widespread employment of these new forms of cellulose. We can buy from a street barrow for 15 cents near silk neckties that look as well as those sold for 75. As for wear, well, they all of them wear till after we get tired of wearing them. Paper vulcanized by being run through a 30% solution of zinc chloride and subjected to hydraulic pressure comes out hard and horny and may be used for trunks and suitcases. Viscose tubes for sausage containers are more sanitary and appetizing than the customary casings. Viscose replaces ramie or cotton in the Welsbach gas mantles. Viscose film, transparent and 1/1000th of an inch thick, cellophane, serves for candy wrappers. Cellulose acetate cylinders, spun out of larger orifices than silk, are trying, not very successfully as yet, to compete with hog's bristles and horsehair. Stir powdered metals into the cellulose solution and you have the Bayco yarn. Bayco, from the manufacturers, Farbenfabriken vorm Freder Bayer and Company, is one of those telescoped names like Sokeny, Nylick, Formenco, Alco, Ropeco, Ripans, Penyan, Anzac, Dagor, Dora, and Cadets, which will be the despair of future philologers. Soluble cellulose may enable us in time to dispense with the weaver as well as the silkworm. It may be one operation to give us fabrics instead of threads. A machine has been invented for manufacturing net and lace, the liquid material being poured on one side of a roller and the fabric being reeled off on the other side. The process seems capable of indefinite extension and application to various sorts of woven, knit, and reticulated goods. The raw material is cotton waste and the finished fabric is a good substitute for silk. As in the process of making artificial silk, the cellulose is dissolved in a cupro-ammoniacal solution, but instead of being forced out through minute openings to form threads, as in that process, the paste is allowed to flow upon a revolving cylinder which is engraved with the pattern of the desired textile. A scraper removes the excess and the turning of the cylinder brings the paste in the engraved lines down into a bath which solidifies it. Tully or net is now what is chiefly being turned out, but the engraved design may be as elaborate and artistic as desired, and various materials can be used. Since the threads wherever they cross are united, the fabric is naturally stronger than the ordinary. It is all of a piece and not composed of parts. In short, we seem to be on the eve of a revolution in textiles that is the same as that taking place in building materials. Our concrete structures, however great, are all one stone. They are not built up out of blocks, but cast as a whole. Lace has always been the aristocrat among textiles. It has maintained its exclusiveness hitherto by being based upon hand labor. In no other way could one get so much painful, patient toil put into such a light and portable form. A filmy thing twined about a neck or dropping from a wrist represented years of work by poor peasant girls or pallid, unpaid nuns. A visit to a lace factory, even to the public rooms where the worn-out women were not to be seen, is enough to make one resolve never to purchase any such thing made by hand again. But our good resolutions do not last long, and in time we forget the strained eyes and bowed backs, or, what is worse, value our bit of lace all the more because it means that some poor woman has put her life and health into it, netting and weaving, purling and knotting, twining and twisting, throwing and drawing, thread by thread, day after day, until her eyes can no longer see and her fingers have become stiffened. But man is not naturally cruel. He does not really enjoy being a slave driver, either of human or animal slaves, although he can be hardened to it with shocking ease if there seems no other way of getting what he wants. So he usually welcomes the great liberator, the machine. He prefers to drive the tireless engine than to whip the straining horses. He had rather see the farmer riding at ease in a mowing machine than bending his back over a scythe. The machine is not only the great liberator, it is the great leveler also. It is the most powerful of the forces for democracy. An aristocracy can hardly be maintained except by distinction in dress, and distinction in dress can only be maintained by sumptuary laws or costliness. Sumptuary laws are unconstitutional in this country, hence the stress laid upon costliness. But machinery tends to bring styles and fabrics within the reach of all. The shop girl is almost as well dressed on the street as her rich customer. The man who buys ready-made clothing is only a few weeks behind the vanguard of the fashion. There is often no difference perceptible to the ordinary eye between cheap and high-priced clothing once the price tag is off. Jewels as a portable form of concentrated costliness have been in favor from the earliest ages, but now they are losing their factitious value through the advance of invention. Rubies of unprecedented size, not imitation, but genuine rubies, can now be manufactured at reasonable rates. And now we may hope that lace may soon be within the reach of all, not merely lace of the established forms, but new and more varied and intricate and beautiful designs, such as the imagination has been able to conceive but the hand cannot execute. Dissolving nitrocellulose in ether and alcohol, we get the collodion varnish that we are all familiar with since we have used it on our cut fingers. Spread it on cloth instead of your skin and it makes a very good leather substitute. As we all know to our cost, the number of animals to be skinned has not increased so rapidly in recent years as the number of feet to be shod. After having gone barefoot for 1,000,000 years or so, the majority of mankind have decided to wear shoes, and this change in fashion comes at a time, roughly speaking, when pasture land is getting scarce. Also there are books to be bound and other new things to be done for which leather is needed. The war has intensified the stringency, so has feminine fashion. The conventions require that the shoe tops extend nearly to skirt bottom, and this means that an inch or so must be added to the shoe top every year. Consequent to this rise in leather, we have to pay as much for one shoe as we used to pay for a pair. Here, then, is a chance for necessity to exercise her maternal function, and she has responded nobly. A progeny of new substances have been brought forth and, what is most encouraging to see, they are no longer trying to worm their way into favor as surreptitious surrogates under the names of leatherette, leatherine, leatheroid, and leather this or that, but come out boldly under names of their own coinage and declare themselves not an imitation, not even a substitute, but better than leather. This policy has had the curious result of compelling the cowhide men to take full pages in the magazines to call attention to the forgotten virtues of good old-fashioned sole leather. There are now upon the market synthetic shoes that a vegetarian could wear with a clear conscience. The soles are made of some rubber composition, the uppers of cellulose fabric, canvas, coated with a cellulose solution such as I have described. Each firm keeps its own process for such substance a dead secret, but without prying into these, we can learn enough to satisfy our legitimate curiosity. The first of the artificial fabrics was the old-fashioned and still indispensable oilcloth, that is, canvas painted or printed with linseed oil carrying the desired pigments. Linseed oil belongs to the class of compounds that the chemist calls unsaturated and the psychologist would call unsatisfied. They take up oxygen from the air and become solid, hence are called the drying oils, although this does not mean that they lose water, for they have not any to lose. Later, ground cork was mixed with the linseed oil, and then it went by its Latin name, linoleum. The next step was to cut loose altogether from the natural oils and use for the varnish a solution of some of the cellulose esters, usually the nitrate, pyroxylin or guncotton, more rarely the acetate. As a solvent, the ether alcohol mixture forming collodion was, as we have seen, the first to be employed, but now various other solvents are in use, among them castor oil, methyl alcohol, acetone, and the acetates of amyl or ethyl. Some of these will be recognized as belonging to the fruit essences that we considered in Chapter 5. Doubtless most of us have perceived an odor as of overripe pears, bananas, or apples, mysteriously emanating from a new lacquered radiator. With powdered bronze, imitation gold, aluminum, or something of the kind, a metallic finish can be put on any surface. Canvas coated or impregnated with such soluble cellulose gives us new flexible and durable fabrics that have other advantages over leather besides being cheaper and more abundant. Without such material for curtains and cushions, the automobile business would have been sorely hampered. It promises to provide us with a bookbinding that will not crumble to powder in the course of 20 years. Linen collars may be waterproofed, and possibly Dame Fashion, being a fickle lady, may some day relent and let us wear such sanitary and economical neckwear. For shoes, purses, belts, and the like, the cellulose varnish or veneer is usually colored and stamped to resemble the grain of any kind of leather desired, even snake or alligator. If instead of dissolving the cellulose nitrate and spreading it on fabric, we combine it with camphor, we get celluloid, a plastic solid capable of innumerable applications. But that is another story and must be reserved for the next chapter. But before leaving the subject of cellulose proper, I must refer back again to its chief source, wood. We inherited from the Indians a well-wooded continent, but the pioneer carried an axe on his shoulder and began using it immediately. For 300 years the trees have been cut down faster than they could grow, first to clear the land, next for fuel, then for lumber, and lastly for paper. Consequently, we are within sight of a shortage of wood as we are of coal and oil. But the coal and oil are irrecoverable while the wood may be regrown, though it would require another 300 years and more to grow some of the trees we have cut down. For fuel, a pound of coal is about equal to 2 pounds of wood, and a pound of gasoline to 3 pounds of wood in heating value, so there would be a great loss in efficiency and economy if the world had to go back to a wood basis. But when that time shall come, as, of course, it must come sometime, the wood will doubtless not be burned in its natural state, but will be converted into hydrogen and carbon monoxide in a gas producer or will be distilled in closed ovens, giving charcoal and gas and saving the byproducts, the tar and acid liquors. As is now, the lumberman wastes 2/3 of every tree he cuts down. The rest is left in the forest as a stump, and tops or thrown out at the mill as sawdust and slabs. These slabs and other scraps may be used for fuel or worked up into small wood articles like laths and clothespins. The sawdust is burned or left to rot, but it is possible, although it may not be profitable, to save all this waste. In a former chapter I showed the advantages of the introduction of byproduct coke ovens. The same principle applies to wood as to coal. If a cord of wood, 128 cubic feet, is subjected to a process of destructive distillation, it yields about 50 bushels of charcoal, 11,500 cubic feet of gas, 25 gallons of tar, 10 gallons of crude wood alcohol, and 200 pounds of crude acetate of lime. Resinous woods such as pine wood and fir distilled with steam give turpentine and rosin. The acetate of lime gives acetic acid and acetone. The wood methyl alcohol is almost as useful as grain ethyl alcohol in arts and industry and has the advantage of killing off those who drink it promptly instead of slowly. The chemist is an economical soul. He is never content until he has converted every kind of waste product into some kind of profitable byproduct. He now has his glittering eye fixed upon the mountains of sawdust that pile up about the lumber mills. He also has a notion that he can beat lumber for some purposes. End of chapter 6. End of section 7. Section 8. Chapter 7. Of Creative Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adam Marsatich, Alexandria, Virginia, 2010. Creative Chemistry by Edwin E. Slosson. Chapter 7. Synthetic Plastics. In the last chapter I told how Alfred Nobel cut his finger and, daubing it over with collodion, was led to the discovery of high explosive, dynamite. I remarked that the first part of this process, the hurting and the healing of the finger, might happen to anybody, but not everybody would be led to discovery thereby. That is true enough, but we must not think that the Swedish chemist was the only observant man in the world. About this same time a young man in Albany named John Wesley Hyatt got a sore finger and resorted to the same remedy and was led to as great a discovery. His father was a blacksmith and his education was confined to what he could get at the seminary of Eddytown, New York, before he was 16. At that age he set out for the West to make his fortune. He made it, but after a long, hard struggle. His trade of typesetter gave him a living in Illinois, New York, or wherever he wanted to go, but he was not content with his wages or his hours. However, he did not strike to reduce his hours or increase his wages. On the contrary, he increased his working time and used it to increase his income. He spent his nights and Sundays in making billiard balls, not at the sort of thing you would expect of a young man of his Christian name, but working with billiard balls is more profitable than playing with them, though that is not the sort of thing you would expect a man of my surname to say. Hyatt had seen in the papers an offer of a prize of $10,000 for the discovery of a satisfactory substitute for ivory in the making of billiard balls, and he set out to get that prize. I don't know whether he ever got it or not, but I have in my hand a newly published circular announcing that Mr. Hyatt has now perfected a process for making billiard balls better than ivory. Meantime, he has turned out several hundred other inventions, many of them much more useful and profitable, but I imagine that he takes less satisfaction in any of them than he does in having solved the problem that he undertook 50 years ago. The reason for the prize was that the game on the billiard table was getting more popular and the game in the African jungle was getting scarcer, especially elephants having tusks more than 2 7/16 inches in diameter. The raising of elephants is not an industry that promises as quick returns as raising chickens or Belgian hares. To make a ball having exactly the weight, color, and resiliency to which billiard players have become accustomed seemed an impossibility. Hyatt tried compressed wood, but while he did not succeed in making billiard balls, he did build up a profitable business in stamped checkers and dominoes. Setting type in the way they did in the 60s was hard on the hands, and if the skin got worn thin or broken the dirty lead type were liable to infect the fingers. One day in 1863 Hyatt, finding his fingers were getting raw, went to the cupboard where was kept the liquid cuticle used by the printers. But when he got there he found it was bare, for the vial had tipped over. You know how easily they tip over, and the collodion had run out and solidified on the shelf. Possibly Hyatt was annoyed, but if so he did not waste time raging about the office to find out who tipped over that bottle. Instead, he pulled off from the wood a bit of the dried film, as big as his thumbnail, and examined it with that satiable curiosity, as Kipling calls it, which is characteristic of the born inventor. He found it tough and elastic, and it occurred to him that it might be worth $10,000. It turned out to be worth many times that. Collodion as I have explained in previous chapters, is a solution in ether and alcohol of guncotton, otherwise known as pyroxylin or nitrocellulose, which is made by the action of nitric acid on cotton. Hyatt tried mixing the collodion with ivory powder, also using it to cover balls of the necessary weight and solidity, but they did not work very well and besides were explosive. A Colorado saloon keeper wrote in to complain that one of the billiard players had touched a ball with a lighted cigar, which set it off and every man in the room had drawn his gun. The trouble with the dissolved guncotton was that it could not be molded. It did not swell up and set, it merely dried up and shrunk. When the solvent evaporated it left a wrinkled, shriveled, horny film, satisfactory to the surgeon, but not to the man who wanted to make balls and hairpins and knife handles out of it. In England, Alexander Parkes began working on the problem in 1855 and stuck to it for 10 years before he, or rather his backers, gave up. He tried mixing in various things to stiffen up the pyroxylin. Of these, camphor, which he tried in 1865, worked the best, but since he used castor oil to soften the mass articles made of Parkensine, did not hold up in all weathers. Another Englishman, Daniel Spill, an associate of Parkes, took up the problem where he had dropped it and turned out a better product, xylonite, though still sticking to the idea that castor oil was necessary to get the two solids, guncotton and the camphor, together. But Hyatt, hearing that camphor could be used and not knowing enough about what others had done to follow their false trails, simply mixed his camphor and guncotton together without any solvent and put the mixture in a hot press. The two solids dissolved one another and when the press was opened there was a clear, solid, homogeneous block of what he named celluloid. The problem was solved and in the simplest imaginable way. Tissue paper, that is, cellulose, is treated with nitric acid in the presence of sulfuric acid. The nitration is not carried so far as to produce the guncotton used in explosives, but only far enough to make a soluble nitrocellulose or pyroxylin. This is pulped and mixed with half the quantity of camphor, pressed into cakes and dried. If this mixture is put into steam-heated molds and subjected to hydraulic pressure, it takes any desired form. This process remains essentially the same as was worked out by the Hyatt brothers in the factory they set up in Newark in 1872, and some of their original machines are still in use. But this protein plastic takes innumerable forms and almost as many names. Each factory has its own secrets and lays claim to particular merits. The fundamental product itself is not patented, so trade names are copyrighted to protect the product. I have already mentioned three: Parkensine, xylonite, and celluloid, and I may add, without exhausting the list of species belonging to this genus, viscoloid, lithozyl, fiberloid, coralline, eburite, pulveroid, ivorine, pergamoid, duroid, ivortus, crystalloid, transparine, litnoid, petroid, pasbocene, selonite, and pyrrolin. Celluloid can be given any color or colors by mixing in aniline dyes or metallic pigments. The color may be confined to the surface or to the interior or pervade the whole. If the nitrated tissue paper is bleached, the celluloid is transparent or colorless. In that case, it is necessary to add an antacid such as urea to prevent its getting yellow or opaque. To make it opaque and less inflammable, oxides or chlorides of zinc, aluminum, magnesium, etc., are mixed in. Without going into the question of their variations and relative merits, we may consider the advantages of the pyroxylin plastics in general. Here we have a new substance, the product of the creative genius of man, and therefore adaptable to his needs. It is hard but light, tough but elastic, easily made and tolerably cheap. Heated to the boiling point of water, it becomes soft and flexible. It can be turned, carved, ground, polished, bent, pressed, stamped, molded, or blown. To make a block of any desired size, simply pile up the sheets and put them in a hot press. To get sheets of any desired thickness, simply shave them off the block. To make a tube of any desired size, shape, or thickness, squirt out the mixture through a ring-shaped hole or roll the sheets around a hot bar. Cut the tube into sections and you have rings to be shaped and stamped into box bodies or napkin rings. Print words or pictures on a celluloid sheet. Put a thin transparent sheet over it and weld them together, and you have something like the horn book of our ancestors, but better. Nowadays, such things as celluloid and pyrrolin can be sold under their own name, but in the early days, the artificial plastics, like every new thing, had to resort to camouflage, a very humiliating expedient, since in some cases they were better than the material they were forced to imitate. Tortoiseshell, for instance, cracks, splits, and twists, but a tortoiseshell comb of celluloid looks as well and lasts better. Horn articles are limited to size of the ceratinous appendages that can be borne on the animal's head, but an imitation of horn can be made of any thickness by wrapping celluloid sheets about a cone. Ivory, which also has a laminated structure, may be imitated by rolling together alternate white opaque and colorless translucent sheets. Some of the sheets are wrinkled in order to produce the knots and irregularities of the grain of natural ivory. Man's chief difficulty in all such work is to imitate the imperfections of nature. His whites are too white, his surfaces are too smooth, his shapes are too regular, his products are too pure. The precious red coral of the Mediterranean can be perfectly imitated by taking a cast of a coral branch and filling in the mold with celluloid of the same color and hardness. The clear luster of amber, the dead black of ebony, the cloudiness of onyx, the opalescence of alabaster, the glow of carnelian, once confined to the selfish enjoyment of the rich, are now within the reach of everyone thanks to this chameleon material. Mosaics may be multiplied indefinitely by laying together sheets and sticks of celluloid, suitably cut and colored to make up the picture, fusing the mass, and then shaving off thin layers from the end. The chef d'oeuvre of the Venetian glass makers, the Battle of Isis, from the house of the Faun in Pompeii, can be reproduced as fast as the machine can shave them off the block. And the tesserae do not fall out like those you bought on the Rialto. The process thus does for mosaics, ivory, and coral what printing does for pictures. It is a mechanical multiplier, and only by such means can we ever attain to a state of democratic luxury. The product, in cases where the imitation is accurate, is equally valuable except to those who delight in thinking that coral insects, Italian craftsmen, and elephants have been laboring for years to put a trinket into their hands. The Lord may be trusted to deal with such selfish souls according to their deserts. but it is very low praise for a synthetic product that can pass itself off more or less acceptably as a natural product. If that is all, we could do without it. It must be an improvement in some respects on anything to be found in nature or it does not represent a real advance. So celluloid and its congeners are not confined to the shapes of shell and coral and crystal, or to the grain of ivory and wood and horn, the colors of amber and amethyst and lapis lazuli, but can be given forms and textures and tints that were never known before 1869. Let me see now. Have I mentioned all the uses of celluloid? Oh no! There are handles for canes, umbrellas, mirrors and brushes, knives, whistles, toys, blown animals, card cases, chains, charms, brooches, badges, bracelets, rings, book bindings, hairpins, campaign buttons, cuff and collar buttons, cuffs, collars and dickies, tags, cups, knobs, paper cutters, picture frames, chessmen, pool balls, ping pong balls, piano keys, dental plates, masks for disfigured faces, pen holders, eyeglass frames, goggles, playing cards, and you can carry on the list as far as you like. Celluloid has its disadvantages. You may mold, you may color the stuff as you will, the scent of the camphor will cling around it still. This is not usually objectionable except where the celluloid is trying to pass itself off for something else, in which case it deserves no sympathy. It is attacked and dissolved by hot acids and alkalis. It softens up when heated, which is handy in shaping it, though not so desirable afterward, but the worst of its failings is its combustibility. It is not explosive, but it takes fire from a flame and burns furiously with clouds of black smoke. But celluloid is only one of many plastic substances that have been introduced to the present generation. A new and important group of them is now being opened up, the so-called condensation products. If you will take down any old volume of chemical research, you will find occasionally words to this effect. The reaction resulted in nothing but insoluble resin, which was not further investigated. Such a passage would be marked with a tear if chemists were given to crying over their failures, for it is the epitaph of a buried hope. It is likely meant the loss of months of labor. The reason the chemist did not do anything further with the gummy stuff that stuck up his test tube was because he did not know what to do with it. It could not be dissolved, it could not be crystallized, it could not be distilled, therefore it could not be purified, analyzed and identified. What had happened was in most cases this: the molecule of the compound that the chemist was trying to make had combined with others of its kind to form a molecule too big to be managed by such means. Financiers call the process a merger. Chemists call it polymerization. The resin was a molecular trust, indissoluble, uncontrollable, and contaminating everything it touched. But chemists, like governments, have learned wisdom in recent years. They have not yet discovered in all cases how to undo the process of polymerization, or if you prefer the financial phrase, how to unscramble the eggs. But they have found that these molecular mergers are very useful things in their own way. For instance, there is a liquid known as isoprene, C5H8. This on heating or standing turns into a gum that is nothing less than rubber, which is some multiple of C5H8. For another instance there is formaldehyde, an acrid-smelling gas used as a disinfectant. This has the simplest possible formula for a carbohydrate, CH2O. but in the leaf of a plant this molecule multiplies itself by 6 and turns into a sweet solid glucose, C6H12O6, or with the loss of water into starch, C6H10O5, or cellulose, C6H10O5. But formaldehyde is so insatiate that it not only combines with itself but seizes upon other substances, particularly those having an acquisitive nature like its own. Such a substance is carbolic acid, phenol, which, as we all know, is used as a disinfectant like formaldehyde because it, too, has the power of attacking decomposable organic matter. Now, Professor Adolf von Baeyer discovered in 1872 that when phenol and formaldehyde were brought into contact, they seized upon one another and formed a combine of unusual tenacity, that is, a resin. But as I have said, chemists in those days were shy of resins. Kleeberg in 1891 tried to make something out of it, and W. H. Story in 1895 went so far as to name the product resinite, but nothing came of it until 1909 when L. H. Baekeland undertook a serious and systematic study of this reaction in New York. Baekeland was a Belgian chemist, born at Ghent in 1863 and professor at Bruges. While a student at Ghent, he took up photography as a hobby and began to work on the problem of doing away with the darkroom by producing a printing paper that could be developed under ordinary light. When he came over to America in 1889, he brought his idea with him and 4 years later turned out Velox, which with doubtless the reader is familiar. Velox was never patented because, as Dr. Baekeland explained in his speech of acceptance of the Perkin Medal from the Chemists of America, lawsuits are too expensive. Manufacturers seem to be coming generally to the opinion that a synthetic name copyrighted as a trademark affords better protection than a patent. Later Dr. Baekeland turned his attention to the phenol condensation products, working gradually up from test tubes to ton vats according to his motto, "Make your mistakes on a small scale and your profits on a large scale." He found that when equal weights of phenol and formaldehyde were mixed and warmed in the presence of an alkaline catalytic agent, the solution separated into two layers, the upper aqueous and the lower a resinous precipitate. The resin was soft, viscous, and soluble in alcohol or acetone. But if it was heated under pressure, it changed into another and a new kind of resin that was hard, inelastic, unplastic, infusible, and insoluble. The chemical name of this product is polymerized oxybenzyl methylene glycol anhydride, but nobody calls it that, not even chemists. It is called Bakelite after its inventor. The two stages in its preparation are convenient in many ways. For instance, the porous wood may be soaked in the soft resin and then by heat and pressure it is changed to the bakelite form and the wood comes out with a hard finish that may be given the brilliant polish of Japanese lacquer. Paper, cardboard, cloth, wood pulp, sawdust, asbestos and the like may be impregnated with the resin, producing tough and hard material suitable for various purposes. Brass work painted with it and then baked at 300 degrees Fahrenheit acquires a lacquered surface that is unaffected by soap. Forced in powder or sheet form into molds under pressure of 1200 to 2000 pounds to the square inch, it takes the most delicate impressions. Billiard balls of bakelite are claimed to be better than ivory because, having no grain, they do not swell unequally with heat and humidity and so lose their sphericity. Pipe stems and beads of bakelite have the clear brilliancy of amber and greater strength. Fountain pens made of it are transparent so you can see how much ink you have left. A new and enlarging field for bakelite and allied products is the making of noiseless gears for automobiles and other machinery, also of airplane propellers. Celluloid is more plastic and elastic than bakelite. It is therefore more easily worked in sheets and small objects. Celluloid can be made perfectly transparent and colorless while bakelite is confined to the range between a clear amber and an opaque brown or black. On the other hand, bakelite has the advantage in being tasteless, odorless, inert, insoluble, and non-inflammable. This last quality and its high electrical resistance give bakelite its chief field of usefulness. Electricity was discovered by the Greeks, who found that amber, electron, when rubbed would pick up straws. This means simply that amber, like all such resinous substances, natural or artificial, is a non-conductor or dielectric and does not carry off and scatter the electricity collected on the surface by the friction. Bakelite is used in its liquid form for impregnating coils to keep the wires from short-circuiting, and in its solid form for commutators, magnetos, switch blocks, distributors, and all sorts of electrical apparatus for automobiles, telephones, wireless telegraphy, electric lighting, etc. Bakelite, however, is only one of an indefinite number of such condensation products. As Bayer said long ago, it seems that all the aldehydes will, under suitable circumstances, unite with the aromatic hydrocarbons to form resins. So instead of phenol, other coal tar products such as creosol, naphthol, or benzene itself may be used. The carbon links, CH2-methylene, necessary to hook these carbon rings together may be obtained from other substances than the aldehydes, for instance from the amines or ammonia derivatives. Three chemists, L. V. Kedman, A. J. Waithe, and F. P. Broek, working in 1910 on the industrial fellowships of the late Robert Kennedy Duncan at the University of Kansas, developed a process using formin instead of formaldehyde. Formin, or, if you insist upon its full name, hexamethylene tetramine, is a sugar-like substance with a fish-like smell. This mixed with crystallized carbolic acid and slightly warmed melts to a golden liquid that sets on pouring into molds. It is still plastic and can be bent into any desired shape, but on further heating it becomes hard without the need of pressure. Ammonia is given off in this process instead of water, which is the byproduct in the case of formaldehyde. The product is similar to bakelite. Exactly how similar is a question that the courts will have to decide. The inventors threatened to call it phenyl endecasaligenosaligenin, but rightly fearing that this would interfere with its salability, they have named it redmanol. A phenolic condensation product closely related to bakelite and redmanol is condensite, the invention of Jonas Walter Aylesworth. Aylesworth was trained in what he referred to as the greatest university of the world, the Edison Laboratory. He entered this university at the age of 19 at a salary of $3 a week, but Edison soon found that he had in his new boy an assistant who could stand being shut up in the laboratory working day and night as long as he could. After 9 years of close association with Edison, he set up a little laboratory in his own backyard to work out new plastics. He found that by acting on naphthalene, the mothball stuff, with chlorine, he got a series of useful products called halo waxes. The lower chlorinated products are oils, which may be used for impregnating paper or soft wood, making it non-inflammable and impregnable to water. If 4 atoms of chlorine enter the naphthalene molecule, the product is a hard wax that rings like a metal. Condensite is anhydrous and infusible, and like its rivals, finds its chief employment in the insulation parts of electrical apparatus. The records of the Edison phonograph are made of it. So are the buttons of our blue jackets. The government, at the outbreak of the war, ordered 40,000 goggles in condensite frames to protect the eyes of our gunners from the glare and acid fumes. The various synthetics played an important part in the war. According to an ancient military pun, the endurance of soldiers depends upon the strength of their soles. The new compound rubber soles were found useful in our army, and the Germans attribute their success in making a little leather go a long way during the late war to the use of a new synthetic tanning material known as neradol. There are various forms of this. Some are phenolic condensation products of formaldehyde, like those we have been considering, but some use coal tar compounds having no phenol groups, such as naphthalene sulfonic acid. These are now being made in England under such names as Paradol, Cresyntan, and Syntan. They have the advantage of the natural tannins such as bark in that they are of known strength and can be varied to suit. This very grasping compound, formaldehyde, will attack almost anything, even molecules many times its size. Gelatinous and albuminous substances of all sorts are solidified by it. Glue, skimmed milk, blood, eggs, yeast, brewers' slops may by this magic agent be rescued from waste and reappear in our buttons, hairpins, roofing, phonographs, shoes, or shoe polish. The French have made great use of casein hardened by formaldehyde into what is known as galalith, i.e. milkstone. This is harder than celluloid and non-inflammable, but has the disadvantages of being more brittle and of absorbing moisture. A mixture of casein and celluloid has something of the merits of both. The Japanese, as we should expect, are using the juice of the soybean, familiar as a condiment to all who patronize chop sueys or use Worcester sauce. The soy glycine, coagulated by formalin, gives a plastic said to be better and cheaper than celluloid. Its inventor, S. Sato of Sendai University, has named it, according to American precedent, Satolite, and has organized $1 million Satolite company at Mukojima. The algin extracted from the Pacific kelp can be used as a rubber surrogate for waterproofing cloth. When combined with heavier alkaline bases, it forms a tough and elastic substance that can be rolled into transparent sheets like celluloid or turned into buttons and knife handles. In Australia, when the war shut off the supply of tin, the government commission appointed to devise means of preserving fruits recommended the use of cardboard containers varnished with magramite. This is a name the Australians coined for synthetic resin made from phenol and formaldehyde like bakelite. Magramite dissolved in alcohol is painted on the cardboard cans, and when these are stoved the coating becomes insoluble. Tarasoff has made a series of condensation products from phenol and formaldehyde with the addition of sulfonated oils. These are formed by the action of sulfuric acid on coconut, castor, cottonseed, or mineral oils. The products of this combination are white plastics, opaque, insoluble, and infusible. Since I am here chiefly concerned with creative chemistry, that is, with the art of making substances not found in nature, I have not spoken of shellac, asphaltum, rosin, ozocerite, and the innumerable gums, resins, and waxes, animal, mineral, and vegetable, that are used either by themselves or in combination with the synthetics. What particular dope or mud is used to coat a canvas or form a telephone receiver is often hard to find out. The manufacturer finds secrecy safer than the patent office, and the chemist of a rival establishment is apt to be baffled in his attempt to analyze and imitate. But we of the outside world are not concerned with this, though we are interested in the manifold applications of these new materials. There seems to be no limit to these compounds, and every week the journals report new processes and patents, but we must not allow the new ones to crowd out the remembrance of the oldest and most famous of the synthetic plasters, hard rubber, to which a separate chapter must be devoted. End of chapter 7. End of section 8. Section 9. Chapter 8. Of Creative Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adam Marsatich, Alexandria, Virginia, 2010. Creative Chemistry by Edwin E. Slosson. Chapter 8. The Race for Rubber. There is one law that regulates all animate and inanimate things. It is formulated in various ways. For instance, running down a hill is easy. In Latin it reads facilis descensus averni. Herbert Spencer calls it the dissolution of definite coherent heterogeneity into indefinite incoherent homogeneity. Mother Goose expresses it in the fable of Humpty Dumpty, and the businessman extracts the moral, you can't unscramble an egg. The theologian calls it the dogma of natural depravity. The physicist calls it the second law of thermodynamics. Clausius formulates it as the entropy of the world tends toward a maximum. It is easier to smash up than to build up. Children find that this is true of their toys. The Bolsheviki have found that it is true of a civilization. So, too, the chemist knows analysis is easier than synthesis, and that creative chemistry is the highest branch of his art. This explains why chemists discovered how to take rubber apart over 60 years before they could find out how to put it together. The first is easy. Just put some raw rubber into a retort and heat it. If you can stand the odor, you will observe the caoutchouc decomposing and a benzene-like liquid distilling over. This is called isoprene. Any freshman chemist could write the reaction for this operation. It is simply C10H16 caoutchouc goes to 2C5H8 isoprene. That is, one molecule of the gum splits up into two molecules of the liquid. It is just as easy to write the reaction in the reverse directions, as 2 isoprene goes to 1 caoutchouc, but nobody could make it go in that direction. Yet it could be done. It had been done. But the man who did it did not know how he did it and could not do it again. Professor Tilden in May 1892 read a paper before the Birmingham Philosophical Society in which he said, "I was surprised a few weeks ago at finding the contents of the bottles containing isoprene from turpentine entirely changed in appearance. In place of a limpid, colorless liquid, the bottles contained a dense syrup in which were floating several large masses of a yellowish color. Upon examination, this turned out to be India rubber." But neither Professor Tilden nor anyone else could repeat this accidental metamorphosis. It was tantalizing, for the world was willing to pay $2 billion a year for rubber, and the forests of the Amazon and Congo were failing to meet the demand. A large share of these millions would have gone to any chemist who could find out how to make synthetic rubber and make it cheaply enough. With such a reward of fame and fortune, the competition among chemists was intense. It took the form of an international contest in which England and Germany were neck and neck. The English, who had been beaten by the Germans in the dye business where they had the start, were determined not to lose in this. Professor W. H. Perkin of Manchester University was one of the most eager, for he was inspired by a personal grudge against the Germans as well as by patriotism and scientific zeal. It was his father who had, 50 years before, discovered mauve, the first of the aniline dyes, but England could not hold the business and its rich rewards went over to Germany. So in 1909 a corps of chemists set to work under Professor Perkin in the Manchester laboratories to solve the problem of synthetic rubber. What reagent could be found that would reverse the reaction and convert the liquid isoprene into the solid rubber? It was discovered by accident, we may say, but it should be understood that such advantageous accidents happen only to those who are working for them and know how to utilize them. In July 1910, Dr. Matthews, who had charge of the research, set some isoprene to drying over metallic sodium, a common laboratory method of freeing a liquid from the last traces of water. In September, he found that the flask was filled with a solid mass of real rubber instead of the volatile colorless liquid he had put into it. 20 years before the discovery would have been useless, for sodium was then a rare and costly metal, a little of it in a sealed glass tube, being passed around the chemistry class once a year as a curiosity, or a tiny bit cut off and dropped in water to see what a fuss it made. But nowadays metallic sodium is cheaply produced by the aid of electricity. The difficulty lay rather in the cost of the raw material, isoprene. In industrial chemistry it is not sufficient that a thing can be made, it must be made to pay. Isoprene could be obtained from turpentine, but this was too expensive and limited in supply. It would merely mean the destruction of pine forests instead of rubber forests. Starch was finally decided upon as the best material, since this can be obtained for about a cent a pound from potatoes, corn, and many other sources. Here, however, the chemist came to the end of his rope and had to call the bacteriologist to his aid. The splitting of the starch molecule is too big a job for man. Only the lower organisms, the yeast plant, for example, know enough to do that. Owing perhaps to the Entente Cordiale, a French biologist was called into the combination, Professor Fernbach of the Pasteur Institute, and after 18 months' hard work he discovered a process of fermentation by which a large amount of fusel oil can be obtained from any starchy stuff. Hitherto the aim in fermentation and distillation had been to obtain as small a proportion of fusel as possible, for fusel oil is a mixture of the heavier alcohols, all of them more poisonous and malodorous than common alcohol. But here, as has often happened in the history of industrial chemistry, the byproduct turned out to be more valuable than the product. From fusel oil, by the use of chlorine, isoprene can be prepared, so the chain was complete. But meanwhile, the Germans had been making equal progress. In 1905, Professor Karl Harries of Berlin found out the name of the caoutchouc molecule. This discovery was to the chemists what the architect's plan of a house is to the builder. They knew then what they were trying to construct and could go about their task intelligently. Mark Twain said that he could understand something about how astronomers could measure the distance of the planets, calculate their weights and so forth, but he never could see how they could find out their names even with the largest telescopes. This is a joke in astronomy, but it is not in chemistry. For when the chemist finds out the structure of a compound, he gives it a name which means that. The stuff came to be called caoutchouc because that was the way the Spaniards of Columbus's time caught the Indian word caoutchouc. When Dr. Priestley called it India rubber, he told merely where it came from and what it was good for. But when Harries named it 1,5-dimethyl-cyclooctadiene 1,5, any chemist could draw a picture of it and give a guess as to how it could be made. Even a person without any knowledge of chemistry can get the main point of it merely by looking at this diagram. Isoprene can be converted to the rubber or caoutchouc molecule. Starting out, there are two isoprene molecules. Each isoprene molecule has 5 carbon atoms. 4 of the carbon atoms are in a straight chain with double bonds between the first 2 and last 2 carbons. A single bond joins the middle 2 carbons. The 5th carbon branches off the second carbon in the straight chain by a single bond. When reacted, the 2 isoprene molecules form one of caoutchouc. The caoutchouc or rubber molecule has a circular or ring shape. Since there were originally 10 carbons, 8 of the carbons form the ring. There are 8 ring bonds. 6 of the ring bonds are single and 2 are double. The 2 double bonds are opposite each other along the ring. The remaining 2 carbons are opposite from each other along the ring and branch from carbons connected with double bonds. The 2 extra carbons are also connected by single bonds. I have dropped the 16 H's or hydrogen atoms of the formula for simplicity's sake. They simply hook on wherever they can. You will see that the isoprene consists of a chain of 4 carbon atoms, represented by the C's, with an extra carbon on the side. In the transformation of this colorless liquid into soft rubber, 2 of the double linkages break and so permit the 2 chains of 4 C's to unite to form one ring of 8. If you have ever played Ring Around a Rosie, you will get the idea. In Chapter 4, I explain that the aniline dyes are made up upon the benzene ring of 6 carbon atoms. The rubber ring consists of 8 at least and probably more. Any substance containing That peculiar carbon chain with two double links C double bond C, single bond C, double bond C, can double up, polymerize, the chemists call it, into a rubber-like substance. So we may have many kinds of rubber, some of which may prove to be more useful than that which happens to be found in nature. With the structural formula of Harries as a clue, chemists all over the world plunged into the problem with renewed hope. The famous Bayer dye works at Elberfeld took it up, and there in August 1909 Dr. Fritz Hoffmann worked out a process for the converting of pure isoprene into rubber by heat. Then in 1910 Harries happened upon the same sodium reaction as Matthews, but when he came to get it patented, he found that the Englishman had beaten him to the patent office by a few weeks. This Anglo-German rivalry came to a dramatic climax in 1912 at the Great Hall of the College of the City of New York, when Dr. Karl Duisberg of the Elberfeld factory delivered an address on the latest achievements of the chemical industry before the 8th and the last for a long time International Congress of Applied Chemistry. Duisberg insisted upon talking in German, although more of his auditors would have understood him in English. He laid full emphasis upon German achievements and cast doubt upon the claim of the Englishman Tilden to have prepared artificial rubber in the 80s. Perkin, of Manchester, confronted him with his new process for making rubber from potatoes, but Duisberg countered by proudly displaying two automobile tires made of synthetic rubber with which he had made a 1,000-mile run. The intense antagonism between the British and German chemists at this Congress was felt by all present, but we did not foresee that in 2 years from that date they would be engaged in manufacturing poison gas to fire at one another. It was, however, realized that more was at stake than personal reputation and national prestige. Under pressure of the new demand for automobiles, the price of rubber jumped from $1.25 to $3 a pound in 1910, and millions had been invested in plantations. If Professor Perkin was right when he told the Congress that by his process rubber could be made for less than 25 cents a pound, it meant that these plantations would go the way of the indigo plantations when the Germans succeeded in making artificial indigo. If Dr. Duisberg was right when he told the Congress that synthetic rubber would certainly appear on the market in a very short time, it meant that Germany in war or peace would become independent of Brazil in the matter of rubber as she had become independent of Chile in the matter of nitrates. As it turned out, both scientists were too sanguine. Synthetic rubber has not proved capable of displacing natural rubber by underbidding it, nor even of replacing natural rubber when this is shut out. When Germany was blockaded and the success of her armies depended on rubber, price was no object. 3 Danish sailors who were caught by United States officials trying to smuggle dental rubber into Germany confessed that they had been selling it there for gas masks at $73 a pound. The German gas masks in the latter part of the war were made without rubber and were frail and leaky. They could not have withstood the new gases which American chemists were preparing on an unprecedented scale. Every scrap of old rubber in Germany was saved and worked over and diluted with fillers and surrogates to the limit of elasticity. Spring tires were substituted for pneumatics. So it is evident that the supply of synthetic rubber could not have been adequate or satisfactory. Neither, on the other hand, have the British made a success of the Perkin process, although they spent $200,000 on it in the first 2 years. But, of course, there was not the same necessity for it as in the case of Germany, for England had practically a monopoly of the world's supply of natural rubber, either through owning plantations or controlling shipping. If rubber could not be manufactured profitably in Germany when the demand was imperative and price no consideration, it can hardly be expected to compete with the natural under peace conditions. The problem of synthetic rubber has then been solved scientifically but not industrially. It can be made but cannot be made to pay. The difficulty is to find a cheap enough material to start with. We can make rubber out of potatoes, but potatoes have other uses. It would require more land and more valuable land to raise the potatoes than to raise the rubber. We can get isoprene by the distillation of turpentine, but why not bleed a rubber tree as well as a pine tree? Turpentine is neither cheap nor abundant enough. Any kind of wood, sawdust for instance, can be utilized by converting the cellulose over into sugar and fermenting this to alcohol, but the process is not likely to prove profitable. Petroleum, when cracked up to make gasoline, gives isoprene or other double bond compounds that go over into some form of rubber. But the most interesting and most promising of all is the complete inorganic synthesis that dispenses with the aid of vegetation and starts with coal and lime. These heated together in the electric furnace form calcium carbide, and this, as every automobilist knows, gives acetylene by contact with water. From this gas, isoprene can be made, and the isoprene converted into rubber by sodium, or acid or alkali, or simple heating. Acetone, which is also made from acetylene, can be converted directly into rubber by fuming sulfuric acid. This seems to have been the process chiefly used by the Germans during the war. Several carbide factories were devoted to it, but the intermediate and byproducts of the process, such as alcohol, acetic acid and acetone, were in as much demand for war purposes as rubber. The Germans made some rubber from pitch imported from Sweden. They also found a useful substitute in aluminum naphthenate made from Baku petroleum, for it is elastic and plastic and can be vulcanized. So although rubber can be made in many different ways, it is not profitable to make it in any of them. We have to rely still upon the natural product, but we can greatly improve upon the way nature produces it. When the call came for more rubber for the electrical and automobile industries, the first attempt to increase the supply was to put pressure upon the natives to bring in more of the latex. As a consequence, the trees were bled to death, and sometimes also the natives. The Belgian atrocities in the Congo shocked the civilized world, and at Putumayo on the upper Amazon the same cause produced the same horrible effects. But no matter what cruelty was practiced, the tropical forest could not be made to yield a sufficient increase, so the cultivation of the rubber was begun by far-sighted men in Dutch Java, Sumatra and Borneo, and in British Malaya and Ceylon. Brazil, feeling secure in the possession of a natural monopoly, made no effort to compete with these parvenus. It cost about as much to gather rubber from the Amazon forest as it did to raise it on a Malay plantation, that is, 25 cents a pound. The Brazilian government clapped on another 25 cents export duty and spent the money lavishly. In 1911, the treasury of Para took in $2 million from the rubber tax, and a good share of the money was spent on a magnificent new theater at Manaus, not on setting out rubber trees. The result of this rivalry between the collector and the cultivator is shown by the fact that in the decade 1907 to 1917, the world's output of plantation rubber increased from 1,000 to 204,000 tons, while the output of wild rubber decreased from 68,000 to 53,000. Besides this, the plantation rubber is a cleaner and more even product, carefully coagulated by acetic acid instead of being smoked over a forest fire. It comes in pale yellow sheets instead of big black balls loaded with the dirt or sticks and stones that the honest Indian sometimes adds to make a bigger lump. What's better, the man who milks the rubber trees on a plantation may live at home, where he can be decently looked after for. The agriculturist and the chemist may do what the philanthropist and statesman could not accomplish: put an end to the cruelties involved in the international struggle for black gold. The United States uses 3/4 of the world's rubber output and grows none of it. What is the use of tropical possessions if we do not make use of them? The Philippines could grow all our rubber and keep a $300 million business under our flag. Santo Domingo, where rubber was first discovered, is now under our supervision and could be enriched by the industry. The Guianas, where the rubber tree was first studied, might be purchased. It is chiefly for lack of a definite colonial policy that our rubber industry, by far the largest in the world, has to be dependent upon foreign sources for all its raw materials. Because the Philippines are likely to be cast off at any moment, American manufacturers are placing their plantations in the Dutch or British possessions. The Goodyear Company has secured a concession of 20,000 acres near Medan in Dutch Sumatra, while the United States is planning to relinquish its Pacific possessions. The British have more than doubled their holdings in New Guinea by the acquisition of Kaiser Wilhelm's land, good rubber country. The British Malay States in 1917 exported over $118 million worth of plantation-grown rubber and could have sold more if shipping had not been short and production restricted. Fully 90% of the cultivated rubber is now grown in British colonies or on British plantations in the Dutch East Indies. To protect this monopoly, an act has been passed preventing foreigners from buying more land in the Malay Peninsula. The Japanese have acquired there 50,000 acres, on which they are growing more than $1 million worth of rubber a year. The British Tropical Life says of the American invasion: "As America is so extremely wealthy, Uncle Sam can well afford to continue to buy our rubber as he has been doing instead of coming in to produce rubber to reduce his competition as a buyer in the world's market." The Malaya estates calculate to pay a dividend of 20% on the investment, with rubber selling at 30 cents a pound, and every 2 cents additional on the price brings a further 3.5% dividend. The output is restricted by Rubber Growers Association so as to keep the price up to 50 to 70 cents. When the plantations first came into bearing in 1910, rubber was bringing nearly $3 a pound, and since it can be produced at less than 30 cents a pound, we can imagine the profits of the early birds. The fact that the world's rubber trade was in the control of Great Britain caused America great anxiety and financial loss in the early part of the war, when the British government, suspecting, not without reason, that some American rubber goods were getting into Germany through neutral nations, suddenly shut off our supply. This threatened to kill the fourth largest of our industries, and it was only by the submission of American rubber dealers to the closest supervision and restriction by the British authorities that they were allowed to continue their business. Sir Francis Hopwood, in laying down these regulations, gave emphatic warning that in case any manufacturer, importer, or dealer came under suspicion, his permits should be immediately revoked. Reinstatement will be slow and difficult. The British government will cancel first and investigate afterward. Of course, the British had a right to say under what conditions they should sell their rubber, and we cannot blame them for taking such precautions to prevent its getting to their enemies. But it placed the United States in a humiliating position, and if we had not been in sympathy with their side, it would have aroused more resentment than it did. But it made evident the desirability of having at least part of our supply under our own control, and, if possible, within our own country. Rubber is not rare in nature, for it is contained in almost every milky juice. Every country boy knows that he can get a self-feeding mucilage brush by cutting off a milkweed stalk. The only native source so far utilized is the guayule, which grows wild on the deserts of the Mexican and the American border. The plant was discovered in 1852 by Dr. J. M. Bigelow near Escondido Creek, Texas. Professor Asa Gray described it and named it Parthenium argentatum, or the silver pallas. When chopped up and macerated, guayule gives a satisfactory quality of caoutchouc in profitable amounts. In 1911, 7,000 tons of guayule were imported from Mexico. In 1917, only 1,700 tons. Why this falling off? Because the eager exploiters had killed the goose that laid the golden egg, or in plain language, pulled up the plant by the roots. Now guayule is being cultivated and is reaped instead of being uprooted. Experiments at the Tucson laboratory have recently removed the difficulty of getting the seed to germinate under cultivation. This seems the most promising of the homegrown plants and, until artificial rubber can be made profitable, gives us the only chance of being in part independent of overseas supply. There are various other gums found in nature that can for some purposes be substituted for caoutchouc. Gutta percha, for instance, is pliable and tough, though not very elastic. It becomes plastic by heat, so it can be molded, but unlike rubber, it cannot be hardened by heating with sulfur. A lump of gutta percha was brought from Java in 1766 and placed in a British museum, where it lay for nearly 100 years before it occurred to anybody to do anything with it except to look at it. But a German electrician, Siemens, discovered in 1847 that gutta percha was valuable for insulating telegraph lines, and it found extensive employment in submarine cables as well as for golf balls and the like. Balata, which is found in the forests of the Guianas, is between gutta percha and rubber, not so good for insulation, but useful for shoe soles and machine belts. The bark of the tree is so thick that the latex does not run off like caoutchouc when the bark is cut, so the bark has to be cut off and squeezed in hand presses. Formerly this meant cutting down the tree, but now alternate strips of the bark are cut off and squeezed so the tree continues to live. When Columbus discovered Santo Domingo, he found the natives playing with balls made from the gum of the caoutchouc tree. The soldiers of Pizarro, when they conquered Inca land, adopted the Peruvian custom of smearing caoutchouc over their coats to keep out the rain. A French scientist, M. de Condamine, who went to South America to measure the earth, came back in 1745 with some specimens of caoutchouc from Para as well as quinine from Peru. The vessel on which he returned, the brig Minerva, had a narrow escape from capture by an English cruiser, for Great Britain was jealous of any trespassing on her American sphere of influence. The Old World need not have waited for the discovery of the New, for the rubber tree grows wild in Annam as well as Brazil, but none of the Asiatics seems to have discovered any of the many uses of the juice that exudes from breaks in the bark. The first practical use was made of it gave it the name that has stuck it to the English ever since. Magellan announced in 1772 that it was good to remove pencil marks. A lump of it was sent over from France to Priestley, the clergyman chemist who discovered oxygen, and was mobbed out of Manchester for being a Republican and took refuge in Pennsylvania. He cut the lump into little cubes and gave them to his friends to eradicate their mistakes in writing or figuring. Then they asked him what the queer things were, and he said that they were India rubbers. The Peruvian natives had used caoutchouc for waterproof clothing, shoes, bottles, and syringes, but Europe was slow to take it up, for the stuff was too sticky and smelled too bad in hot weather to become fashionable in fastidious circles. In 1825, Macintosh made his name immortal by putting a layer of rubber between two cloths. A German chemist, Ludersdorf, discovered in 1832 that the gum could be hardened by treating it with sulfur dissolved in turpentine, but it was left to a Yankee inventor, Charles Goodyear of Connecticut, to work out a practical solution of the problem. A friend of his, Hayward, told him that it had been revealed to him in a dream that sulfur would harden rubber, but unfortunately the angel or defunct chemist who inspired the vision failed to reveal the details of the process. So Hayward sold out his dream to Goodyear, who spent all his own money and all he could borrow from his friends trying to convert it into a reality. He worked for 10 years on the problem before the lucky accident came to him. One day in 1839 he happened to drop on the hot stove of the kitchen that he used as a laboratory a mixture of caoutchouc and sulfur. To his surprise, he saw the two substances fused together into something new. Instead of the soft, tacky gum and the yellow, brittle brimstone, he had the tough, stable, elastic solid that has done so much since to make our footing and wheeling safe, swift and noiseless. The gumshoes or galoshes that he was then enabled to make still go by the name of rubbers in this country, although we do not use them for pencil erasers. Goodyear found that he could vary this vulcanized rubber at will. By adding a little more sulfur he got a hard substance which, however, could be softened by heat so as to be molded into any form wanted. Out of this hard rubber, vulcanite or ebonite were made from combs, hairpins, penholders, and the like, and it has not yet been superseded for some purposes by any of its recent rivals, the synthetic resins. The new form of rubber made by the Germans, methyl rubber, is said to be a superior substitute for the hard variety, but not satisfactory for the soft. The electrical resistance of the synthetic product is 20% higher than the natural, so it is excellent for insulation, but it is inferior in elasticity. In the latter part of the war, the methyl rubber was manufactured at the rate of 165 tons a month. The first pneumatic tires, known then as patent aerial wheels, were invented by Robert William Thomson of London in 1846. On the following year a carriage equipped with them was seen in the streets of New York City. But the pneumatic tire did not come into use until after 1888, when an Irish horse doctor, John Boyd Dunlop of Belfast, tied a rubber tube around the wheels of his little son's velocipede. Within 7 years after that, a $25 million corporation was manufacturing Dunlop tires. Later America took the lead in this business. In 1913, the United States exported $3 million worth of tires and tubes. In 1917, the American exports rose to $13 million, not counting what went to the Allies. The number of pneumatic tires sold in 1917 is estimated at 18 million, which at an average cost of $25 would amount to $450 million. No matter how much synthetic rubber may be manufactured or how many rubber trees are set out, there is no danger of glutting the market, for as the price falls, the uses of rubber become more numerous. One can think of 1,000 ways in which rubber could be used, if only it were cheap enough. In the form of pads and springs and tires, it would do much to render traffic noiseless. Even the elevated railroad and the subway might be opened to conversation, and the city made habitable for mild-voiced and gentle folk. It would make one's step sure, noiseless and springy. Whether it was used individualistically as rubber heels or collectivistically as carpeting and paving. In roofing and siding and paint it would make our buildings warmer and more durable. It would reduce the cost and permit the extension of electrical appliances of almost all kinds. In short, there is hardly any other material whose abundance would contribute more to our comfort and convenience. Noise is an automatic alarm indicating lost motion and wasted energy. Silence is economy, and resiliency is superior to resistance. A gumshoe outlasts a hobnailed sole, and a rubber tube full of air is better than a steel tire. End of chapter 8. End of section 9. Section 10, Chapter 9, of Creative Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adam Marsatich, Alexandria, Virginia, 2010. Creative Chemistry by Edwin E. Slosson. Chapter 9. The Rival Sugars. The ancient Greeks, being an inquisitive and acquisitive people, were fond of collecting tales of strange lands. They did not care much whether the stories were true or not, so long as they were interesting. Among the marvels that the Greeks heard from the Far East, two of the strangest were that in India there were plants that bore wool without sheep, and reeds that bore honey without bees. These incredible tales turned out to be true, and in the course of time Europe began to get a little calico from Calicut, and a kind of edible gravel that the Arabs who brought it called sukkar. But of course, only kings and queens could afford to dress in calico and have sugar prescribed for them when they were sick. Fortunately, however, in the course of time, the Arabs invaded Spain and forced upon the unwilling inhabitants of Europe such instrumentalities of higher civilization as arithmetic and algebra, soap and sugar. Later, the Spaniards, by an act of equally unwarranted and beneficent aggression, carried the sugar cane to the Caribbean, where it thrived amazingly. The West Indies then became a rival of the East Indies as a treasure house of tropical wealth, and for several centuries the Spanish, Portuguese, Dutch, English, Danes, and French fought like wildcats to gain possession of this little nest of islands and the routes leading thereunto. The English finally overcame all these enemies, whether they fought her singly or combined. Great Britain became mistress of the seas and took such Caribbean lands as she wanted, but in the end her continental foes came out ahead, for they rendered her victory valueless. They were defeated in geography, but they won in chemistry. Canning boasted that the New World has been called into existence to redress the balance of the old. Napoleon might have boasted that he had called in the sugar beet to balance the sugar cane. France was then, as Germany was a century later, threatening to dominate the world. England, then as in the Great War, shut off from the seas the shipping of the aggressive power. France then, like Germany later, felt most keenly the lack of tropical products, chief among which, then but not in the recent crisis, was sugar. The cause of this vital change is that in 1747 Marggraf, a Berlin chemist, discovered that it was possible to extract sugar from beets. There was only a little sugar in the beet root then, some 6%, and what he got out was dirty and bitter. One of his pupils in 1801 set up a beet sugar factory near Breslau under the patronage of the King of Prussia, but the industry was not a success until Napoleon took it up and in 1810 offered a prize of 1,000,000 francs for a practical process. How the French did make fun of him for this crazy notion. In a comic paper of that day you will find a cartoon of Napoleon in the nursery beside the cradle of his son and heir, the King of Rome, known to the readers of Rostand as L'Aiglon. The emperor is squeezing the juice of a beet into his coffee, and the nurse has put a beet into the mouth of the infant king, saying, "Suck, dear, suck. Your father says it's sugar." In like manner did the wits ridicule Franklin for fooling with electricity, Rumford for trying to improve chimneys, Parmentier for thinking potatoes were fit to eat, and Jefferson for believing that something might be made of the country west of the Mississippi. In all ages, ridicule has been the chief weapon of conservatism. If you want to know what line human progress will take in the future, read the funny papers of today and see what they are fighting. The satire of every century from Aristophanes to the latest vaudeville has been directed against those who are trying to make the world wiser or better, against the teacher and the preacher, the scientist and the reformer. In spite of the ridicule showered upon it, the despised beet year by year gained in sweetness of the heart. The percentage of sugar rose from 6 to 18 and by improved methods of extraction became finally as pure and palatable as the sugar of the cane. An acre of German beets produces more sugar than an acre of Louisiana cane. Continental Europe waxed wealthy while the British West Indies sank into decay. As the beets of Europe became sweeter, the population of the islands became blacker. Before the war, England was paying out $125 million for sugar, and more than two-thirds of this money was going to Germany and Austria-Hungary. Fostered by scientific study, protected by tariff duties, and stimulated by export bounties, the beet sugar industry became one of the financial forces of the world. The English at home, especially the marmalade makers, at first rejoiced at the idea of getting sugar for less than cost at the expense of her continental rivals. But the suffering colonies took another view of the situation. In 1888, a conference of the powers called at London agreed to stop competing by the pernicious practice of export bounties, but France and the United States refused to enter, so the agreement fell through. Another conference 10 years later likewise failed, but when the parvenu beet sugar ventured to invade the historic home of the cane, the limit of toleration had been reached. The Council of India put on countervailing duties to protect their home-grown cane from the bounty-fed beet. This forced the calling of a convention at Brussels in 1903 to equalize the conditions of competition between beet sugar and cane sugar of the various countries, at which the powers agreed to a mutual suppression of bounties. Beet sugar then divided the world's market equally with cane sugar, and the two rivals stayed substantially neck and neck until the Great War came. This shut out from England the product of Germany, Austria-Hungary, Belgium, northern France, and Russia, and took the farmers from their fields. The battle lines of the Central Powers enclosed the land which used to grow a third of the world's supply of sugar. In 1913, the beet and the cane each supplied about 9 million tons of sugar. In 1917, the output of cane sugar was 11.2 million and of beet sugar 5.3 million tons. Consequently, the old world had to draw upon the new. Cuba, on which the United States used to depend for half its sugar supply, sent over 70,000 tons of raw sugar to England in 1916. The United States sent as much more refined sugar. The lack of shipping interfered with our getting sugar from our tropical dependencies, Hawaii, Puerto Rico, and the Philippines. The homegrown beets give us only a fifth, and the cane of Louisiana and Texas only a 15th of the sugar we need. As a result, we were obliged to file a claim in advance to get a pound of sugar from the corner grocery, and then we were apt to be put off with rock candy, muscovado, or honey. Lemon drops proved useful for Russian tea, and the long sweetening of our forefathers came again into vogue in the form of various syrups. The United States was accustomed to consume almost a fifth of all the sugar produced in the world, and then we could not get it. The shortage made us realize how dependent we have become upon sugar. Yet it was, as we have seen, practically unknown to the ancients, and only within the present generation has it become an essential factor in our diet. As soon as the chemist made it possible to produce sugar at a reasonable price, all nations began to buy it in proportion to their means. Americans, as the wealthiest people in the world, ate the most, 90 pounds a year on the average for every man, woman, and child. In other words, we ate our weight of sugar every year. The English consumed nearly as much as the Americans, the French and Germans about half as much, the Balkan peoples less than 10 pounds per annum, and the African savages none. Pure white sugar is the first and greatest contribution of chemistry to the world's dietary. It is unique in being a single definite chemical compound, sucrose, C12H22O11. All natural nutriments are more or less complex mixtures. Many of them, like wheat or milk or fruit, contain in various proportions all of the three factors of foods, the fats, the proteids, and the carbohydrates, as well as water and the minerals and other ingredients necessary to life. But sugar is a simple substance, like water or salt, and like them is incapable of sustaining life alone, although unlike them it is nutritious. In fact, except the fats, there is no more nutritious food than sugar, pound for pound, for it contains no water and no waste. It is therefore the quickest and usually the cheapest means of supplying bodily energy. But as may be seen from its formula as given above, it contains only three elements, carbon, hydrogen, and oxygen, and omits nitrogen and other elements necessary to the body. An engine requires not only coal, but also lubricating oil, water, and bits of steel and brass to keep it in repair. But as a source of the energy needed in our strenuous life, sugar has no equal and only one rival, alcohol. Alcohol is the offspring of sugar, a degenerate descendant that retains but few of the good qualities of its sire and has acquired some evil traits of its own. Alcohol, like sugar, may serve to furnish the energy of a steam engine or a human body. Used as a fuel, alcohol has certain advantages, but used as a food, it has the disqualification of deranging the bodily mechanism. Even a little alcohol will impair the accuracy and speed of thought and action, while a large quantity, as we all know from observation, if not experience, will produce temporary incapacitation. When man feeds on sugar, he splits it up by the aid of air into water and carbon dioxide in this fashion. C12H22O11 cane sugar plus 12O2 oxygen goes to 11H2O water plus 12CO2 carbon dioxide. When sugar is burned, the reaction is just the same. But when the yeast plant feeds on sugar, it carries the process only part way, and instead of water, the product is alcohol, a very different thing. So they say who have tried both as beverages. The yeast or fermentation reaction is this: C12H22O11 cane sugar plus H2O water goes to 4C2H6O alcohol plus 4CO2 carbon dioxide. Alcohol then is the first product of the decomposition of sugar, a dangerous halfway house. The twin product, carbon dioxide or carbonic acid, is a gas of slightly sour taste, which gives an attractive tang and effervescence to the beer, wine, cider, or champagne. That is to say, one of these twins is a pestilential fellow, and the other is decidedly agreeable. Yet for several thousand years mankind took to the first and let the second for the most part escape into the air. But when the chemist appeared on the scene he discovered a way of separating the two and bottling the harmless one for those who prefer it. An increasing number of people were found to prefer it, so the American soda water fountain is gradually driving demon rum out of the civilized world. The brewer nowadays caters to two classes of customers. He bottles up the beer with the alcohol and a little carbonic acid in it for the saloon, and he catches the rest of the carbonic acid that he used to waste and sells it to the drug stores for soda water or uses it to charge some non-alcoholic beer of his own. This catering to rival trades is not an uncommon thing with the chemist. As we have seen, the synthetic perfumes are used to improve the natural perfumes. Cottonseed is separated into oil and meal, the oil going to make margarine and the meal going to feed the cows that produce butter. Some people have been drinking coffee, although they do not like the taste of it, because they want the stimulating effect of its alkaloid, caffeine. Other people like the warmth and flavor of coffee, but find that caffeine does not agree with them. Formerly, one had to take the coffee whole or let it alone. Now one can have his choice, for the caffeine is extracted for use in certain popular cold drinks, and the rest of the beans sold as caffeine-free coffee. Most of the soft drinks that are now gradually displacing the hard ones consist of sugar, water, and carbonic acid, with various flavors, chiefly the esters of the fatty and aromatic acids such as I described in a previous chapter. These are still usually made from fruits and spices, and in some cases the law or public opinion requires this, but eventually, I presume, the synthetic flavors will displace the natural, and then we shall get rid of such extraneous and indigestible matter as seeds, skins, and bark. Suppose the world has always been used to synthetic, and hence seedless figs, strawberries, and blackberries. Suppose, then, some manufacturer of fig paste or strawberry jam should put in 10% of little round hard wooden nodules, just the sort to get stuck between the teeth or caught in the vermiform appendix. How long would it be before he was sent to jail for adulterating food? But neither jail nor boycott has any reformatory effect on nature. Nature is quite human in that respect, but you can reform nature as you can reform human beings by looking out for heredity and culture. In this way, Mother Nature has been quite cured of her bad habit of putting seeds in bananas and oranges. Figs she still persists in adulterating with particles of cellulose as nutritious as sawdust. But we can circumvent the old lady at this. I got on Christmas a package of figs from California without a seed in them. Somebody had taken out all the seeds. It must have been a big job. And then put the figs together again, as natural looking as life and very much better tasting. Sugar and alcohol are both found in nature. Sugar in the ripe fruit, alcohol when it begins to decay. But it was the chemist who discovered how to extract them. He first worked with alcohol and unfortunately succeeded. Previous to the invention of the still by the Arabian chemists, Man could not get drunk as quickly as he wanted to because his liquors were limited to what the yeast plant could stand without intoxication. When the alcoholic content of wine or beer rose to 17% at the most, the process of fermentation stopped because the yeast plants got drunk and quit working. That meant that man confined to ordinary wine or beer had to drink 10 or 20 quarts of water to get 1 quart of the stuff he was after, and he had no liking for water. So the chemist helped him out of this difficulty and got him into worse trouble by distilling the wine. The more volatile part that came over first contained the flavor and most of the alcohol. In this way he could get liquors like brandy and whiskey, rum and gin, containing from 30 to 80% of alcohol. This was the origin of the modern liquor problem. The wine of the ancients was strong enough to knock out Noah and put the companions of Socrates under the table. But it was not until distilled liquors came in that alcoholism became chronic, epidemic, and ruinous to whole populations. But the chemist later tried to undo the ruin he had quite inadvertently wrought by introducing alcohol into the world. One of his most successful measures was the production of cheap and pure sugar which, as we have seen, has become a large factor in the dietary of civilized countries. As a country sobers up, it takes to sugar as a self-starter to provide the energy needed for the strenuous life. A 5 o'clock candy is a better restorative than a 5 o'clock highball or even a 5 o'clock tea, for it is a true nutrient instead of a mere stimulant. It is a matter of common observation that those who like sweets usually do not like alcohol. Women, for instance, are apt to eat candy, but do not commonly take to alcoholic beverages. Look around you at a banquet table, and you will generally find that those who turn down their wine glasses generally take 2 lumps in their demi-tasses. We often hear it said that whenever a candy store opens up, a saloon in the same block closes up. Our grandmothers used to warn their daughters, "Don't marry a man who does not want sugar in his tea. He is likely to take drink." So, young man, when next you give a box of candy to your best girl and she offers you some, don't decline it. Eat it and pretend to like it, at least, for it is quite possible that she looked into a physiology and is trying you out. You never can tell what girls are up to. In the Army and Navy ration, the same change has taken place as in the popular dietary. The ration of rum has been mostly replaced by an equivalent amount of candy or marmalade. Instead of the tippling trooper of former days, we have the chocolate soldier. No previous war in history has been fought so largely on sugar and so little on alcohol as the last one. When the war reduced the supply and increased the demand, we all felt the sugar famine, and it became a mark of patriotism to refuse candy and drink coffee unsweetened. This, however, is not, as some think, a mere curtailment of a superfluous or harmful luxury, the sacrifice of a pleasant sensation. It is a real deprivation and a serious loss to national nutrition, for there is no reason to think the constantly rising curve of sugar consumption has yet reached its maximum or optimum. Individuals overeat, but not the population as a whole. According to experiments of the Department of Agriculture, men doing heavy labor may add 3/4 of a pound of sugar to their daily diet without any deleterious effects. This is at the rate of 275 pounds a year, which is 3 times the average consumption of England and America, but the department does not state how much a girl doing nothing ought to eat between meals. Of the 2,500 to 3,500 calories of energy required to keep a man going for a day, the best source of supply is the carbohydrates, that is, the sugars and starches. The fats are more concentrated but are more expensive and less easily assimilable. The proteins are also more expensive and their decomposition products are more apt to clog up the system. Common sugar is almost an ideal food, cheap, clean, white, portable, imperishable, unadulterated, pleasant tasting, germ-free, highly nutritious, completely soluble, altogether digestible, easily assimilable, requires no cooking and leaves no residue. Its only fault is its perfection. It is so pure that a man cannot live on it. 4 square lumps gives 100 calories of energy, but 25 or 35 times that amount would not constitute a day's ration. In fact, one would ultimately starve on such fare. It would be like supplying an army with an absolute abundance of powder, but neglecting to provide any bullets, clothing, or food. To make sugar the sole food is impossible. To make it the main food is unwise. It is quite proper for man to separate out the distinct ingredients of natural products, to extract the butter from the milk, the casein from the cheese, the sugar from the cane. But he must not forget to combine them again at each meal with the other essential foodstuffs in their proper proportion. Sugar is not a synthetic product, and the business of the chemist has been merely to extract and purify it. But this is not so simple as it seems, and every sugar factory has had to have its chemist. He has analyzed every mother beet for 100 years. He has watched every step of the process from the cane to the crystal, lest the sucrose should invert to the less sweet and non-crystallizable glucose. He has tested with polarized light every shipment of sugar that has passed through the custom house, much to the mystification of congressmen who have often wondered at the money and argumentation expanded in a tariff discussion over the question of the precise angle of rotation of the plane of vibration of infinitesimal waves in a hypothetical ether. The reason for this painstaking is that there are dozens of different sugars, so much alike that they are difficult to separate. They are all composed of the same 3 elements, C, H, and O, and often in the same proportion. Sometimes 2 sugars differ only in that one has a right-handed and the other a left-handed twist to its molecule. They bear the same resemblance to one another as the 2 gloves of a pair. Cane sugar and beet sugar are, when completely purified, the same substance, that is, sucrose, C12H22O11. The brown and straw-colored sugars which our forefathers used and which we took to using during the war are essentially the same, but have not been so completely freed from moisture and the coloring and flavoring matter of the cane juice. Maple sugar is mostly sucrose, so partly is honey. Candies are made chiefly of sucrose with the addition of glucose, gums, or starch to give them the necessary consistency and of such colors and flavors, natural or synthetic, as may be desired. Practically all candy, even the cheapest, is nowadays free from deleterious ingredients in the manufacture. though it is liable to become contaminated in the handling. In fact, sugar is about the only food that is never adulterated. It would be hard to find anything cheaper to add to it that would not be easily detected. Sanding the sugar, the crime of which grocers are generally accused, is the one they are least likely to be guilty of. Besides the big family of sugars which are all more or less sweet, similar in structure, and about equally nutritious, there are, very curiously, other chemical compounds of altogether different composition which taste like sugar but are not nutritious at all. One of these is a coal tar derivative discovered accidentally by an American student of chemistry, Ira Remsen, afterward president of Johns Hopkins University, and named by him saccharin. This has the composition of C6H4COSO2NH, and as you may observe from the symbol it contains sulfur S and nitrogen N and the benzene ring C6H4 that are not found in any of the sugars. It is several hundred times sweeter than sugar, though it has also a slightly bitter aftertaste. A minute quantity of it can therefore take the place of a large amount of sugar in syrups, candies, and preserves. So because it lends itself readily to deception, its use in food has been prohibited in the United States and other countries. But during the war, on account of the shortage of sugar, it came again into use. The European governments encouraged what they formerly tried to prevent, and it became customary in Germany or Italy to carry about a package of saccharin tablets in the pocket and drop one or two into the tea or coffee. Such reversals of administrative attitude are not uncommon. When the use of hops in beer was new, it was prohibited by British law, but hops became customary nevertheless, and now the law requires hops to be used in beer. When workingmen first wanted to form unions, laws were passed to prevent them. But now, in Australia for instance, the laws require workingmen to form unions. Governments naturally tend to a conservative reaction against anything new. It is amusing to turn back to the pure food agitation of 10 years ago and read the sensational articles in the newspapers about the poisonous nature of this dangerous drug, saccharin, in view of the fact that it is being used by millions of people in Europe in amounts greater than once seemed to upset the tender stomachs of the Washington poison squads. But saccharin does not appear to be responsible for any fatalities yet, though people are said to be heartily sick of it. And well they may be, for it is not a substitute for sugar except to the sense of taste. Glucose may correctly be called a substitute for sucrose as margarine for butter, since they not only taste much the same, but have about the same food value. But to serve saccharin in the place of sugar is like giving a rubber bone to a dog. It is reported from Europe that the constant use of saccharin gives one eventually a distaste for all sweets. This is quite likely, although it means the reversal within a few years of prehistoric food habits. Mankind has always associated sweetness with food value, for there are few sweet things found in nature except the sugars. We think we eat sugar because it is sweet, but we do not. We eat it because it is good for us. The reason it tastes sweet to us is because it is good for us. So man makes a virtue out of necessity, a pleasure out of duty, which is the essence of ethics. In the ancient days of India, the great Raja Trishhanku possessed an earthly paradise that had been constructed for his delectation by a magician. Therein grew all manner of beautiful flowers, savory herbs, and delicious fruits, such as had never been known before outside heaven. Of them all the Raja and his harems liked none better than the reed from which they could suck honey. But Indra, being a jealous god, was wroth when he looked down and beheld mere mortals enjoying such delights. So he willed the destruction of the enchanted garden. With drought and tempest it was devastated, with fire and hail, until not a leaf was left of its luxuriant vegetation, and the ground was bare as a threshing floor. But the roots of the sugar cane are not destroyed though the stalk be cut down. So when men ventured to enter the desert where once had been this Garden of Eden, they found the cane had grown up again, and they carried away cuttings of it and cultivated it in their gardens. Thus it happened that the nectar of the gods descended first to monarchs and their favorites, then was spread among the people and carried abroad to other lands until now any child with a penny in his hand may buy the best of it. So it has been with many things. So may it be with all things. End of chapter 9. End of section 10. Section 11, Chapter 10 of Creative Chemistry. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Adam Marsatich, Alexandria, Virginia, 2010. Creative Chemistry by Edwin E. Slosson. Chapter 10. What comes from corn? The discovery of America dowered mankind with a world of new flora. The early explorers, in their haste to gather up gold, paid little attention to the more valuable products of field and forest, but in the course of centuries their usefulness has become universally recognized. The potato and tomato, which Europe at first considered as unfit for food, or even as poisonous, have now become indispensable among all classes. New World drugs like quinine and cocaine have been adopted into every pharmacopoeia. Cocoa is proving a rival of tea and coffee, and even the banana has made its appearance in European markets. Tobacco and chicle occupy the nostrils and jaws of a large part of the human race. Maize and rubber are become the common property of mankind, but still may be called American. The United States alone raises 4/5 of the corn and uses 3/4 of the caoutchouc of the world. All flesh is grass. This may be taken in a dietary as well as a metaphorical sense. The gramineaceae provide the greater part of the sustenance of man and beast. Hay and cereals, wheat, oats, rye, barley, rice, sugarcane, sorghum, and corn. From an American viewpoint, the greatest of these, physically and financially, is corn. The corn crop of the United States for 1917, amounting to 3,159,000,000 bushels, brought in more money than the wheat, cotton, potato, and rye crops all together. When Columbus reached the West Indies he found the savages playing with rubber balls, smoking incense sticks of tobacco, and eating cakes made of a new grain that they called maíz. When Pizarro invaded Peru He found this same cereal used by the natives not only for food, but also for making alcoholic liquor, in spite of the efforts of the Incas to enforce prohibition. When the Pilgrim Fathers penetrated into the woods back of Plymouth Harbor, they discovered a cache of Indian corn. So throughout the three Americas, from Canada to Peru, corn was king, and it has proved worthy to rank with the rival cereals of other continents, the wheat of Europe and the rice of Asia. But food habits are hard to change, and for the most part, the people of the Old World are still ignorant of the delights of hasty pudding and Indian pudding, of hoe cake and hominy, of sweet corn and popcorn. I remember 30 years ago seeing on a London stand a heap of dejected popcorn balls labeled "Novel American Confection. Please try one." But nobody complied with this pitiful appeal but me, and I was sorry that I did. Americans used to respond with a shipload of corn whenever an appeal came from famine sufferers in Armenia, Russia, Ireland, India, or Austria, but their generosity was chilled when they found that their gift was resented as an insult or as an attempt to poison the impoverished population, who declared that they would rather die than eat it, and some of them did. Our Department of Agriculture sent maize missionaries to Europe with farmers and millers as educators and expert cooks to serve free flapjacks and pones, but the propaganda made little impression, and today Americans are urged to eat more of their own corn because the famished families of the war-stricken region will not touch it. Just so the beggars of Munich revolted at potato soup when the pioneer of American food chemists, Bumford, attempted to introduce this transatlantic dish. But here we are not so much concerned with corn foods as we are with its manufactured products. If you split a kernel in two, you will find that it consists of three parts: a hard and horny hull on the outside, a small oily and nitrogenous germ at the point, and a white body consisting mostly of starch. Each of these is worked up into various products, as may be seen from the accompanying table. The hull forms bran and may be mixed with the gluten as a cattle food. The corn steeped for several days with sulfurous acid is disintegrated, and on being ground the germs are floated off, the gluten or nitrogenous portion washed out, the starch grains settled down, and the residue pressed together as oil cake fodder. The refined oil from the germ is marketed as a table or cooking oil under the name of mazola, and comes into competition with olive, peanut, and cottonseed oil in the making of vegetable substitutes for lard and butter. Inferior grades may be used for soaps, or for glycerin and perhaps nitroglycerin. A bushel of corn yields a pound or more of oil. From the corn germ also is extracted a gum called paragol that forms an acceptable substitute for rubber in certain uses. The red rubber sponges and the eraser tips to pencils may be made of it and can contribute some 20% to the synthetic soles of shoes. Starch, which constitutes 55% of the corn kernel, can be converted into a variety of products for dietary and industrial uses. As found in corn, potatoes, or any other vegetables, starch consists of small, round, white, hard grains, tasteless and insoluble in cold water. But hot water converts it into a soluble, sticky form which may serve for starching clothes, or making cornstarch pudding. Carrying the process further with the aid of a little acid or other catalyst, it takes up water and goes over into a sugar, dextrose, commonly called glucose. Expressed in chemical shorthand, this reaction is C6H10O5 starch plus H2O water goes to C6H12O6 dextrose. This reaction is carried out on 40 million bushels of corn a year in the United States. The starch milk, that is, the starch grains washed out from the disintegrated corn kernel by water, is digested in large pressure tanks under 50 pounds of steam, with a few tenths of 1% of hydrochloric acid until the required degree of conversion is reached. Then the remaining acid is neutralized by caustic soda and thereby converted into common salt, which in this small amount does not interfere but rather enhances the taste. The product is the commercial glucose or corn syrup, which may, if desired, be evaporated to a white powder. It is a mixture of three derivatives of starch in about this proportion: maltose 45%, dextrose 20%, dextrin 35%. There are also present 3 or 4/10ths of 1% salt and as much of the corn protein and a variable amount of water. It will be noticed that the glucose, dextrose, which gives name to the whole, is the least of the three ingredients. Maltose or malt sugar has the same composition as cane sugar, C12H22O11, but is not nearly so sweet. Dextrin or starch paste is not sweet at all. Dextrose or glucose is otherwise known as grape sugar, for it is commonly found in grapes and other ripe fruits. It forms half of honey and is one of the two products into which cane sugar splits up when we take it into the mouth. It is not so sweet as cane sugar and cannot be so readily crystallized, which, however, is not altogether a disadvantage. The process of changing starch into dextrose that takes place in the great steam kettles of the glucose factory is essentially the same as that which takes place in the ripening of fruit and in the digestion of starch. A large part of our nutriment, therefore, consists of glucose either eaten as such in ripe fruits or produced in the mouth or stomach by the decomposition of the starch of unripe fruit, vegetables, and cereals. Glucose may be regarded as a pre-digested food. In spite of this well-known fact, we sometimes read poor food articles in which glucose is denounced as a dangerous adulterant and even classed as a poison. The other ingredients of commercial glucose, the maltose and dextrin, have of course the same food value as the dextrose, since they are made over into dextrose in the process of digestion. Whether the glucose syrup is fit to eat depends, like anything else, on how it is made. If, as was formerly sometimes the case, sulfuric acid was used to effect the conversion of the starch, or sulfurous acid to bleach the glucose, and these acids were not altogether eliminated, the product might be unwholesome or worse. Some years ago in England there was a mysterious epidemic of arsenical poisoning among beer drinkers. On tracing it back, it was found that the beer had been made from glucose, which had been made from sulfuric acid, which had been made from sulfur, which had been made from a batch of iron pyrites, which contained a little arsenic. The replacement of sulfuric acid by hydrochloric has done away with that danger, and the glucose now produced is pure. The old recipe for homemade candy called for the addition of a little vinegar to the sugar syrup to prevent graining. The purpose of the acid was of course to invert part of the cane sugar to glucose, so as to keep it from crystallizing out again. The professional candy maker now uses the corn glucose for that purpose, so if we accuse him of adulteration on that ground, we must levy the same accusation against our grandmothers. The introduction of glucose into candy manufacture has not injured but greatly increased the sale of sugar for the same purpose. This is not an uncommon effect of scientific progress, for as we have observed, the introduction of synthetic perfumes has stimulated the production of odoriferous flowers, and the price of butter has gone up with the introduction of margarine. So, too, there are more weavers employed and they get higher wages than in the days when they smashed up the first weaving machines, and the same is true of printers and typesetting machines. The popular animosity displayed toward any new achievement of applied science is never justified, for it benefits not only the world as a whole, but usually even those interests with which it seems at first to conflict. The chemist is an economizer. It is his special business to hunt up waste products and make them useful. He was, for instance, worried over the waste of the cores and skins and scraps that were being thrown away when apples were put up. Apple pulp contains pectin, which is what makes jelly gel, and berries and fruits that are short of it will refuse to gel. But using these for their flavor, he adds apple pulp for pectin and glucose for smoothness and sugar for sweetness, and if necessary, synthetic dyes for color. He is able to put on the market a variety of jellies, jams, and marmalades at very low price. The same principle applies here as in the case of all compounded food products. If they are made in cleanly fashion, contain no harmful ingredients, and are truthfully labeled, there is no reason for objecting to them. But if the manufacturer goes so far as to put strawberry seeds or hayseed into his artificial strawberry jam, I think that might properly be called adulteration, for it is imitating the imperfections of nature, and man ought to be too proud to do that. The old-fashioned open kettle molasses consisted mostly of glucose and other invert sugars together with such cane sugar as could not be crystallized out. But when the vacuum pan was introduced, the molasses was impoverished of its sweetness, and beet sugar does not yield any molasses. So we now have in its place the corn syrups consisting of about 85% of glucose and 15% of sugar, flavored with maple or vanillin or whatever we like. It is encouraging to see the billboards proclaiming the virtues of Caro syrup and Mazola oil, when only a few years ago the products of our national cereal were without honor in their own country. Many other products besides foods are made from cornstarch. Dextrin serves in place of the old gum arabic for the mucilage of our envelopes and stamps. Another form of dextrin, sold as Cordex, is used to hold together the sand of the cores of castings. After the casting has been made, the scorched core can be shaken out. Glucose, is used in place of sugar as a filler for cheap soaps and for leather. Altogether, more than 100 different commercial products are now made from corn, not counting cob pipes. Every year, the factory of the United States work up over 50 million bushels of corn into 800 million pounds of corn syrup, 600 million pounds of starch, 230 million pounds of corn sugar, 625 million pounds of gluten feed, 90 million pounds of oil, and 90 million pounds of oil cake. 2 million bushels of cobs are wasted every year in the United States. Can't something be made out of them? This is the question that is agitating the chemists of the Carbohydrate Laboratory of the Department of Agriculture at Washington. They have found it possible to work up the corn cobs into glucose and xylose by heating with acid. But glucose can be more cheaply obtained from other starchy or woody materials, and they cannot find a market for the xylose. This is a sort of sugar, but only about half as sweet as that from cane. Who can invent a use for it? More promising is the discovery by this laboratory that by digesting the cobs with hot water there can be extracted about 30% of a gum suitable for bill posting and labeling. Since the starches and sugars belong to the same class of compounds as the celluloses, they also can be acted upon by nitric acid with the production of explosives like gun cotton. Nitro sugar has not come into common use, but nitro starch is found to be one of the safest of the high explosives. On account of the danger of decomposition and spontaneous explosion from the presence of foreign substances, the materials in explosives must be of the purest possible. It was formerly thought that tapioca must be imported from Java for making nitro starch, but during the war, when shipping was short, the War Department found it could be made better and cheaper from our homegrown corn starch. When the war closed, the United States was making 1.72 million pounds of nitro starch a month for loading hand grenades. So too, the Post Office Department discovered that it could use mucilage made of corn dextrin, as well as that which used to be made from tapioca. This is progress in the right direction. It would be well to divert some of the energetic efforts now devoted to the increase of commerce to the discovery of ways of reducing the need for commerce by the development of home products. There is no merit in simply hauling things around the world. In the last chapter, we saw how dextrose or glucose could be converted by fermentation into alcohol. Since cornstarch, as we have seen, can be converted into dextrose, it can serve as a source of alcohol. This was, in fact, one of the earliest misuses to which corn was put, and before the war put a stop to it, 34 million bushels went into the making of whiskey in the United States every year, not counting the moonshiners' output. But even though we left off drinking whiskey, the distillers could still thrive. Mars is more thirsty than Bacchus. The output of whiskey, denatured for industrial purposes, is more than 3 times what it was before the war, and the price has risen from 30 cents a gallon to 67 cents. This may make it profitable to utilize sugars, starches, and cellulose that formerly were out of the question. According to the calculations of the Forest Products Laboratory of Madison, it costs from 37 to 44 cents a gallon to make alcohol from corn, but it may be made from sawdust at a cost from 14 to 20 cents. This is not wood alcohol, that is methyl alcohol, CH4O, such as is made by the destructive distillation of wood, but genuine grain alcohol, ethyl alcohol, C2H6O, such as is made by the fermentation of glucose or other sugar. The first step in the process is to digest the sawdust or chips with dilute sulfuric acid under heat and pressure. This converts the cellulose, wood fiber, in large part into glucose, corn sugar, which may be extracted by hot water in a diffusion battery as in extracting the sugar from beet chips. This glucose solution may then be fermented by yeast and the resulting alcohol distilled off. The process is perfectly practicable but has not yet been proved profitable. But the sulfite liquors of the paper mills are being worked up successfully into industrial alcohol. The rapidly approaching exhaustion of our oil fields, which the war has accelerated, leads us to look around to see what we can get to take the place of gasoline. One of the most promising of the suggested substitutes is alcohol. The United States is exceptionally rich in mineral oil, but some countries, for instance England, Germany, France, and Australia, have little or none. The Australian Advisory Council of Science, called to consider the problem, recommends alcohol for stationary engines and motor cars. Alcohol has the disadvantage of being less volatile than gasoline, so it is hard to start up the engine from the cold. But the lower volatility and ignition point of alcohol are an advantage in that it can be put under a pressure of 150 pounds to the square inch. A pound of gasoline contains 50% more potential energy than a pound of alcohol, but since the alcohol vapor can be put under twice the compression of the gasoline and requires only 1/3 the amount of air, the thermal efficiency of an alcohol engine may be 50% higher than that of a gasoline engine. Alcohol also has several other conveniences that can count in its favor. In the case of incomplete combustion, the cylinders are less likely to be clogged with carbon and the escaping gases do not have the offensive odor of the gasoline smoke. Alcohol does not ignite so easily as gasoline and the fire is more readily put out, for water thrown upon blazing alcohol dilutes it and puts out the flame, while gasoline floats on water and the fire is spread by it. It is possible to increase the inflammability of alcohol by mixing with it some hydrocarbon such as gasoline, benzene, or acetylene. In the Taylor-White process, the vapor from low-grade alcohol containing 18% water is passed over calcium carbide. This takes out the water and adds acetylene gas, making a suitable mixture for an internal combustion engine. Alcohol can be made from anything of a starchy, sugary, or woody nature, that is, from the main substance of all vegetation. If we start with wood, cellulose, we convert it first into sugar, glucose, and of course we could stop here and use it for food instead of carrying it on into alcohol. This provides one factor of our food, the carbohydrate, but by growing the yeast plants on glucose and feeding them with nitrates made from the air, we can get the protein and fat. So it is quite possible to live on sawdust, although it would be too expensive a diet for anybody but a millionaire, and he would not enjoy it. Glucose has been made from formaldehyde and this in turn made from carbon, hydrogen, and oxygen. So the synthetic production of food from the elements is not such an absurdity as it was thought when Berthelot suggested it half a century ago. The first step in the making of alcohol is to change the starch over into sugar. This transformation is effected in the natural course of sprouting, by which the insoluble starch stored up in the seed is converted into the soluble glucose for the sap of the growing plant. This malting process is that mainly made use of in the production of alcohol from grain. But there are other ways of effecting the change. It may be done by heating with acid, as we have seen, or according to a method now being developed, the final conversion may be accomplished by mold instead of malt. In applying this method, known as the amylo process, to corn, the meal is mixed with twice its weight of water, acidified with hydrochloric acid and steamed. The mash is then cooled down somewhat, diluted with sterilized water, and inoculated with the mucor filaments. As the mash molds, the starch is gradually changed over to glucose, and if this is the product desired, the process may be stopped at this point. But if alcohol is wanted, yeast is added to ferment the sugar. By keeping it alkaline and treating with the proper bacteria, a high yield of glycerin can be obtained. In the fermentation process for making alcoholic liquors, a little glycerin is produced as a byproduct. Glycerin, otherwise called glycerol, is an intermediate between sugar and alcohol. Its molecule contains 3 carbon atoms, while glucose has 6 and alcohol 2. It is possible to increase the yield of glycerin, if desired, by varying the form of fermentation. This was desired most earnestly in Germany during the war, for the British blockade shut off the importation of the fats and oils from which the Germans extracted the glycerin for their nitroglycerin. Under pressure of this necessity, they worked out a process of getting glycerin in quantity from sugar, and news of this being brought to this country by Dr. Alonzo Taylor, the United States Treasury Department set up a special laboratory to work out this problem. John R. Eoff and other chemists working in this laboratory succeeded in getting a yield of 20% of glycerin by fermenting blackstrap molasses or other syrup from California wine yeast. During the fermentation, it is necessary to neutralize the acetic acid formed with sodium or calcium carbonate. It was estimated that glycerin could be made from waste sugars at about a quarter of its wartime cost, but it is doubtful whether the process would be profitable at normal prices. We can, if we like, dispense with either yeast or bacteria in the production of glycerin. Glucose syrup suspended in oil under steam pressure with finely divided nickel as a catalyst and treated with nascent hydrogen will take up the hydrogen and be converted into glycerin. But the yield is poor and the process expensive. Food serves substantially the same purpose in the body as fuel in the engine. It provides the energy for work. The carbohydrates, that is, the sugars, starches, and celluloses, can all be used as fuels and can all, even, as we have seen, the cellulose, be used as foods. The final products, water and carbon dioxide, are in both cases the same, and necessarily therefore the amount of energy produced is the same in the body as in the engine. Corn is a good example of the equivalence of the two sources of energy. There are few better foods and no better fuels. I can remember the good old days in Kansas when we had corn to burn. It was both an economy and a luxury, for, at 10 cents a bushel, it was cheaper than coal or wood, and preferable to either at any price. The long yellow ears, each wrapped in its own kindling, could be handled without crocking the fingers. Each kernel as it crackled sent out a blazing jet of oil, and the cobs left a fine bed of coals for the corn popper to be shaken over. Driftwood in the pyrotechnic fuel they make now by soaking sticks in strontium and copper salts cannot compare with the old-fashioned corn-fed fire in beauty and the power of evoking visions. Doubtless such luxury could be condemned as wicked nowadays, but those who have known the calorific value of corn would find it hard to abandon it altogether, and I fancy that the Western farmer's wife, when she has an extra batch of baking to do, will still steal a few ears from the crib. End of chapter 10. End of section 11.